Good morning, all. Am I audible? Everything is good in terms of audio, video. Okay, thank you. Good morning, all. Good morning. The videos were never meant to be available on the channel. It is about interaction with me for your doubts. PGIOH556, I don't know your name, sorry. The whole point was a live interaction. Otherwise, I could have easily recorded this session at my leisure time and published it. Why am I doing it live? Not for you to see recordings. Right? So the videos have been pulled down. If you are attending this, you are attending this. If you are not attending this, you are missing this. That is the whole point. So keep attending. That's my request. Today's topics are heavyweight topics. If you understand today's topics, at least 50% of your problem is over. Good morning, Abhinav. Okay, we start in 10 minutes. Let's see how many of you join. Today being a Saturday, it should be easier for you than yesterday. Good morning, Rick. Morning, Ashmita. Good morning, Shirajit. I hope the lag is better today, in the sense that it is less. Shubhodev, good morning. Okay, 5 more minutes, we'll get started. I see 34 now. Anyone has any idea why we have dropped so much on the attendance? Today is Messi's session, is it? People have gone out to watch Messi. Okay, we'll live with whatever joins, because anyways you have joined keeping your other commitments, so we will go ahead and have the session, not a problem. But 35 out of 450 registrations is not what I was expecting, but that's okay. We'll live with it. Let's see if this grows as we go forward. So I thought today was more important topics, more people will join than yesterday. But if this is how all of you want it to be, then this is how it will be. I will complete the session, don't worry. We will do as per what our plan is. And again, I will publish the quiz results at the end of day today, which will be an aggregation of yesterday and today. And have a look. I hope all of you have updated your last names to include your registration numbers, roll numbers. And with that we can move on. Those who have had without a roll number and then a registration number, it's very difficult to actually aggregate it from a coding perspective, because there are chances that somebody else's name might be the same, and hence the roll number was asked. So while I'll make an attempt tonight to see if more optimizations can be done to the list to accommodate more people who did not give their roll numbers. Worst case scenario, the quizzes that you did without your roll numbers would remain separate, and the quizzes that you gave with the roll numbers will remain separate. So 2 entities will be there for you, but each of the entities will be ranked differently. That is the worst case scenario. Niladri, good morning. Priyam, good morning. Okay, so let's wait for a couple of more minutes and then we'll get started. Good morning, Samiran. Jeet Nandi, good morning. Okay, so it's 9. Let us start. Good morning, everybody. We are starting with 2 heavyweight topics today. Mostly 40 to 50% of your marks will be from these 2 topics. Remaining 20 will be from tomorrow's topic, which is the graph, traversals, etc. And the rest of 30-20% will be from your yesterday's topics that we had covered. So that's the weightage that I have seen as far as the last few years of questions is concerned. So if today and tomorrow's topics you do properly, you should be able to have 70% of the syllabus completed. That's my guarantee to you. So let us try to understand whatever you don't understand. Mostly some of it will be new to you, some of it may not be new to you. So if it is not new to you, be patiently with me. Some words, some sentences might be new even in that topic. So be attentive is what my request is. Try to bring a different mindset than yesterday. Yesterday we had good interactions. Please continue those good interactions. Otherwise, I feel demotivated. Ask good questions. Let me answer them. And I have already posted a Google Sheet or a Google form where you can post what all you want to be discussed in second half tomorrow. So we will take that up in second half tomorrow. Please keep putting your thoughts into that Google form so that we have an aggregated list of things that we want to discuss. That's my earnest request. Today, try to bring in a different thought process, different mindset. That's my only request, because as I said, today and tomorrow will be 70% of your syllabus. So if you put some extra effort in order to understand what is happening, then I'm sure you will be able to get a head start into the DSA paper before your final revisions. So with that, let us start. We have 70 people in the chat, and I hope this increases beyond 100 as we go forward. Thank you for joining, but don't just join, be in the entire session is what my request is. Again, I will repeat, I cannot stress enough how important these two sessions will be along with tomorrow's session. 70% of your questions will be from these three sessions. Today 2 sessions and tomorrow half session. So please be attentive. Please understand what is happening. Please ask questions. Please make it interactive. And with that, let us start today's session. If you have who is this? He's saying, when will today's class start? Please send me the link. They are not part of. I thought everybody was part of the WhatsApp group. One minute, let me send the link to her. Okay, so today we have some 9 quizzes lined up. So we will want you to participate in all those quizzes. I have made an attempt to aggregate the quiz results from yesterday, and then you have seen the results from yesterday. We will aggregate again the results from today's sessions. So please participate in the quizzes. I have convinced Techno International Newtown to increase the number of prizes from 3 to 5. So top 5 will now get a prize or a goodie bag once the sessions are over. We will announce when that goodie bag will be available, and it will be available for you to collect. So that's on the quiz part of it. So let us start today's sessions. We start off with linked list, and you have already seen this, so I will not waste time on this. That was the agenda for today. Now if you see linked list, then first let us talk about what is a linked list. Most of you know about it, but as I said, please be attentive. Even if one sentence, one word is new to you, that my tab is not working. Let me see. Yeah. Okay. So what is a linked list? From a linked list perspective, we know that in an array, it is a contiguous memory location. So if I want, let's say 100 pockets from an array, and my memory does not have 100 locations in a continuous manner. It has 100 locations, but sporadically. Let us say that in the memory, my 100 locations are like this. Let us say this is my memory, and in the memory, this is blocked, this is blocked, this is available, this is blocked, this is blocked, this is blocked. So even if I ask 10 locations, I will not get 10 contiguous locations, right? I will not get it. So, but if I ask linked list to create 10 nodes, linked list can create 10 nodes. Each location for linked list can be independent. It need not be back to back. It need not be side by side. So that is the main advantage of a linked list, that you are able to use memory in an optimized manner as compared to an array, where an array will say always give me contiguous memory locations. Do not give me any memory location which are not contiguous, because array works on incrementing the pointer and going to the next location. So if it is not contiguous, it will not work. That is the simplest way to understand it. Now if I take this linked list as an example, then typically a linked list will include what? Include a payload. Now the payload is the data that we call it. So I would call it as a payload. So linked list has a payload, and linked list will, because it has to be linked, it will have to have the link to the next node. We call these as nodes. The boxes which actually contain the payloads. Payload means anything that it can store, any data that it can store. The purpose of it, right? The purpose of it was to store something. So that storage, whatever it stores, is called as the payload. So that's the payload here. So every linked list will have a payload. Now payload can be comprising of a structural entity. You can have many different native data types, like a character, like an integer inside this structure, and you can say this entire structure is my payload. You can say that, or you can just say that my payload is as simple as one integer. That is also something you can say. So any kind of data type can be a part of the payload, right? In our example of whatever we do going forward, we will be using the example where my payload is an integer and my next, that is the link that is being stored with the current node and the next node, so that the first node can actually know where the next node is, and the next node can know where the next node is, and so on and so forth. And that is why we are saying that my next node will be having a pointer, or my next pointer will be having the address of the actual next node. So if this actually gets created at 1000 memory location and this gets created at 2000 memory location, then here I am going to store 2000, which means that now this particular node knows where the next node is. The next node knows where the next node is. So here also I will have a payload. Here also I will have, let's say this is 3000 location, and this particular node will need to have a link to the next node, which means it needs to know where the next node is. That is the address of the next node, right? So that is where, and what is this pointer? What is this pointing towards? This is pointing towards the same kind of node. I was this is my entity. What am I? I am a node. What am I pointing to? I am also pointing to a node. That is why if you see here that the pointer is of the same data type as yourself. Pointer is of the same data type as yourself, because whatever you are pointing to a similar kind of a entity. That is why the entity which is star next will be of type struct node. So that is how you need to interpret the structural organization of a linked list. Now this would mean that we will need to start from somewhere. So we need to maintain one more pointer which we call as head, and the head pointer will contain the starting node's address. In this case it is 1000. So now head starts pointing towards this particular node. So if I know head, then I can come here and utilize the next pointer to go here, then again a next pointer to go here, and then finally at the end I will have some way to understand that I don't need to go further. That is, my total data has ended, which means that there will be a null there in terms of this particular pointer. So this pointer will therefore have null to signify that this node does not link up with any other node. That is, the pointer is null means the pointer is not pointing anywhere, so which means it is that significance. Now if I take some operations of linked list that we will typically cover, then those operations are listed on the left, right? So if I take those operations and start explaining one by one quickly, what you will understand is that when we talk about any kind of browsing or traversal, for lack of better words, then that traversal means that we will start from here and somehow we will navigate to this particular data, right? And then we will move forward using this particular next address. You see, this is at 3600. So we will use this to go to the next. Again, use this data, use this to go to the next, and so on and so forth. That is called as traversal. So going from here to here to here to here and investigating each element for our own purpose, whatever that purpose is called as traversal. So if you actually traverse, what is the order of it? Because you might be traversing for going through all the nodes. So if you are going through all the nodes, then don't you think the traversal is a function of n? Right? The more the number of elements, more the number of nodes, traversal will take more time, because I'm going one at a time. So if there are 100, I'll have to go 100 times. So that's why the time complexity for traversal is an order of n. When you are actually inserting, then there are three possibilities of insertions. The three possibilities of insertions are insertion at the beginning. So if I say that I will have a node here, if I say I have a node here, then this node will have to be inserted means what? This node will have to be inserted means that this node will now, the head will now start pointing to this node. So I will have to cancel this connection and utilize that connection to this node, and I will have to make this point here, right? So the next pointer of this, so let's say this is a data and this data is 7. However, the next pointer of this should now contain 3200, because 3200 is the address of my next node. So net what will become is that I will start from here, I'll come here, this is my first node, the next will take me here, and then I will move on. So what did I do? I inserted this node at the beginning, right? So 15 was the first node, now 15 becomes the second node. That's what is insert at beginning. Now if I take insert at the end, then the same thing we will do. We will have a node here. This will be the node. Let us say it is 75 we are trying to insert. At the end means, of course, the last, it is at the last, so the pointer will be, the next pointer will be null. So if the next pointer is null, then what we will do is, we will, this node is so far so good, but then this node should be now connected. This last node, which was the last node, is no more the last node. So this node has to be connected like this, right? So then only we can have a continuous like this, right? So how will we connect this node? We will say that your null is not going to be null anymore. It will store the actual address of this. So let's say the actual address of this is 4700. Then it will start storing 4700 here. And that's it. So 4700 means it will start storing that, and 4700 will take it to this particular last node, and then we will have a null, which means it will end. So if I am browsing, I will come through the head here, and then with 4700 I will enter here, and then I will see null, I will stop. So that is how you do the insertion at the end. The next thing that you are supposed to probably remember is that, okay, insertion at beginning, insertion at end, I understand. What about insertion at the between, or at a position, or after a key? Whatever it is, it will give you a position, right? So let us say that my position is here. I want to insert here a particular node, right? So if I want to insert here a particular node, then don't you think that this pointer becomes invalid? Therefore, we have to say that this pointer will start pointing here, right? So this pointer will start pointing here. So then if this is 4700, then this pointer should now start saying 4700, and then this should now point here, which means I should be saying that 4000 will be the address of this particular next pointer of this new node that I am entering. Let's say the value of this new node is 75 that I am inserting, right? So then what did I do? I removed this pointer, I created one pointer here, I created one more pointer here. So there were 3 pointer adjustments I have done, right? So remember, throughout this session we will talk about pointer adjustments, and it comes, so remember those pointer adjustments or the number of times the pointer adjustments happen. So if you take the insertion process, the 3 steps that we discussed, the first step will take an order of 1, because we are taking the node here and inserting it. The second step also we are taking it here and inserting it, but in order to reach the last node, we have to reach the last node to insert this here. So I have to go like this to reach the last node, right? So once I reach, I can insert at the end. So the order of insertion will be at the end, at the end will be order of n. Whereas if I am inserting in between, then I am traversing like this. Here also the order will be order of n. Why? Because this could also be the last node, right? I could have said that it is going to be inserted after 90. Rather than saying last node, I could have said that it is going to be inserted after 90. In that case also, it is going to be order of n. So the worst case scenario for insert at position will be order of n. Now, Just checking the live if there are any thing regarding the infrastructure. Okay, so everybody is okay. Deletion. If we talk about deletion now, exactly the same thing as insertion. I will not spend much time on deletion. You can yourself understand. I will just take one simple example. If I am deleting this record, what would happen? This node, this record pointer should come here. That's all I'm saying. And I should free this memory. These are the two steps we will do. So you will see some algos as we go along the way. And that's how that will happen. So deletion from the beginning will also be order of 1. I don't need to do anything to traverse. But deletion from the end, if I have to go like this and delete this, then I'm actually using my n iterations. So that's why we will have order of n as deletion from the end. But if I'm deleting this node, then also I have to come like this and delete this node. Instead of the last node, even if I'm deleting in-between node, that still will be order of n, because this in-between node could also be the last node, because I'm searching for that node. I don't know where I'll get it. So at any point of time, if I get it, I will delete it, and that could be the last node. That is why we are saying order of n there also. Now next is on the searching part of it. Searching part of it, again, same thing. If I am actually searching for some node, let's say I'm searching for 90. How many iterations will I take? 1, 2, 3, 4. And we had 4 nodes. So we took order of n. So searching will also be order of n. Updating, if I'm trying to update 90 with, let's say 100, then I will traverse like this 1, 2, 3, 4 and then update. So how many times did I do? 4. Size is 4, order of n. So that is in a nutshell all the actual functions or methodologies or the operations that you will do on a linked list. And for each of those operations, we have talked about what will be the order. So the orders are sporadically asked, 1 marks, 2 marks, right? So remember how we are deriving the orders. No need to mug up. If you understand this picture, understand what I did, I'm sure you can actually do it all by yourself. Now, if I talk about the way in which the linked list will move, right? So if I talk about traversal, now be very, very careful when we talk about traversal. Now traversal means that I have a head pointer which is pointing here. Now if I say my current head pointer is equal to let's say head pointer wherever it is pointing, arrow next. That means that if you remember that the structure had a next pointer, right? So we had a next pointer here, right? So I'm trying to say that whatever is my head pointer pointing to, whatever that next pointer is, put it inside head. That means head now starts pointing here, isn't it? Because 3600 was inside this. So this link gets broken. So if you have to browse, you have to use this head arrow next or the node arrow next every time, like an iteration, right? I++. That is exactly what you do here. Temp arrow next. You will have to move the temp, temporary variable rather than head, because as you see here, head is actually changing its position, and you cannot change head from a linked list standpoint. It is the most important element in your dictionary when you talk about linked list. You cannot touch head. Please don't touch head for any kind of traversal operation. That's why what you typically will do is that you will take this head inside a temporary variable. So take a temporary variable, temporary pointer, and put it equal to head, right? So then what happens is now you have the capability to not touch this, and now you have the capability to say that okay, I have temp here and this temp is equal to head. That means temp is also pointing here, right? Whatever is the value of head, what was the value of head? 3600, because temp was pointing to the 3200. Temp was pointing here. 3200. Temp was pointing here. So temp, head was pointing here. So temp will also have 3200. Both of them will have 3200. Both of them are pointing to the same node. Now you are free to actually say temp is equal to temp arrow next. Temp equal to temp arrow next. Every time you are browsing till when? Till temp becomes equal to null. So unless temp becomes equal to null, so till the time temp is not equal to null, you keep on doing this. Right? And that way what will happen? Temp is sometime here. The next time it runs the loop, temp is temp arrow next. So temp becomes 3600. So temp starts pointing here. So this pointer goes away. This pointer goes away. And this becomes 3600. And then you say again temp arrow next. Then this pointer goes here. Right? So this is how it will move. So this reference will go away then. This particular reference will go away. Then again, if you say temp arrow next, then temp will move to 4400. So then temp will start pointing here. Then again you say temp arrow next. Now temp will go to where? The next is null. So temp will go to a something, you can imagine it is a entity which is beyond this boundary, or it is actually null. Right? So if it is null, then what did I say? Till temp not equal to null. So when it is null, it stops. So this is how the browsing will happen, traversing will happen, and that's exactly what is written here. Right? So starting from head, how will you browse is what is written here. The exact thing I have explained here. Now, if I move on, then just see the rest of the things when I talk about in terms of the operations. Let's say you are searching something. Then what will you do? This same operation, I will not repeat the operation for saving out on some time. The operation, now you understood that you need to actually do the traversal in the manner that I said. Take temp, copy it with head, and then start moving temp till it actually goes to null. Right? So that's what you are doing. Now search, what is search? Search is going to be that I'm searching for an element, right? So if I'm searching for, let's say 17, then what will I do? I'll take my temp, right? I will not repeat the process how temp is there, and exactly the same process. Temp will be head and so on and so forth. We move temp to temp next and so on and so forth. So first it will point here. Now we will check whether my searched value, whatever that search value is, let's say I'm searching for 17, right? Is this data 17? Is temp point, wherever temp is pointing to, is that temp data equal to the 17? Right? If the temp data is not equal to 17, then what we will do is we will say temp, please move here. If again I will check this with 17, if it is not, I will say move it here. Then I will get this data as 17. Then I will return what? I will return, let's say, a count. Here I had maintained a position. So I will say that my position as I move along, this is at position 1, this is at position 2, this is at position 3. So when I actually get my value, I will return this position. That means it is at the third value. So that is how it will happen. Update also on the same lines. If we will have to take temp, go to this particular value, update it to, let's say, 90. We will do it along the same lines. The same way we are doing search, we will do update also. So all these three operations are relying on the manner that we have taken temp. For our traversal, we go to our desired node and then we make the operations that we are supposed to do. Now if we are now creating a node, right? So then what we will do is, as I said, we will make sure that we create something called as new node. So we will create a pointer called as new node. This is a pointer, and this pointer will contain the address of this particular element. Let us say the address is this, and this is of node type, right? So this is the new node that we have created. So this will contain 1000. That is the address of the new node, and this new node contains a data value and whatever it is. So let us say the data that we are putting is 75. Now we wanted to insert it in the beginning. So head points to 3200. So now head should start pointing to 1000 because this is the first element. So if you see the value of head was also a pointer, right? So head was containing 3200. Now head will start containing what? Head will start containing 1000. So we will put head as 1000, right? So as soon as we do that, what happens is this particular link comes and joins here because this is my 1000, right? And then what we do is, so we will then move this new node. So my new node is right now pointing here, right? So my new node is perfectly fine. My new node pointer is pointing to the new node that we created at 1000, right? So 75 now needs to have my, what have I done? I have done that we will start from here, we will come here, this is my new node, perfectly fine. Then what? Then what? Isn't it missing? Then this should go here, right? So then what we will say is that this should be 3200. Right, so we will make this as 3200. Then what will happen? This link automatically will get created. This link will automatically get created. Now we have a situation where we can say that yes, we will start from head, because head is pointing to 1000. Right, so if head is pointing to 1000, we are supposed to go to 1000. So we are going to 1000. This is 1000, right? So we are going to 1000, and after 1000 we are saying that we will go to 3200. So we'll go here. How many pointers did you adjust? You adjusted 2 pointers, one pointer here, right, and the one pointer here. These are the 2 pointers you adjusted. Therefore, the number of pointer operations for insert at beginning is 2 pointers. If you do insert at end, you will also do same 2 pointer adjustment. Only thing is, the extra thing that you will have to do is make a loop to actually move to the end, because head was very easy. It was available to you. Wherever you wanted to insert, it was immediately available to order of 1, but we'll have to take an order of n to go to the end. So this is the thing that we will have to do first. How? We know now. You know the browsing algorithm, you know the traversal algorithm. I just told you, take temp and move like this. So now you have come here. So what do? You create a new node. You create a new node, and this is your pointer that is pointing here. So let us say this is 1000. So then what will you do? This at the end means this will update itself to 1000. Immediately what will happen? This link gets created. Right? So you are actually trying to do what? You are trying to do a new node at the end, which means the null entity now will start pointing to the last entity that you have created, the new last entity that you have created, which has 75, and put a null here. Right? So how many pointer operations did you do? Again, you did 2 pointer operations. Why? Because you have removed this particular, you have adjusted this null to this particular node, and you have also made yourself as null, which means that 2 pointers you have actually updated, which is what exactly this calls out, that the number of pointer adjustments you are making is exactly 2. So that's on this particular insert at end. Now if you see insert after, then insert after would mean, let me clear this off. Okay, so insert after would mean that, let us say I want to insert here. Then again I will create a new node here, and this will be my 75. This is created at 1000. My new node pointer is pointing to this particular node, which is fine. All I'm saying is that this node will now start pointing here. That means I'm removing this pointer. I'm removing this pointer which was pointing to 4000, and I'm making it equal to 1000. So now it starts pointing here. As soon as it starts pointing here, we get the traversal to from here to here to here. Then we have to move back here to complete the chain, right? So then what we'll have to do, we'll have to make this as 4000. Right? So when I make this as 4000, then this link automatically gets created. So what did we do? We have changed 2 pointers, right? One pointer we have changed here, one pointer we have changed here, right? So these 2 pointer changes would mean that we will do 2 pointer exchanges again, right? So that's how we will talk about. And all this code, when you see inside this code, they are doing the same thing that I am doing. First it is aligning the new node with the actual data. Then it is saying that new nodes next will be equal to temp next. Remember that we have actually moved forward using temp, right? So we had taken a temp and we moved forward. So temp is actually now, temp is actually right now pointing to the element after which we will have to put the data. So temp is right now pointing here, right? So after this element we will have to put the data. So if I have to put 4000 inside my new node, I will say that this 4000 is nothing but temp arrow next, right? Because temp is pointing here. The next, before we actually touch this, this is still 4000. So then temp arrow next is 4000, right? So then I can easily make this 4000 as temp arrow next. So what happens is this link gets created. Now once this link gets created, then we can say that temps next is equal to my new node. So temps next is equal to my new node. Then what will happen is this 4000 will be replaced. Temps next is 4000 will be replaced with this 1000. So this will replace with 1000. So these are the two things that is happening here. The rest of it is the browsing loop, which we have already talked about, right? So that's on the insertion. Deletion, exactly the same. I'll not spend much time on deletion, but we will need to just understand that when we are let's say I'm deleting here, there are 3 cases here. Let's talk about one of the cases. Rest of the cases exactly the same as insertion, right? Let me talk about deletion at the end. So what will you do? You will first need to reach the node which you want to delete. So you'll have to come here, right? So if you have to come here, actually speaking, you will have to stay here, not here. And that is why I took up this example, slightly different from the rest. So what am I saying? I'm saying that temp, I have taken you here, you are moving here, then you are moving here. Can you check at every point in time whether temp arrow next is equal to null? That means temp arrow next is this, that means this, that next is null. That means where am I? I am in the penultimate node, and you should stop at the penultimate node, that is the last but one node when you are deleting. And the reason for that is that because you will be deleting this last node, right? If you move temp here, I have stopped here. Suppose that I had moved my temp here accidentally, then I will never be able to come back here and make this. I will never be able to come back here and make this as null, because this is my last node now. After this is deleted, this will become my last node. So this has to be changed to null. But if I have moved already to the last node, which is of no significance to me, I will be deleting it, so I will free it, right? I will have to use the free syntax to free it. Then how will I come back and make this as null? So let me do one thing. Let me stay back at the penultimate node where I have to change this particular thing to null. So I will stay back at that node, and what I will do is I will say that, and how I reach to that penultimate node I have told you like this, right? Temp next, right? We will check that for null. That is sitting at one node. I will check one node ahead, right, for temp next to be null or not. So there, if I see null, that means the next node is null. That means I am the second last. I am the second last means I should be null. So I will change this to null. That is easy for me. I will change this to null, right? And then before doing that, what I will do is I will also free this particular node, right? So I will free the particular node before doing that. So I will say that free temp next. So free temp next is what I will say. So till the time temp next is not null, I will say that go and free the temp next, and depending on the way I am writing the loop, I will say free temp next, right? So free temp next means this will be freed, and then I will say that my temp next wherever I am is equal to null. So I did this with the first line, and then I will do this for the second line. This will become null. So then this element is off, this pointer is off, and hence we are all good, that we have achieved what we did. How many pointer operations did we do? Only one. That is, we changed this, right? So that is the only pointer operation we did. This is the pointer we have changed. So this pointer change is one pointer change. So mostly all delete operations are one pointer change. All insert operations are double pointer change. So now let's talk about a different concept, which is all of this using linked list, but how are we using it for, let's say, a stack, right? So if we are using this linked list for a purpose, then one of the purposes that we will need to use this linked list is for creation of a stack, right? So can we create a stack using a linked list? So let us see a node. Let us say that there is a node like this, which has value and which has the next. This is how, let's say, we can imagine a node, right? We can imagine a node the way we want. I'm putting the value at the bottom, the next pointer at the top. So or rather let me put it the way we normally read it. Let us make it simpler for you. So we have a value, we have the next pointer, which is let's say null. Now when I create one more node, so when I say push, right, what is going to happen is, if I assume this is a stack and this is my first element of the stack, then the second element will come here. What will the second element have? The value, and the next pointer of the second element will be pointing to this particular node, because then the second element will know that you have another element below you, right? So that is where you are creating a linkage between the topmost element and the next element. Similarly, if you do it one more time, then another node will be created, and you will have the value here for that node, and the next pointer here will be pointing to this node, right? So the more you do push, this is what exactly will happen. And each time what is happening is, there is a top, which is a pointer, which will keep on pointing here. So every time, so the first time you did it, top was pointing here. Then you created this node, then top started pointing here. Then you created this node, then top started pointing here. So you are moving top to the new node. The new node that you are creating, you are moving that top towards the new node, so that the top gets maintained always to point to the last node of this particular stack. And if you are actually wanting to do a pop, then what you need to do is, you will say that the top, you will actually do one thing, that this let me remove this, becomes clearer for you. Yeah, so let's say the top is pointing like this, and now you want to remove something. So if I want to remove from a stack, I can only remove from here, right? The last the first in last out concept. So if I remove this, then my top should now come down and point to here, right? So top would point to top becomes top arrow next, right? So top will be top arrow next. That is how it will point to the next node. So top was pointing here. What is top arrow next? This one. So if I say top equal to top arrow next, then this line gets created. Top equal to top arrow next, then this line gets created, and this line gets destroyed. And that is what you will do, and then you will free this particular node. So don't forget to free that particular node. And that is how the entire thing behaves when we are actually saying that linked list. How do we use linked list to help us create a stack? So this is how you do it. So we will keep on creating nodes, keep on making top point to the last node of the linked list, right? So if I see it in a flat manner, then this is what I will see, like this, and I will have a top pointer which points here. This is your stack using linked list, as simple as that. And this is your null. This is always pointing to null, because this is at the bottommost portion, right? There is no more linkages possible. So this is how you can visualize a linked list as a stack. Code is here. I've explained most of it. So go through it in case you are not aware of it. Let us talk about some concepts of linked list. If a new node is inserted at the front of a single linked list, so if I have a linked list like this, and I am inserting a new node at the front, so if I'm inserting the new node at the front like this, so my head was pointing here. Now I'm saying the head needs to point here. That is how my new node will be inserted. This is how my new node will be inserted, right? Then what will be the time complexity? I don't need to browse, I don't need to traverse, I don't need to do anything. I will just come here and say that I will do these two pointer adjustments, one pointer adjustment here and one pointer adjustment here. That's all I will do. So my order will be order of 1, right? Next is, suppose we add a node at the tail of a single linked list, but only if the head reference is given. What is the asymptotic cost? It is saying that I want to add it at the end, and I only know head. Then what will I do? If I have to add a node here, right? I can add a node here only if I know this node. That is the end node. So then I will have to traverse from head like this. How much order am I taking? Order of n. Right? So the answer is order of n. Removing the first node from a single linked list requires how much in the worst case? Again, if you are having a node set like this and you want to remove this, you already know that this points to head. So from head you can directly come here, right? And then you can say the next, whatever is the next is your new head. So you will say this is my new head. So this link gets broken, this link gets broken, right? So all you are doing is changing some pointers, right? And if that is the case, that is what you are doing, and you are not browsing, then of course your order is order of 1. So that's on the some of the concepts, and some of these tricky things come in short questions. It will be useful for you to probably practice whatever you saw and much more variations of that. So between array and linked list, I've already explained. We have a fixed size, we have dynamic size. We know that we can increase linked list. We have just seen I can insert, I can delete, but in array I cannot, right? I cannot insert in between. I cannot increase the size of the array. I can insert in between, but it's not going to increase the size of the array. And I will have to spend so much time in order to rationalize the array. So if I take an array like this and I want to insert in between, suppose I have these positions filled up and I want to insert here, then what do I need to do? I need to make these empty. I need to make these empty, right? So I will have to move this to the right. I will have to move this to the right. I will have to move this to the right. Then only this becomes empty. And then I will have to insert. So it's an order of n cost, right? As compared to order of 1 cost in terms of a linked list. So insertion and deletion is costly for an array. Flexibility, the growth part of it. The last thing is, what does null pointer indicate in a single linked list? It indicates the end of the list, right? A null pointer, whenever you encounter it, it will always indicate the end of the list. That is, there is no other elements in the list. Linked list is not suitable data structure for which of the four? Linked list is what? Linked list is a linear data structure, right? So we saw the linear data structure, non-linear data structure last class, yesterday. So linked list is a linear data structure. If it is that, then I can do all kinds of linear operations. But I cannot do divide and conquer operations. Binary search is a divide and conquer operation. I cannot divide using a linked list, right? So that's the problem that I cannot do. So this question and the next question, both of the questions will actually point towards any kind of logarithmic operations, which is binary, which is divide and conquer in nature, will be impossible to do with a linked list, right? You will have to rely on non-linear data structures for that. Right, so with linear data structures, you can only achieve so much. With a non-linear data structure like graph or tree, that is where you can actually do your divide and conquer operations. Right, so remember this point, that divide and conquer is only possible using non-linear data structures, not with linear data structures. That is the answer to these questions. Okay, write an algorithm to insert in the middle of a linked list. Okay, now middle means a bit different here. Middle means that we don't know what is the middle of a linked list. When I say middle of a linked list, let us take 5 nodes. Let us take 1 node, 2 node, 3 nodes, and then we will take 2 more nodes, and in these 5 nodes we will be using 2 pointers. First of all, let us understand the question. The question says, I want to insert an element in the middle of a linked list. Now, how do we identify the middle? First of all, if you know the number of nodes, then you can divide it by 2 to identify the middle, which is okay. Suppose you know the number of nodes. Suppose somehow you know this is 5. You have divided it by 2. Then you know 5 by 2 is what? Right, so you know 5 by 2 is what, and that 5 by 2 will be let's say 2.5, and you will probably be taking a ceiling or a floor to get to 2 or to get to 3. Either ways it is fine. Yesterday I have explained this. Now if you know that, then at least you will have to start from here and make these many number of iterations to actually reach there, right? So 2 means you'll have to go to the second node and make that many number of operations to actually go there. So net you are making an n by 2 operation. Net you are making an n by 2 operation even if you know the number of nodes, right, to actually reach there. Instead, you could actually do a logarithmic complexity to actually reach to the middle, and that is what we will try to achieve. N by 2 doesn't mean that it has become half, right? N by 2 still means order of n. Why? I will explain. N by 2 means order of n. Okay, let me put it up on the chat window. Why I am saying n by 2 time is actually equal to order of n. Can you explain? Can somebody tell me in one sentence why n by 2 is order of n? N by 2 operations is order of n. No one? Come on. We don't use integers in order. Tanmay, repeat the question. I am saying why n by 2 is treated as an order of n. Okay, I have to traverse the whole linked list to know one half of the position. Not really. It doesn't relate to linked list or anything. I am saying if any algorithm takes n by 2 operations, we still say that the order is n. Discard the numbers and put n as significant cause it grows linearly, because it's still half. None of you are coming to where I started or where I started from yesterday. The answer is very simple and it is very mathematical, right? The answer is that when can I say it is an order of n? Y equal to mx plus c. So when the graph is like this, then only I can say it is an order of n, right? Can I write n by 2 as y equal to mx plus c? I can write it, na? I can say y equal to half n plus 0. What is this half? This half is your m. What is this? This is your c. So then can you therefore conclude that this is a straight line? If it is a straight line, then this is an order of n. That is the reason. Does that make sense, guys? Right, so that is the reason what I am trying to say in terms of y equal to mx plus c. So that's the answer I was expecting, not qualitative answers, right? Be mathematical. So mathematically this n by 2 is nothing but n, because as I said, for large numbers it does not matter, and that's why we are getting order of n, y equal to mx plus c. Now coming back to where we were, right? So we said that if we have the entire list count, we can still take half of it and make n by 2 operations, which means that effectively we are doing an order of n to actually put the element inside this particular, identify the midpoint. So to identify the midpoint, we will take order of n in conventional algorithms. Instead, what we will do is we will say that we will take a slow pointer and a fast pointer. So we will take a slow pointer which is pointing to head and a fast pointer which is also pointing to head to start with. And then what we will do is we will say the slow pointer which is pointing to head, and let's mark these elements. This is 1, this is 2, this is 3, this is 4, and this is 5. So the slow pointer is now pointing to 1, the fast pointer is now pointing to 1. Right, so both the slow and the fast are pointing to 1. Now if both the slow and the fast are pointing to 1, can I say that slow, please go to slow arrow next? So I say that slow will move to slow arrow next. Every iteration, I will do iterations now. I'll say slow, move to slow arrow next. For the fast, I will say fast, move to fast arrow next arrow next. So I'll ask slow to go to the next node, and so slow will go to 2. Fast will go to 3. I will ask fast to go one skipped next node, which is 3. Then the next iteration, this will go to 3, this will go to 5. So where is my fast? My fast is right now here because it is at 5. Where is my slow? My slow is here. One more movement would make fast go out of bounds. So my loop will stop, will not make that movement. That is the time till which this particular code will actually execute. This particular code will execute till none of them become null. If any one of them becomes null due to a pointer movement, the code will come out. So in this situation where slow is pointing at 3, right, and fast is pointing at 5, the code will exit. Now when I have exited, the position of slow is my midpoint. The position of slow is my midpoint, isn't it? We have 3 here, which is my midpoint. So I got my midpoint by doing a logarithmic complexity. So I am dividing, right? I am multiplying by 2 and skipping or dividing by 2, whatever way you want to treat it. You are actually achieving a logarithmic complexity in order to find out what is your midpoint. After that, you will take order of 1 to actually do the insertion, right? So that is how we will attack this problem. Insertion, I'm not going, we have explained insertion. So for this particular problem, important for you to realize is the midpoint finding is through a logarithmic complexity where we take a slow pointer and a fast pointer, and we move the slow pointer once, fast pointer 2 times. We stop when any one of them becomes null, and at the time when we come out of the loop, my slow will be always pointing to the mid. We will insert the element there. Logarithmic complexity. So I hope that is clear as far as this is concerned. Okay, so I have a question which is saying that isn't it possible to count the number of traversals and divide the count by 2 to achieve the result? Then we can traverse to the middle pointer for insertion. Count the number of traversals and divide the count by 2. That means you have already made. How will you count the number of traversals? You are saying that I will count the number of traversals, which means you will traverse, which means you will say 1 traversal, 2 traversal, 3 traversal, 4 traversal, 5 traversal, and then divide. By this time you are doing this, you have already consumed order of n. So that's an inefficient algorithm, right? I hope Ghost Coder I could answer your question. Okay, so let's move on. How can a polynomial such as 6x cubed plus 4x square minus 2x plus 10 be represented by a linked list? So these are the applications that we are now talking about, right? So if we have to represent this, do you realize that you will have to store this element inside the data, the payload that I said, and this is also the payload. So if you store these two things as the payload, then you can achieve this particular term. This term can be therefore stored in memory. So if I say that I will have a struct, which is called as node, and here I will put int, let's say coefficient, and we will also put int power, and we will keep the next pointer here as a normal routine. So then this is what we call as the payload, right? We talked about it. So my payload to store one term of this polynomial is one node. Next node that we create will store this. So the first node that we will create will be let's say like this. So we will create 6 in the coefficient part, we will store 3 in the power part, and then we will have a line to actually signify the next pointer. Suppose this is at 1000 and the next payload is starting here, next node is starting here, and this node is at 2000, then we will keep 2000 here, and this will therefore point here. Here what we will store is minus 4x square. If you see here, what is not minus, sorry, plus 4x square. I could not see it, my bad. So this is 4 and 2. 4 is the coefficient, 2 is the power. and then we will also store the next node, and this will have, let's say, 3000 as the address, then 3000 will become this particular address, and here also we will store minus is there, right? Remember, this coefficient 2 comes with minus or plus, right? Because if the code is like this, the generic formula is ax square plus ax cube plus bx square plus cx plus d, right? So all the while we are saying plus, so if any of the pluses get changed, you will have to accommodate that into your coefficient. So you will have to store minus 2, and you will have to store 1 for that matter in this third term. And then the last term is like this, where definitely because it is last you will put null, and let's say it is at 4000, so we will put 4000 here, and this is pointing here, and what will come here, we will need to put 10. Where is this? 10 and 0, right? So this is how, why 0? Because this can be represented as 10x to the power 0, right? So that is why the power is 0 here. So 10, 1000, 2000, 3000, 4000. So that is where we will say that this will be possible in terms of executing the linked list in a manner where if we can tactfully take our node like this, then the payload can be accumulated to be represented with a linked list. So this is how we will represent this polynomial through a linked list. I hope we can I can make you understand this. Now, can we generate the polynomial from this head? Yes, of course we can generate. So what we will do is we'll come through this head. We will understand this is our coefficient, this is our power. We understand it is a function of x. So we will start writing our print statement. So we will say print whatever that node is, temp, arrow, let's say coefficient, raised to the power, then we will format this string, right? So we will say that this is the first part of this problem. So let us say that I'll just write one portion of the format, and you can understand that we will say a percent d, then we will say x, right? Percent dx, and then the rest of the stuff, right? The rest of whatever we wanted to put, and we will say here, because we can't do a superscript, we will therefore say here another percent d. So what we will put here on the right side as the substitutors are that first percent d is your temp arrow next. First percent d is your temp arrow coefficient. So first percent d is temp arrow coefficient, and the second substitution is your temp arrow power. So when this comes out, in your console, what will you see? You will see 6x raised to the power of percent d is coming from power, right? So 6x raised to the power of 3. So if you are looping from head and writing this print syntax inside the loop, don't you think you can actually reproduce 6x to the power 3? That means you have reproduced this particular term, and likewise you can do this print statement intelligently to reproduce all the terms, right? So then ultimately when the loop comes out, then you will see that you have actually produced 4x exponent 2 minus 2 exponent x exponent 1 plus 10 x exponent 0. This is what will come out of the loop, and this is exactly the polynomial that you started off with, right? So you reproduce the polynomial from this particular structure, hence your working was correct, right? So that's on the linked list style of addressing this. Another question on polynomials that typically come is addition of polynomials using whatever we are seeing on the screen. So if we have to add these two polynomials, then again the same funda we will take. We will say that there we will take a polynomial 1, which is our, instead of head, we will call the pointer as polynomial 1. So polynomial 1 will be for utilizing more of space. I am doing this now. 5, 4, 5 means it is the coefficient, 4 means it is the power, right? So I hope you can understand from the previous example only I am saying. So 5, 4, and it will then move to the next, which is 5, 3. Next it will move to 10 2. Next it will move to 8 1. Next it will move to 3 0. So that's there, and we will also have 3 3 as the next polynomial, which is our poly 2. So poly 2 will be pointing like this, and poly 1 is pointing like this, right? So that is my head of polynomial 1 and polynomial 2. So 3 3 will be going to 2 2, and this will be going to let's say 7 1, and this will be going to 8 0. So that is the polynomial that we will have. Now we have to imagine that we have an entity here, just to make sure that we have a parity in terms of the powers, right? It will be clearer as we go along. Let's say first what we will see is that if my polynomial 1's power is greater than polynomial 2's power, then what do you think the resultant polynomial should have in terms of the total value that we have to actually do? So if polynomial 1 power is greater than polynomial 2's power, then this is what is the case. This is exactly the case. Polynomial 1's power is greater than polynomial 2's power. At this particular node, right, 4 is greater than 0. Right? So if that is the case, then polynomial 1's power is greater than polynomial 2's power would mean that in fact what will happen is, this is an imaginary node, right? So what you will need to think about is 4 is greater than 3. So in that sense, if you take it as a real standpoint, real node, polynomial 2 is pointing here. So polynomial 2's power is 3. Polynomial 1's power is 4, right? So polynomial 1's power 4 is greater than polynomial 2's power, which is 3. So this is from a virtual standpoint if you want to imagine. This is from a realistic standpoint if you want to imagine. But the code will always take the real standpoint. So polynomial 1 power is greater than polynomial 2 power. Hence, I will say insert a fresh node. So what am I trying to do? I am trying to create a fresh polynomial, which is my result polynomial, let's say. And that result polynomial will have the addition result of these two polynomials. So what should it have? It should have 5 as the coefficient and 4 as the power for the first node, because that is what will be the output of the first node. First term, if these two terms are added, then 5 4 will be the output, na? So that is what I am trying to say. So we will insert what? We will insert polynomial 1 coefficient and polynomial 1 power. So all I need to say is, I'll need to call an insert function. We'll write that insert function, but that insert function does what? It takes polynomial 1's coefficient and polynomial 1's power, right? So that it knows that I will insert something. Okay, tell me the coefficient, tell me the power, I will insert that node. So it inserts this node. I gave it 5 and 4 because polynomial 1's coefficient is 5, polynomial 1's power is 4. Therefore, I gave it 5 and 4. It was happy. So it did that. Next, what I will say is, now you are done. So polynomial 1, please move on to polynomial 1 dot next. So now polynomial 1 moves here, right? But polynomial 2 is still pointing here. Now again this comparison will happen, right? So there could be a situation where we will also have the ulta. There could be a situation where these two polynomials were given to in an opposite sense. The second polynomial was first polynomial was second. Then you would have done the opposite thing, right? Exactly the opposite thing. I'll just write it from a sake of sanity here. If polynomial 1 dot power is less than polynomial 2 dot power, that means it is an ulta thing, and we will insert who is greater. Polynomial 2 is greater. So we will take polynomial 2. Polynomial 2's coefficient, and we will take polynomial 2's power. So this will not happen in this example, but I just gave it from the consistency because your code is always going to be generic code. Next, what will happen is we will come to a situation when both are equal, right? If both are equal, then by the way, after this we will also have to do the movement, right? So we will also have to do the movement of polynomial 2. So polynomial 2 arrow is basically polynomial 2 is equal to, sorry, this was equal to here, is polynomial 2 arrow next. Right, so that is the movement that we did in the last case. Now when polynomial 1 and polynomial 2 are equal, then what will happen? Then we will just need to insert the addition of polynomial 1 and polynomial 2. So we will say insert what? Insert polynomial 1 dot coefficient plus polynomial 2 dot coefficient. That is what we will say. So then what happens is 5 gets added to 3. Therefore, the node that we will get will be 8, right? Because we are saying addition here of both the coefficients. And what do we give as the power? Any one of them. We will give any one of them as the power. So we will give polynomial 1 arrow power and then close it off. So this actually says, okay, take polynomial 1's power, which is right now at 3. So this node gets created. And this is the way by which the resultant polynomial now goes into a loop, and the resultant polynomial gets calculated as 10 plus 7, which will be 17, and this will be 2. Then it will go to this side, and then we will have, sorry, not 10 plus 17, 10 plus 2 will be 12. So this will be 12 here. So we will have here 12 and 2, and then we will have 8, 15 and 1, and then at the end we will have 11 and 0. So that is how these 3 statements will actually create this resultant input, because you have this insert function which will help you to create that. That's exactly what I have written here in terms of the 3 cases, right? I hope this is something that you can correlate. If you come back and revisit this algo, I'm sure you can understand. I'll go to the chat window because I've not seen the chat window for quite a while. Let me see. It's still half n log n on decreasing constant factor. Okay. Isn't it possible to count the number of traversal? Okay, ghost coder, I answered. Sir, should I write code or algo in XM for these kind of operations if nothing mentioned? What is XM? PK34626. I didn't understand what is XM. Should I write code or algo in Acha, exam? Okay, sorry. I am not that young as you, so I don't know these chat lingos. Should I write code or algo in exam? See, first of all, this paper is about algorithm. So I keep telling that you should not be writing code, because this is algorithm. If they ask you to write code, there is nothing you can do about it. But I don't think that you should be pressurized to understand and learn code and write code as a part of this examination. As long as you can write proper algo, you should be good, unless they have not asked you explicitly. So anything that they have asked algo, whenever they say algo, pseudocode, write plain English. Yesterday I have told you how to write it, right? So write plain English. Okay, next you are saying that, sir, you were telling that divide and conquer operations are only possible using non-linear data structure, but we can use them in an array. Of course we can use them in an array. We can use means what? Are we really dividing that linear structure? Do you really think we are dividing that linear structure? Because what we did, if you remember the binary search algorithm, the binary sort algorithm, sort we have not done, the search algorithm, we took an array only. We took an array and we said that we will divide and conquer. But what we are saying here is that a linear list is not meant to be used as a divide and conquer mechanism. We are not saying that you cannot use. There is a difference between both. Try to understand, right? So it is not advantageous to use a non-linear data structure for divide and conquer. The reason is that in divide and conquer, you will have to move the indexes at random positions. If you understand 0, and then it will go, some index will go to the end, and that way you don't need a contiguous data structure for that. If you are taking one index here, one index there, you don't need a contiguous data structure. Unnecessarily you will be using a contiguous data structure, which is an array, to actually implement divide and conquer forcefully. And that is what I meant by saying that it is not done normally. So I hope PK34626 you can understand what I'm saying. Yes, these are the typical questions, Tanmay, you can expect. But then Ghost Coder has just responded by saying MAKAUT can give you the most unpredicted questions in any examination. How can we sort a linked list? We have not gone to sorting, Babu. Sorting is for tomorrow, right? So let's join tomorrow and understand that. Sir, where can we store the sign of every exponent in the exponent field for general polynomials? Yes, you can store the sign. You can take another field for that matter in the payload for the exponent also. Can you write algorithm? What algorithm I have to write, Aditya? I didn't understand. Be specific which algorithm. I'm more than happy to help you to write it. Any method to do bubble sort or any method to bubble sort a linked list. Again, bubble sort you can do, but bubble sort on a linked list will be done in the same manner as you do bubble sort for an array. There is nothing special that you will do for bubble sort on a linked list. You will go through one pass where you will check whether swaps are necessary. Then you will do the next pass if there was a swap. Then you will keep on doing passes till there is no swap. So you will have to, when I say passes, you will have to traverse from the head to the end, head to the end, head to the end. There is nothing much to debate about that because anyway array is also a linear structure and linked list is also a linear structure. So this will actually move on the way we just now said. It will move on. Polynomial 1 algo I have written, Aditya. So I don't know what else you are expecting. So the algo for the polynomial 1 is what I have written here. That these are the ifs I will write. If polynomial 1 arrow power is greater than polynomial 2 arrow power, then do this insert, do this polynomial 1 movement. Right? And if polynomial 1 dot power is less than, so I will say this is exactly what is written here. If, else, else. Right? So these three conditions is what exactly I have written here. And then this first part of it is the initialization that I did here. Take two polynomials, polynomial 1, polynomial 2, and then insert the coefficients into their node data structures. Right? So that is the first set of 3 steps. So I have already given this here. This is the first set of steps, and this step is the second set of steps. So it's already here, Aditya. I'm not sure if that helps. If you get time, please repeat the question I have asked you. Soham Gorai, have you filled the Google form? I told you to fill it up. Fill it up. We will discuss all the questions. Please fill it up. I want all the questions in one place first, Soham. I have already sent it to you. Please acknowledge that you will fill it up and make sure that this is available for us to consume tomorrow. I really want to address your doubts. I don't want this to be a monologue. I will give you whatever I think is important, but I don't know what is your gray area. Soham, you had a gray area. Please put it in that document that I have shared. Please check the chat window. I have given the Google form. Type it there. I will definitely address it tomorrow. Okay, chalo, let us move on to the okay, what we have. Okay, it's quiz time. Excellent. Chalo, quiz. I think today we will get delayed. A lot of things to do, and that's the reason we will get delayed today. Don't worry, if you get delayed, we have ample time tomorrow. I will try to see how quickly we can finish off the last module. But that's why am I being shown in dotted colors? My entire mouth, my entire body has become dotted. Okay, chalo, let it be like that. Now, what are we supposed to do? What did we complete? Linked list. Okay. So guys, give me a good performance. I hope this is helping you, and if it is helping you, let's see the results. Come on. Messi is in town. We should at least respect that. How many do we have? 27. Okay, I will start at 100. We have 122 of you, but I'll start at 100. Oh, it's already 100. I missed seeing that it is already 100. My bad. So let's start off. Chalo. All the best. Let's see. Good go. %. Okay, good. Vishal, Aditya, Priyanshu. Most of the names are common. Thank you. 76 is good for the first start. Order of n, don't get confused. Beginning, I don't have to make any traversals, right? So no need for any order of n. Move on. Next question. I'll end the quiz. 476. Very good. Good. Shayan has come up. Priyanshu, Vishal, good. But your results are good. Thank you. Let's keep up this momentum. 70 above is a good start. Shayan, Vishal, Dipayan, I'm seeing your name for the first time, probably. Good. But what happened? If delete by key, if previous is null, deleted node was, it's a linked list, right? If whatever is the previous node is null, then what does it mean? That you are trying to delete a node where nothing existed before it. So then why will you say it is the last node? It's obviously the first node. A first node has nothing before it, na? A last node has nothing after it. So that is the reason. So I thought you'd do a better job here. 38 of you mistook this as the last node, probably because you didn't have time to think about it, which is okay. Fastest finger first, I can understand. Let's move on. 94, 95, 96, 97. Okay, keep on typing. Very, very easy. Hundred and 6, 7, 8, 9. Okay, keep on typing. One correct. Good. Leaderboard is okay. 79%. Nice. It was an easy one, I know, but then at least you are attentive. That's also okay. So last question. Given you some hints also this time. Okay, leaderboard doesn't change. 54. I gave the hint also still. Why didn't you see that there was a word, there was a character R, there was a character V? You couldn't make the word traversal out of it. Come on. I thought I'll give you a hint and you'll get this correct. So inserting at end without a tail pointer. You don't have anything at the tail. Sometimes you have tail pointers, right? So, but you don't have a tail pointer. You only have a head pointer. If you have a head pointer, then all the way you'll have to go to the end, which means what? Traversal. Right? So that was the answer. Let's see the end assessment result. Ayush. Okay, good. Tanmoy, Priyanshu. Good. Okay, chalo. Let's move on. We have the next thing to cover. Class accuracy is 66%. Not that good. I would have expected. I think we dropped down on that 50% question. Right? Otherwise, this class accuracy would have been above 70. We started off well. Okay, so we will move on to the next part of this session, which is circular linked list. So let's talk about circular linked list now. I will need to switch. Where do I switch? In fact, we start off with double linked list. So anyway, we'll cover circular also. Don't worry about that. That comes next. So double linked list. We'll talk about the various things that we can do in double linked list, the same manner that we talked about in the linked list, right? So let us do that. So what is a double linked list? Only one change. Only one change. This is the only change that you are doing in the double linked list, which is you are giving the opportunity for one node to know its previous node. That's the only change. Just like this node knows the next node through this pointer, so this node will also know the previous node through this pointer. So you need one more pointer, which is the previous pointer. So this is the additional thing that you need. No other difference, right? And then all the operations will be typically similar. Let us see all the operations, right? So then what are we getting? First operation is traversal. In the traversal operation, now I can go from the head end or from end to head also. So typically if I have a tail pointer getting maintained just like a head pointer, then I can use this tail pointer and I can use this particular pointer to go to this node, then this particular pointer to go to this node, and then reach null. So I can do a tail to head kind of a traversal using this tail pointer, or I can do the normal head to end traversal using the head pointer. I have both the ways that I can go, but in both the ways I will have to go like this, or like this. That means I am consuming an order of n, right? From an insertion span standpoint, nothing changes. If you insert at the beginning like this, then you are actually inserting it with the cost of just changing the pointers. So all you need to do is your head will now start pointing here, and this will start pointing here, and this pointer will go away. So this is order of 1. If you do it at the end, you have to reach the end to do it. Changing pointers is order of 1, but to reach the end, you will have to actually consume the relevant amount of time with which you will traverse the particular list. But then I just now said we have tail, right? So if we have tail, then do we really bother about this traversal? Should we take head and go all the way to insert at the end? The end is followed by tail, right? So the end already is here. Can I not use just the tail directly? Yes, I can. If there is a tail pointer approach, then it will be order of 1. If there is no tail pointer, then it will be order of n. So then I will have to definitely use this to go there. But if there is a tail pointer, I can directly create a node here and make my tail pointer point there instead of here. Same way that we are doing with head pointer. So that is how you will have to write if it talks about insertion. Remember, for all linked lists, there is a concept of a tail pointer. Sometimes it is allowed, sometimes it is not, depending on what the question says. If the question doesn't say anything, you are free to introduce the tail pointer and say that if we use the tail pointer, this is how it will be. If we don't use the tail pointer, this is how it will be, right? You are free to use that. So remember this gives the examiner a better insight that you know a breadth of the knowledge that has been asked. A lot of students will be actually doing just the head pointer concept. But if you know that you can also use a tail pointer and introduce it, unless they say don't do that, introduce it, that's brownie points for you. So remember that concept. So that's insertion. Next comes deletion. I will not go to that. Same thing. It is an order of 1 at the beginning, at the end. Again, depending on whether you are using the tail pointer, it will be order of 1. Not using the tail pointer, it will be order of n. And if you are actually deleting this record, then this record might be the last record, which is insert and deletion at a particular key or at a particular position. So that is what you are, if you do that, then this also will be an order of n. Because this could be the last element or this could be the first element. Even if you take the tail pointer and do that deletion, the tail pointer could be deleting the first element. Then also you will do a order of n traversal, or the head pointer might be deleted. Through the head pointer you are doing the deletion, then through the head pointer it could be the last element, then also it will be order of n. Searching will be order of n either ways, from head to wherever you want to go or from tail to wherever you want to go. It will be order of n. Updating will be again order of n. So most of it is similar to the single linked list, with the only difference is that if you use the tail pointer now, the tail pointer gives you the benefit to come back because of the previous pointer. Now, if you see the double linked list operations, right, the traversal, the search, the update, nothing changes, right? There is no change from what we did in the last examples of linked list, right? So on a single linked list, the way we did traversal, we had taken temp here, right, and we had said that temp is equal to my head, And with that, we started saying that, okay, temp point here, then temp please go here, then temp please go here. That is what we said till it reached null. So that is what we are doing here. This is what we are doing, exactly the same thing that we talked about in linked list. Single linked list is what we are doing in the double linked list. So these three operations do not change for a double linked list. So that gives us some time to get into the other operations of a double linked list. Now the other operations of a double linked list, insert at beginning, the only difference is the previous adjustment. So insert at beginning means what? Insert at beginning means that I am inserting a record like this at the beginning, which means that there are two things that will happen. One is that this becomes the first node. So if this becomes the first node, then let us say this is the value of x. This is my previous and this is my next. Now because it is the first node, the previous should point to null, right? The previous should point to null because it's the first node. And because this is no more the first node, this pointer will go away and this pointer should now come here, right? So I should be pointing from here to here. That means this is my first node, this is my second node. And because now I have this node created completely, this head cannot point here. So this head has to start pointing here. So the head will point to this new node. The new node will point to previous as null. The new nodes next will point to the previous value of head, which was the earlier first node. That is exactly what we are doing here. We are only making the previous adjustments. These are the two lines that is additional from your linked list question. So new node dot previous is equal to null. This is the null pointer adjustment. This is the previous adjustment that I was talking about. New node dot previous. This previous didn't exist in single linked list. Now it exists. So you have to make some adjustments. What is the adjustment? Make it null because first node. And the head previous is equal to new node because head is pointing here. So its previous was null. Now it should point here, right? So head previous, actually the arrow from previous would be like this. This is the arrow. Head previous will be coming towards this, pointing here, and here this should point towards this. So we are talking two pointers here, previous pointer here and the next pointer here. So the next pointer here will point to this node and the previous pointer will point to this node, because we have now two ways, right? So both the pointers will need to be adjusted here. So that's on the algorithm for insert at beginning. Insert at end, similarly you will only need to adjust the previous nodes only. So the previous adjustments at the end is the only thing that you will have to do as compared to what you did in the linked list way of doing things. So if I take remove this, and if I take the end, if I take the end that I'm adjusting a node here, and this is my previous, this is my next, right? Then what am I doing? I'm going to say that this particular pointer will now start pointing here, right? Because this is now the last node, and this pointer becomes null. And this particular pointer, this is the previous pointer, this is exactly what is new. This will point here. So that is the only thing that you will do, right? So these are the two pointer adjustments that we will have to do here, right? So that's something that you need to remember, that you just take a node, you just put that adjustments here. You understand that, okay, this next will no more point to null because it is no more the last node. So it should point to the next element. Yes, okay, good. The next element is pointing to null as the last node. Okay, good. But the next element also has a previous. So the previous has to point to the earlier, wherever the tail was earlier pointing. Right, so that is how you will do. And the tail will have to now shift and point here. Right, so that is if you have a tail. If you don't have a tail, don't work on it. Right, so that's something that exactly is written in these two lines. Rest of the code is exactly the same as your linked list code. Now coming to your double linked list in terms of insert after and the delete beginning. Insert after is again simple. You make it here, and if you do that, again you will have to adjust the previous pointers only, nothing else. The rest of the code is going to remain the same. You will traverse first, you will traverse first and come to the position where you want to insert and hold on there. So your temp will be holding on here. So temp is actually pointing here, and now you have created this node. So in this node you are actually using your previous and next, and you have, let's say this is the value. So you will have to break these two pointers, right? You'll have to break these two pointers. So the forward pointer, that is the next pointer, will start pointing here. The reverse pointer, which is from the previous, will start pointing here, and this particular next pointer will now start pointing to the next node, and this particular previous pointer will now start pointing to the previous node. So that is how you will adjust. So these are 4 pointer adjustments, right? Please remember this word 4. So anything that you are doing in between makes you adjust 4 pointers, because there are actually 4 pointers. Whenever you are putting something in between, right? If I put something in between, then there is 4 pointers that needs to be adjusted. This particular pointer will need to be adjusted. This particular pointer needs to be adjusted. This pointer and this pointer, right? Because you are inserting something in between, these 4 pointers will come into play, definitely, right? So please remember this. In between you are adjusting 4 pointers. Delete at beginning, nothing changes. Similar to that, all you need to remember is, if you are deleting at the beginning, if this node goes off, then what happens? The previous record pointer is now orphan. It is pointing to something which is non-existent, right? So the previous record should be changed so that it becomes null. So this particular record now has become the first record, because this is deleted. So then this should be pointing to null instead of pointing to here. That is the only change that you have to do. The rest of the changes you are anyway doing in the linked list style of doing things. Head will be moving there and so on and so forth. You will be freeing that node and so on and so forth. We have discussed that also. So that's on the on that part. Delete at the end, delete at the key. Again, I will not go much into depth of that. Let us see delete by key. Delete by key, I have just now explained. Insert by key. Let us take this, right? Delete by key. So delete by key, if I take that, because I think yes, I think delete end is what we discussed in the linked list. So this we have discussed in the linked list style, in the single linked list. So let us discuss another different algorithm, which is delete by key. So this will probably take 90% of what we needed to do in the linked list way of doing things, single linked list, along with 10% more of how we change that to make it compatible with double linked list. So that will serve both the purpose. So if we actually say that we will delete here this particular record, then we will need to stop our pointer here, right? Stop our traversal here. You remember we started off with temp and we said temp you are head, and then you move temp, please move to temp arrow next. This is what we said we will do. We will use this as our traversal routine, right? So we will do this till we reach null, till temp reaches null. I am saying don't take this till temp reaches null, because you are supposed to delete by key. By key means you are supposed to search for A and then exit. So if you get if you do temp arrow next, temp arrow next, temp arrow next, and suddenly get A, then exit. So suppose I will exit here, right? If I exit here, then what it means is that I have actually taken a scenario where my entry here is supposed to be deleted, and I have reached that node that I have found that needs to be deleted. So my temp is right now pointing here, right? So I am saying that if you see here, temp is not equal to null and temp arrow data not equal to key. I am going on doing temp arrow next, temp arrow next, temp arrow next, right? So till the time I find the data, and till the time temp is not null, go on doing temp arrow next, right? So if I do that, then I will actually reach a situation where at some point I will come out here. Suppose there are more nodes here, right? Then, and we started off from here, then I will reach here at some point and I will stop there. When I have come out, then whatever I have as my previous record, So if I draw this a bit better, because this was only 3 items, it is difficult to explain with 3 items. Let me draw with more items. So I will say that this is my first node, this is my second node, this is my third node, and this is my fourth node. In fact, let me take 5 nodes. Now I want to delete this, because we are saying delete by key. Suppose this is my key element, right? And I want to delete it. Then don't forget we are talking about double linked list. So we have to give both side arrows. So if we give both side arrows now, this is how it will look like. Okay, now if I have to delete this, then I need to just make 4 pointer adjustments again. So this particular arrow will now go here. This particular arrow will now go here, which means these two will now be solid lines, right? So this is the only adjustment that we will have to make. So my next pointer of this should go to temp arrow next. My next pointer of that should go to temp arrow next, and my previous pointer of temp arrow next should go to, see, temp arrow next previous pointer. This is what I wrote here. Temp arrow next previous pointer will go to temp arrow prev. So temp is here. See, temp is pointing here, right? So temp arrow next is pointing where? Here. That previous is here. So temp arrow next dot previous will go where? Will go here, na? This is the line it should go. So it should go to temp prev. This is the prev, right? This is the prev, it was already pointing. This is the prev. So I will say this line should utilize this address, whatever is stored here, to actually go there. So this is what will happen when I say, so this is the prev pointer that is already existing. I will just take this prev and say that I want to use this prev's address. That means this will automatically start pointing here, right? So that's what I have done here. Temp next prev equal to temp prev, and that takes care of this adjustment, right? And then if I say temp prev next, what will happen? Temp prev next. That means I am here, temp. Prev is here. Prev is pointing here. Prev is pointing here. Temp prev next is this. So I'm making adjustment to this pointer. So temp prev next, I'm adjusting so that it moves here, right? So that is what I'm doing here, temp next. So this was temp next. So I'm saying temp, your prev is here. That prev will take me here. So that prev's next, I will adjust that pointer so that it starts pointing here. How? Utilizing the temp next. So temp next pointer was already pointing there. So I will utilize that and move there. So that is how I will do this. So these are the 2 lines that is extra as compared to deleting from a single linked list at any point or at any key or after any key. So that's on the double linked list operations. Now, who will answer this question? Let's use the chat window for this. Inserting a node after a given node in a double linked list requires how many pointer exchanges? Use the chat window, guys. Okay, everybody is answering correctly. Yes, it is 4 pointer exchanges. I am inserting at after a given node. So if this is the double linked list style of doing things, then I am taking one node here and I'm taking this pointer and moving it here. That is the first pointer adjustment. The second pointer adjustment is I am removing this and making sure this points here. Then I am removing this and making sure this points, not that, sorry. I am removing so then I am making sure that I am utilizing this pointer to go there, and this particular pointer, which is I don't know whether I said the previous thing wrong. Let me redo and restate whatever I'm saying. Somehow I feel I said it wrong. In case you got it wrong, I don't want you to get it wrong. If it all has happened, my bad, sorry for that. So let me bring it back to where it was. So first things first, when I'm inserting, then this particular node, no more points here, so this will have to go away, and therefore this will start pointing here. That is the first thing. Second, this node cannot point to this previous node because now this has become the previous node, so this pointer will go away and we will start pointing here. So those are the two things definitely we'll have to adjust. Next, what we'll have to do is this previous node for this particular node will need to point to the previous node that is there, and the next node for this will have to point to the next node for that. So these are the adjustments, the 4 adjustments that we had to do. So that's on this. Question on double linked list comes just like this. Consider 3 cases: first node, last node, any intermediate node, right? Some of you would have got this in your CA exams. I know about that. So it's very important for you to understand the deletion and insertion, at least these 2 operations from these 3 use cases, right? Beginning, end, in between, right? So that please, if you have to do something on double linked list, do this question. Deletion and insertion, how does it implement, or how do you implement that as an algorithm? So that's on double linked list. So let us have one more quiz now. Let me see the chat window. Chat window, nothing much. There are 3 pointer operations for insertion at beginning. Farhan, why 3 pointer operations? Okay, let us see why 3 pointer operations. Farhan is saying there are 3 pointer operations for insertion at beginning. So we are talking double linked list is what I will assume, Farhan. So we have let's say these 2 nodes, and this actually points to null, and this is my head which is pointing here, and this is pointing to null. So if this is the case and I want to insert at the beginning, then I will insert my node here, and my insertion node should have 1 pointer adjustment which will be towards null. This pointer will now come here, that is 2, and so the previous pointer has gone. The next pointer will be pointing here, 3, and I will also have to move my head pointer here. So it will always be 4, Farhan. It will not be 3. The head also has to move, right? So I thought you missed the head probably. Does that answer your question, Farhan? Okay, now let's move on to our quiz. Let's see if you get a better result from a double linked list standpoint. Okay, get ready. We'll start. Go ahead, start. Okay, I didn't share my screen. Sorry. I was thinking what's happening. Why are people not joining? Doing it, guys. 1 minute. I had opened it, but I didn't share my screen. Now, go ahead. We'll start at 105. Five more. Okay, so let's start. $76. Good. Asifu, Rangad, Rungshit. Good. 76 means the rest I will not be worried. Let's move on. Shayon, Dipendu, Ashmita. Okay, what happened? 56. Okay, new node is the correct answer. Head previous becomes new node. We are talking about what? We are talking about a double linked list. You have to remember that. So you are inserting something in the beginning, and head is not null. That means it's not an empty list. That means the conventional things we have been discussing, right? So the head previous has to become the new node. Right, so because so that head now starts whatever that second element now has become, right? That second element is the first element is no more the first element, it has become the second element. So the second element was pointing towards head. So that second element's previous now should point towards the new node that you have created, no? Because you have inserted that. So the previous has to be changed. So that is the answer to that. So I don't think you had the time to understand the question because of this fastest finger issue. Otherwise, this result would have been better. Think about it unanswered. Good. I think some more time. Abhishek. Okay, good. Ritam. Good. I see 2 new names. Excellent. So it will be null. So you have deleted the last node. Last node was actually temp. So its previous was the previous to that node. That previous next will be now null. because that becomes the new last node. So temp, previous, next will be null because temp no more exists. That is the answer. All of you should get this correct. It's the same answer that you gave on the chat window. Come on, 59. This is the same answer you guys gave on the chat window. What happened? Why 2? You are inserting after a node, that means in between. In between is always 4 because you have to adjust those 4 pointers. You have previous from the main node that you are inserting. You have next from the main node. And you have next from the previous node and previous from the last node. These are the 4 pointers you'll have to adjust. So I don't know why 33 of you answered 2. The rest 6 and 2 I can understand typo or something else. But 33 of you, please get the facts checked. I'm getting worried. Arjun Sagar Gupta, good. Aditya Pal, these two names are new. But guys, help me understand. How is 135 students in this quiz, whereas 109 people are in the stream? That means people are not joining the stream and directly joining the quiz. Strange. Okay, so be it. That's how you want it. Yeah, the answer was tail, but I thought most of you would get it. Null, tail, null, next, tail, last. So many. Double linked list traversal can be done from head to end or from the end to the head. Now end has 2-3 words. We had 4 blank spaces. So be intelligent, na guys. 50% of you have not applied your brains. Head to end or tail to head. Let's see. Tanmay, Shurojit, Ayush, Sengupta. Okay, good. We see new leaderboards. Good. Okay, so congratulations, guys. Let's see how your day would be. Let's see if you maintain the leaderboard position. Others, you know, this is a very volatile leaderboard, so you have ample chances to catch up. Don't worry. Let's start off with circular linked list. We are at 11. We will take a 15 minutes break after the circular linked list and before we start trees. So that will finish off with the linked list. So that's something that we will do. I will remove this so that you start seeing the other screen. Circular linked list is pretty basic to understand. Only critical thing of circular linked list, think about a linked list first. What is a linked list? Just think about that picture. Now in that picture, imagine that you don't have a head. You don't have a head. Instead, they are giving you this, that at the end, whatever is the end will come back and hit you here. Right? So from the end, you will come back to the head portion. So if that is the case, then we will only have something which we will call as last. And this is what you see here. It is the same linked list, single linked list that you know, same structure. Only thing is, instead of head, we are calling this as last. You can also keep head, doesn't matter. But then you will lose certain things. I'll explain what you will lose. So, as I said, we will keep last. We will not keep this head. I have kept this head here to make you understand that what you will lose when you actually adopt to this kind of a problem. So if you keep head here and you want to reach the last node, right? So if you want to reach the last node, what will be the order? You will have to take this head and then go like this, reach the last node. So the order, if you keep the head and go via the head, is order of n. Now imagine you have, instead of the head, you have a tail here. Right? So if you have a tail here, then you are already at the last node. So it will be an order of 1. Very nice. Now you will say, how will I go to the first node? You have taken me to the back. Now you are saying it is order of 1. Now if I have to go to the first node, then it will be order of n again. I will say no. Why? Because the tail next is pointing where? To your head, original head, isn't it? So tail next is pointing here, which is what? Your original head, right? So you get both the benefits. You get to go to the last node directly, and you also get to keep your first node. I hope you understand. This is the only thing about circular linked list that you need to understand. The rest will fall in place. Right? So this is the only thing, and this is a very important interview question also. I typically ask this question also. That what is the one beautiful thing about circular linked list that you need to actually talk to me about? How does it help? It helps like this. See, just by changing the pointer back, you could directly go to the tail, and from the tail again you could come back to the head directly. Order of 1. There is no order of n concept anymore. Right? For a traversal perspective, there is no order of n concept anymore. So when I say traversal perspective, of course it depends on where you want to end, but then going to the tail will not mean that you have to take order of 1, or going from the tail to the head doesn't mean that you have to take order of 1. That means if you have to visit every node, then order of n is okay. But if you have to go directly to the tail or directly to the head, then it is order of 1. Right? So that is what I am trying to tell you. So that's what this says, that if you have to traverse every node, there is nothing doing. You will have to take through all the n's. Right? So order of n. And similarly, insertion of new node before the current head will be an order of 1. Right? So before the current head, the head is here. So if you want to insert a node here, then all you need to do is temp next is here already. Your last next is here. So last next will start pointing here. This will be broken. So the last next will go from here to this new node, and this new node will start pointing here. That's all. 2 pointer adjustments you'll need to make. And what did you do? Did you do any loops? No. That's why it is order of 1. If you are doing an insertion at the end, then you use the tail pointer. You have a tail pointer. It will be an order of 1. insertion at the end, order of 1, because you know the tail. You don't need to traverse there. You don't need to go from here to here to here to here. You can directly use tail. You are already here. Now start the insertion process. Right? So without the tail pointer, you will have order of 1. And if you don't use tail like this, that is the last pointer like this, then of course it will be order of n. But typically for a circular linked list, nobody is crazy enough not to use the tail pointer or the last pointer. Now deletion, same thing. Deletion from the beginning. If you have the tail pointer or the normal pointers, you will take an order of 1. That is the last pointer. From the end also will be order of 1, and from at any point, any position internally, that will take order of n, because you'll have to reach that node from whichever direction you start, from the tail order or from this side head order also, wherever you start. Searching again will be the same as deleting, because you'll have to search for that element. You'll have to go through painfully all the elements, right? So that will be still order of n. Updating will also be an order of n. So that is on your circular linked list. Define circular linked list and double linked list. Circular linked list, you just need to talk about the extra thing that I just talked about, that the last node points to the first node, forming a circle, right? So that's why it is called a circular linked list. So this is the last node points to the circle, and in the double linked list, the last node points to null. Now, there is nothing called as a circle there. There the number of pointers maintained is 1, but here in double linked list it will be 2. Traversal is circular. Traversal is in both the directions. So here we can go like this and this, but here in circular linked list you understood that we can go like this, right? So this is the traversal part of it. Memory, here we will take less because we are using less number of pointers. Here we will use more pointers, and hence the memory will be more. So that is how you will probably, if this question comes on circular and double, it has come many a times, it has come. Even short notes come on circular and double. Be careful. Just write the meaty points, the important points. These are the important points, right? How do you store the first node? Or sorry, how do you store the last node? How many pointers per node? How is the traversal? How is the impact on memory? What advantages do you get? Those are the things that you should think directly and start answering the question. What type of linked list contains a pointer to the next as well as to the previous? Double linked list. That is what it contains. What advantages, disadvantages use circular linked list? So let's see this. This is important. Now circular linked list, we know the advantage. I'll not go to the advantage. The disadvantage is that you could be directly going like this, and this can go on infinitely because you don't know where to end. There is no null pointer, so you don't know where to end. So that could be an infinite loop risk unless you know where, in a business logic perspective, how to stop. Now, because you don't know where is the start, where is the end, debugging a circular linked list will be very difficult. So if there is a problem, you will keep on wondering how this node came here, because you don't know that if you are going around in circles, you don't know where is the start, where is the end. Then how will you trace the elements, that this was the first element, this was the second element, this was the third element? So there is no concept of 1, 2, 3, 4 there. Everything is in a circle. Everything has the same priority. Insertion and deletion operations are more complex. Of course, it is more complex because we'll have to take care of adjusting the previous, adjusting the next, and all of that, right? So because not the previous, when I said previous, I meant the previous nodes next, right? So we will have to adjust the previous nodes next when we insert in between. We will have to adjust the current nodes next to the next element that is in line in the circular linked list. In order to do that, we might see that we are already at the end. So this we are already inserting here. Then at the end, this insertion will actually take me to the head. So I have to adjust this pointer very carefully as compared to if insertion happens here. So if insertion happens at the end or insertion happens at the beginning, the adjustments are much more tedious in a circular linked list. And of course, as I said, insertions are the complexity of having a logical overhead is much higher as compared to a linear linked list. Logical overhead means that the understandability of what to do in terms of logic or logic awareness of how you are actually going to see the code and understand what it is trying to do is much higher in a circular linked list as compared to the linear linked list. So advantage is okay. You can write advantages of circular linked list. I told you the advantage, right? Head you can get directly, tail you can get directly, you can move around freely. All those are advantages. But how to probably discover the disadvantages. That's why I discussed the disadvantages with you. Please remember at least a couple of points on disadvantages before you go for the exams. So that's on circular linked list. Let us do a quiz on circular now, and then we will break. Let me see the chat window. What's happening? I have to rename to get to the leaderboard. For inserting node at the end, double linked list text 3 pointer exchanges. Okay, so who will answer this now? Ketchup Knight has a question. No, sorry, PK34626. For inserting a node at the end of a double linked list. Inserting a node at the end of a double linked list. So he's saying that I want to insert a node at the end of a double linked list. So this is my double linked list, right? And I want to insert this node. How many pointer exchanges will happen? Let's see the chat window. Islamic Talks has already given 2 pointers. All of you, tell me what. Now this was pointing to null because it was the end. Any answers coming up? 3, 2, 3, 3, 3, 2, 3. 3, 2. Okay, so people are mixed with 3 and 2. That means definitely in exams some of you will get this wrong. We are talking double linked list here. We are not talking circular linked list. The question was from double linked list. Right? So in double linked list, if we have to insert this node at the end, then of course this pointer has to be changed to point here. That is 1. This pointer has to be changed to point here because its previous is this, and this pointer has to point to null. So that is 3 pointer exchanges. When you are writing a null pointer assignment as a number, when you are counting that inside a number, be very, very explicit. Lot of universities do not accept a null pointer exchange as a valid pointer exchange. I mean, this was the new node that you are inserting, so it will obviously have null. So what is the big deal? That is what they will say, right? So, but I would prefer you answer it as null, but be very explicit why you are counting this as 3. Because while lot of universities don't, lot of universities do. And my take on it is that if this was in between, then you would have done something else with this null pointer. You would have adjusted this somewhere else. If it was in before, then what about the previous pointer? If you were talking about, let's say, the double linked list, then this previous pointer would be again null. Will you count this or will you not count this? So you have to think about that when you actually write the answer, right? My take on it is, if there is an adjustment that you are making, don't assume that because you created a fresh node, it is already null, so no adjustment is being made. Don't assume that. Creation of a new node does not give you the right to assume that it is null, hence I will not adjust it, right? So don't assume that, because logically it has to point to null. So that is a logical addition that you have to do, and hence that's why I said 50% of people say that it is supposed to be there, and 50, and that's how the chat window is also divided, if you see. So 3 and 2, none of them is wrong. You can explicitly say that the other way around also. You can say that null pointer adjustment I have not considered. I will tell that answer is 2, and null pointer adjustment I have not considered because the default value is null. I'm not saying that is wrong, but all I'm trying to say is, when I think logically, I will have to think this box. In this box, how many pointers am I supposed to adjust, is what they are saying, right? In this box, I'm supposed to adjust the last pointer also. The last pointer has to be pointing to null. Why will I worry about what it has? By default, it may have something, but I have to adjust it to null. And that's why I will consider that in my dictionary of writing, and I will mention that. Because it is an ambiguous thing, I'll mention that. So you also mention that, please. Whenever you are doing it, either count it or don't count it, but mention that you have counted it or you have not counted it. I hope I am making myself clear. Yes, so it will not be, Ayush, you are right. If it's already null, it will not be counted as an operation, because null to null is not, in normal compilers it will not. Old compilers anyway doesn't have optimization. It would have anyway done the CPU scheduling and done a null to null assignment also. So as I said, right, there is no right or wrong answer to this. You are supposed to make it null. You created a node. Did you get null by default? No. The node creation algorithm gave you null. So there is an adjustment there. So a junk value was converted to null by an adjustment. And you utilize that saying that it is the last. Hence it is null. I will take this null. But then you are not counting the fact that you had actually in reality you had a blank structure where something was null, junk, which got converted to null. So there are ways to debate about it, Ayush. I am saying that be safe. Either say it is there or don't say it is there. Mention that, count it accordingly. That's all I am saying. Okay. Partho has an interesting opinion with tail pointer 4. Yes, good. I like how you are thinking, Partho. If you have a tail pointer here, the tail pointer was pointing here. So the tail pointer will now start pointing here. That is exactly, Partho, how you will score brownie points. Nobody talked about tail pointer. I also didn't talk about the tail pointer. But we mentioned earlier in this call, right, that if you are actually doing something which is not asked for, but it is the right thing, do the right thing. You will score brownie points, I'm telling you. So good. Okay, let's move on. Quiz time. Chalo. And then break time. Quiz time. Where is the quiz? Here. Okay. Now this side. We do circular and then we start with trees. Chalo. How many are here? 113. We will start at 105. It's already 105. So let me wait. If you join from mobile, why would YouTube not show it? I'm confused. I see 109 here, 111, 112. By the time I start chat, it will be 130. Still don't understand. Okay, chalo. $76. Good. Meghna, Disha. Meghna, I'm seeing you for the first time. Probably Disha, I've seen you. Rungshit, I've seen you. So good. I will move on, nothing much to do here. Shayon, Rungshit, Arindam. Let's see. Okay. I expected this. 47. Strange results. 48 and 60. Now, which one is correct? How will you understand? Finding the last node. Yes. So finding the last node, 48 of you have answered. Now guys, if you don't have a pointer, see, as I said in the beginning, that we have removed the head, we have maintained only last or a tail, whatever we want to call it. We have removed the head. Now they are saying remove the tail. Then where is your pointer? So you will have to find the last node first. From the last node only you can come to the first node because it is looped. So some of 50 of you have assumed that you have the head. That is no traversal because you already know the head. But we had said we had removed the head. There is no head concept in a circular linked list. Please get that straight. There is no head. That is why you have a tail, and the tail is also removed. Now find out how you can from a perspective of who is the last, because the last can only give you the clue to who is the first, because the last is attached to the first. Once you get the first, then you do whatever you want from a deletion perspective or insertion perspective. So please understand that you cannot just assume that head is there and therefore there will be no traversal. Your point is, get me the last node, I will find out. Now how I'll go do that, don't ask that question here. That has several ways to do it. So that's the answer to this. Let's move on. Anish, what is happening? You are attentive. Where it is mentioned circular linked list. (69), which is still okay. This is okay. 22 of you still think order of n. Insertion at the end with the tail pointer. You have the tail pointer. Why are you worried about order of n? And Anish, I don't know whether you are attentive here or it's a typo or you mistook this. What is this quiz about? Can anybody write what this quiz is about? What topic this quiz is about? It's about circular linked list. Then why are you asking this question where it is mentioned circular linked list? Right? So I'm surprised that you are not understanding what this quiz is about. This quiz is about circular linked list. Right? So each of the questions will have to be interpreted with that knowledge, circular linked list. Nothing else, unless otherwise it is mentioned as something else. See, here also it is not mentioned, insertion at the end with a tail pointer. Now you will ask me, is it a circular linked list? Right? It's about this topic, right? So let's be attentive on that. Let's move on. most of you should get this correct. Good, 81%. I thought so. Okay, good. We will move on. Okay, leaderboard doesn't change much, 67, that is good. At least you utilized that hint probably. So the answer is tail. Now you might ask me or ask yourselves, insert at beginning, what is tail got to do with it? We are doing it at the beginning. But that's the beauty of circular linked list, right? That's what we discussed. That if you have the tail, then tail's next is your head. And now you know head, then you can do an insert at beginning. And that is why you need the tail pointer. So that's why this answer is tail. Ending. Okay, good. Asifur Rungshit Sayan. Good. So we will break for the live stream is on. We will break for 10 minutes and we'll come back. Let me put a break window of 10 minutes. And we will come back exactly when this timer elapses. Chalo. Guys, we are back. You heard some nice music, now hear my boring music. Are you all here? All ready? Should we start? Okay, let's start off. Good. So we start off by touching upon a very important topic, which will be very useful from both your interview perspective as well as your subsequent papers that you will have in the subsequent years. Trees, right? It will be a part of your if you have the paper called design analysis and algorithm, it will be very much part of it, thick and thin part of it, right? So trees is something we need to very well understand if we are actually to stay in the relevant streams that we are in. Now, if you see from a trees perspective, what I've tried to do is, let me put this here. Yeah. Okay. So from a trees perspective, what I've tried to do is, I'm trying to show you this side so that I can increase this and you can concentrate on the wordings here, and then we will move to the left side. So in your syllabus, what is mentioned is that you need to understand the terminologies of a tree, right? So the terminologies of a tree starts from the root. Now, who is the root? A root is somebody who does not have any parent. That's all. First of all, you need to understand what are we talking. We are talking about nodes, right? What are nodes? Nodes are any entity that is storing some data in this hierarchical fashion. That is what is a node, right? So if a node is any entity that stores data in a hierarchical fashion, which we call as a tree, then what is a root? A root is a node. Everything is a node. Every round shape that you see on this screen is a node, right? So everything is a node means root is a node, but it is a special node which does not have any parent. So that is what is the root. The data that I was storing inside is called as the key. Every node is connected with the next node by using an edge. So we call that as an edge. Somebody who has children like this, that is an edge connecting to lower level nodes, is actually called as a parent. And somebody who has a parent, that is an edge that is connecting to some higher level node, is called a child. This entire block, this triangular block that you see on the screen, is actually also a smaller tree and therefore is called as a subtree. So anything that you take here smaller in nature is also a subtree. This is a subtree. This is a subtree. This is a subtree. I can also say that this is a subtree. I can do any combinations of nodes as long as it is part of the bigger picture. It is a subtree. I can say this is a subtree. Yes, this is also a subtree. A single node at the leaf is also a subtree, right? These are called leaf nodes because they do not have any more children associated to it. So that's why all of these are called as leaf nodes. And if you have nodes of the same parent, that is B, then we call them as siblings. So that is on the data structure of the tree. Now the height of a tree is actually very important. Height, level and depth, these three things are very important. Height of a tree is, let's take this example now. When you start from wherever you want to measure the height, suppose I want to measure the height from here. if I start from here and I traverse to the leaf node, how many edges am I using? I am using 2 edges. So the height of f is going to be 2, but with a caveat. The caveat is this edges should be the longest path. So if I actually go from the root, right, what I said, height is from that particular node. If you look down and go to a leaf node, mind it, you have to go to a leaf node, and that traversal has to cover the maximum path. So for example, if I am here and I want to measure the height of root, then I can go here, and I reach a leaf node. Then is my height 2? No, because there is a longer path like this to reach to one more leaf node, which is 4. So the root node's height is going to be 4. Remember that height is always the largest height. What about level? Every node at that particular generation, we call this generation. So this is some generation, this is some generation, this is some, just like the your family tree, right? These are generations, so those are called levels. So at this level, all the nodes will have the same generation of parents, same generation of grandparents, and so on and so forth. They start with a 0 index. Sometimes they can start with a 1 index depending on the question. Be careful on levels, what index it starts from. So these are called as levels. What is the depth of a tree? The depth of a tree is and come back to the root, come back to the height. We express, or I express to you, what is the height of a node. I said height of this node is something, or I said height of this node is something, I said height of this node is something. Then what is the height of this entire tree? Height of the entire tree is the height of the root. As simple as that. Right? So height of the root is the height of the tree. But you can have height of separate nodes. You can say that this node has a height of 1. Yes, you can say that. Each node has a height, the tree has a height which is equal to the height of the root. So that's on the this side of things, height side of things. On the depth side of things, which I said is also important, the depth of a tree is actually going to be the suppose you are underneath the water and you look up, then basically you are at a depth, and when you look up and you want to reach the surface, the amount of distance you have to cover is your depth. So likewise, if I am considering this is where I have drowned myself, right? I'm drowning. This is at this level is where I'm drowning. Then if I look up and want to go to the root is my surface. Then how many edges did I cover? 1, 2, 3, 4. I covered 4 edges. So my depth of this M is going to be 4. Right? So my depth will be 4. See, the depth is actually matching with the levels. If I see the depth of G, if I look up, I will go to the root. So to go to the root, how many edges? 2. So the depth of this is also matching. So depth is the same as level, provided you start with a 0 index. Remember that. So that's what I wanted to show you here. Now let us come to the other side of the story. We are now talking certain terminologies, and we'll also talk about certain mathematics which we will derive also in order to make you understand more about what is typically being asked. So the edge and n-1 property is something that we need to be aware of. So we know what is an edge by now. How many edges are there? If I count the edges, 1, 2, 3, 4, 5 and 6. So we have 6 edges. So we have 6 edges, and these 6 edges that we have is what we have written here. But imagine how many nodes we have. 1, 2, 3, 4, 5, 6, 7. So n is 7 for us, which is the total number of nodes, and edge is 6, which brings us to a formula which says that the total number of edges will be n-1. Right? That's the tree property, which says that my total number of edges for any number of nodes that you give me will be always n minus 1. Right? So that's something that please remember this. And it's whatever we are doing in trees in a mathematics formula standpoint will always be a function of n or e, the number of nodes or the number of edges. So I hope you understand node and edges now. Binary trees, let's talk about them. General tree is where there is no restriction on the number of children. Right? So you can have as many number of children in a general tree. But in a binary tree, you will always be having 2 children at most. Right? I'm not saying always be having, you could have 0 children also or 1 children also in a binary tree. But the point is that it is the maximum of 2 children, whereas there is infinite number of possibilities of children in a general tree. Now, if in a binary tree, if I write it like this, A, C, B, D, then this tree is the same as this tree, because the sequence in which we wrote CBD is not the same as the sequence in which BCD is, but it does not matter for a general tree. But however, it matters for a binary tree perspective that if I write it like this, this is no more the same tree as the left hand side. So the sequence of the left child and the right child, it matters, the position matters. So that's the difference between a binary tree and a general tree. 2 things, children are limited and children are ordered. So those are the 2 things that you will have to remember when we talk about binary trees. Now, how do we store a binary tree in a 1D memory? Right? Yesterday we took a 2D matrix and we started and stored it into a 1D array. Similar concept. This is a graphical structure. It's more of a 2-dimensional structure. It has a dimension along this line. It has a dimension along this line. So how do we store this 2-dimensional into an array? What we will do is, how do we read things? Top to bottom, left to right. That is what we do. Top to bottom. And in every top to bottom, in every row, what are we doing? Left to right, left to right, left to right. So that's what we are doing. We will read this in the same manner. So A will go to the first index of the array. By the way, here we are using 1 index, 1 based indexing. And then B will go here, next element. Then C comes the next element. So natural process, whatever you read, the next elements come here and beside here. Right? Now, if I talk about that, okay, excellent, you have been successful in taking a 2D graph and put it into a 1D array. Very nice. Now, can you tell me from that 2D array or 1D array, if I point you to one element, can you tell me who is the child of that particular element? Who is the parent of that particular element? So that's where these 2 formulas will now come in. Let's talk about this particular case where I say that I is equal to 6. If I equal to 6, we are here. Right? So if I equal to 6 and we are here, then the parent of that particular value of I is, or parent of f in this case, is going to be the index that we are in divided by 2 and the floor value of that, which is going to be 3. So parent of f, it is saying it is in the 3rd index. Go to the 3rd index, you will find the parent of f. We get C. Is C the parent of f? Yes, of course, C is the parent of f. Right? So that is how you get to the parent of f. So the formula for parent is this. Do not forget it. Parent is I by 2, floor of that. When we say children of B, then we know B means I equal to 2. And the children formula is 2i for the left child, and for the right child it will be 2i plus 1. So we get the left child as 3, the right child as 4. So at the 3th index and at the 4th index, we will get the left and right child for B. So at the 3th index, 2i, my bad. I'm sorry guys. That's the problem in a muted chat. Otherwise you would have corrected me by now. Okay, so 2i means 2 into 2, 4. And 2i plus 1 is this one, which means 2 into 2 plus 1, which is 5. So when I say that we are working with I equal to 2, which is B, right? So for B, who are my children? For B, my children are 4 and 5. Check B's children, whether they are D and E or not. Yes, they are D and E. So these are the two formulas that you have to remember when it comes to storage of binary tree as an array, because you will not need to just store, you'll also need to retrieve and understand who is the children, who is the child, and that's how you do it. Now we come to a full binary tree. These are different types of trees. Sometimes short notes come. So if you read this particular small portions, you don't need to write anything else. You can immediately start writing one paragraph about it. Just remember whatever is written here. You can actually rephrase this into an entire paragraph. Full binary tree or a strict binary tree is that we said binary tree can have 0, 1 or 2 children. Now I am saying no, I will not allow this one. You can only have 0 children or you can only have 2 children. So this particular node has 0 children, whereas this particular node has 2 children. These nodes have 0 children and this node has 2 children. So this is definitely satisfying my full binary tree. So that's on full binary tree. The next type of tree is complete binary tree. Complete binary tree is saying that every level is filled up from the left to right. So it is not like this, that you will have a tree like this. You cannot have a tree like this and say that this is a full binary tree. That's not how it works, because your left has to be filled up first, right? So left fill up first is important, and all the levels will be filled up except for the last level, right? Why? Because the last level is the leaf level and you may not have the appropriate number of elements to fill up all the parents. So like here, we did not have the last element to actually justify that the entire level will be filled up. So this level filled up means what? 1 node should be there. This level filled up means what? 2 nodes should be there. This level filled up means what? 4 nodes should be there. But we don't have this node, which is fine because this is my last node. Last node is allowed, or last level. Last level is allowed. And did you fill it up from left to right? Yes, I did fill it up from left to right. I didn't have D empty. D is on the left. So those are the 2 important points on binary trees, complete binary tree. The perfect binary tree is when every level is filled up with its max number of nodes. And the total number of nodes as such that will come will be, what is the height of this tree? The height of this tree, if you see, is 1, 2. So the height of this tree is 2. Now if I say 2 to the power h plus 1 minus 1, it is 2 to the power 2 plus 1 minus 1, which is 2 to the power 3 minus 1, which is 7. And you see the number of nodes here, you will see that it will have 7 nodes. So the n is equal to 2 to the power h plus 1 minus 1 is an important formula that you will have to remember to calculate the number of nodes or to calculate the height interchangeably when it comes to any kind of sums. So that's on perfect binary tree. On skewed binary tree, we are really talking about something which is going like this, like an ordered pair. Like if I say I have 1, 2, 3, 4, 5, 6, 7, 8. Right? If I have to store this in a binary search tree, let's say, then you know by now that in a binary search tree, the right node will be greater than the parent, the left node will be less than the parent. And when I say right node, I should not say right node. Right subtree should be greater than the parent. Left subtree should be less than the parent. So if I have 1 here, 2 should be here, 3 should be here, 4 should be here, 5 should be here, 6, 7, 8. Which means I am constantly going to the right direction without utilizing these relevant nodes which I am missing to utilize upon, right? And therefore my height is unnecessarily increasing. If I could have utilized some of these nodes here, then my height would have decreased, right? So but my height is constantly increasing. Now what is going to be the height of this tree? If you see the height of this tree, this height of this tree is the same as the total number of edges that we are counting, because if I just take 1, 2, 3, let's say we have 5 elements to be done. So if these are the 5 elements, 4 and then 5. Suppose these are my 5 elements. If these are my 5 elements, what is the height of this particular tree? So the height of this particular tree, as I told you, any height of any tree is from the root. If I go to the largest leaf, so largest leaf is here, so I will take 1, 2, 3, 4. So I took 4. I counted 4 edges. But isn't this the maximum edges of your tree? Right? This is the maximum number of edges of your tree also. That means you are really talking about this formula now. We just now talked about this formula. We have come back to that formula again. So we were talking about this formula, right? E equal to n minus 1. We had learned how it is coming. Now we are saying that we are now seeing a situation where the height of a skewed binary tree is equal to the total number of edges of the tree. So the height is equal to the total number of edges, which is equal to n minus 1. Right? So n is the total number of nodes. Count the total number of nodes. 5 nodes are there. That means my height is equal to 4, which is equal to the edge. So the total number of edges, which means equal to the E, not the edge. There is no edge as such, but E stands for the total number of edges. Right? So now the fact that we now have this formula where my height of a tree is equal to the total number of edges, and that total number of edges is going to be evidently equal to n minus 1, because your whole tree is skewed to the right. There are no more edges. Therefore all the edges are contributing to what? The height of the tree. That's on binary search tree. So what is the so you should not take a skewed binary tree like this, for that matter. You should not take this is not a skewed binary tree. Like everybody should be towards the left, everybody should be towards the right. Then this particular statement is valid, that my edges is going to be the height of the skewed binary tree. Balanced binary tree is what? A balanced binary tree is when the left subtree height is the same or is minus the right subtree height is less than equal to 1, which means the left subtree height from A is going to be what? The left subtree height from A is going to be 1, in the sense that you just have actually not 1. So from A, if I take the left subtree, the height, in fact it will be 1. If I draw it like this, then it will be clear. So A, B, C, D, E. Now you cannot have a tree not starting with a root. When I say left subtree, I mean left subtree is this. When I say right subtree, I mean right subtree is this. So this edge is not counted when we talk about left subtree and right subtree, right? So that edge, so when I say this particular subtree's height, that is equal to 1, this particular subtree's height is also equal to 1, right? So height of left minus height of right is equal to 1 minus 1 is equal to 0, which is less than equal to 1, which is still okay. Can I have something like this? Can I have a tree like this, let's say? So if I have this and I take the height of my left subtree versus my right subtree, then the height of my left subtree is 2 here, because this is 1 and this is the second edge, whereas the height of the right subtree is 1 here, right? So that becomes my 2 minus 1, which is equal to 1, which is less than equal to 1. So if I would have increased the left subtree a bit, and if I would have kept the right subtree limited, right, then the left subtree is this, whose height is 1, 2, 3, right, whereas the right subtree is still 1. So 3 minus 1 is equal to 2. 2 is less than equal to 1 is incorrect. Therefore, this is not a balanced binary tree. So not a balanced binary tree. So balanced means that there is not much difference between the left subtree and right subtree. We have tried to utilize most of the space that we have in order to fill the nodes. That's what the balanced binary tree is trying to tell you. Now binary search trees we have already discussed. Only thing you remember is in a binary search tree, because your left subtree is less than the node, that is the parent, right, is less than the right subtree, what you are actually achieving is an in-order traversal. So you are saying that the left root and right concept is completely going to generate me a sorted array, because this is how it is structured. This is my left, this is my root, because this is my parent, and this is my right. So if I go and make an in-order traversal, then in-order traversal of a binary search tree means that go to the left, go to the root, go to the right, right? And in that case, what I will be doing, this will be always less than this root, and which will be always less than this right, because that's how BST is structured. So this means that we will have a situation where ultimately at the output we will have a sorted array, and that is only possible if you do an in-order traversal of a BST. So remember these two things, in-order and BST. If you do that, then only you get a sorted array, right? So that's on the binary search tree. Now we'll calculate certain things. Maximum number of nodes at a given depth. So it is saying, how do you find out the maximum number of nodes at a given depth? So if I take the first level, then this is the maximum number of nodes I can have, right? When I say depth can be interchangeably taken as level. If I take the level at 0, this we had discussed just now. So this is level 0 as well as depth 0, right? So next, if I take this 2 nodes, and this is at level 1, depth 1. So if I take one more, then this is at level 2, depth 2. So how many nodes do I have at depth 0? At depth 0 I have 1 node. At depth 1 I have 2 nodes. At depth 2 I have 4 nodes. At depth 3 I would have had 8 nodes, right? So can I find out a correlation between this depth and this number? The correlation is that this 1 can be generated from 2 to the power 0, where I am banking on this 0 as this 0, right? So then I can definitely put a generic formula out of this and say that this is equal to 2 to the power of 1. This is equal to 2 to the power of 2. This is equal to 2 to the power of 3, right? So can I therefore say at a depth of k we will have 2 to the power of k maximum nodes? So at this level I have maximum nodes of how many? 4. At this level I have 2. At this level I have 1. So at the kth level I will have this 2 to the power of k maximum nodes. So that is what maximum nodes at a given depth. It is not talking about the total number of maximum nodes. It is only saying at that depth what is the maximum node, and that's what we found out. At that depth of k it will have 2 to the power k maximum number of nodes. So that's on the binary trees, on that particular matrix that we wanted to measure. Now if I switch this and say that, okay, now we know this, now can you tell me then what is the total number of nodes at a particular depth, given a particular depth, and we are giving this depth as, let's say this is 0, this is 1, this is 2, and this is 3, right? So this is at depth 3. Why? Because if you see, you will take 3 edges to go to the root. You will take one edge here, one edge here, one edge here to go to the root. I told you depth is how many edges you will take to reach the surface, right? So that's what, and the surface is your root. So you get 3 edges. Now in this tree, they are asking that given that I have given you this maximum level that you can go till 3, tell me the total number of nodes. Tell me the total number of nodes. So if you remember the way we calculated average, we took every position and we took it independently. Here also we'll take independently, and we'll say that at level 0, at level 0, I can have how many nodes? 1 node. At level 1, I can have how many nodes? 2 nodes. At level 2, I can have how many nodes? 4 nodes. Then we can have 8 nodes. So at level k, how many nodes can we have? 2 to the power of k. Because this was at level 0 means 2 to the power of 0. Then this was 2 to the power 1, 2 to the power 2, 2 to the power 3, then dot 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 2 to the power k. So this translates to a summation of 2 to the power I, where I ranges from level 0 to k, which is equal to 2 to the power of k plus 1 minus 1 when you do it from a geometric progression standpoint. So this is what is the maximum number of nodes given a particular level. That is how you will get the maximum number of nodes. Okay, now let me go back to the chat window and see what's happening before I move on, because this is going to be a lengthy session. Repeat n-1 please. Tanmoy. n-1. What was n-1? Acha, n-1, the edges. You still want that repeated? Edge is equal to n-1? Tanmoy say yes, I will repeat it. If say no, I will not repeat it. Okay, now sir, but what if B didn't have 2 children? Say E. What if B didn't have 2 children? Say E wasn't the child of B, then F would have been at 5. Yes, how does that matter? Come on, here, let me see what you are trying to say. So you are talking about the flattening, I am sure. So let me go there. So you were talking about E. What is the question you are asking? You are asking that what if B didn't have 2 children? Say E wasn't the child of B. Okay, E wasn't the child of B. Okay, so the tree looks like this: A, B, C, D, and F. Perfectly possible. This is what you are trying to say. If this is how the situation is, then you will fill it up in the same manner as you go left to right. Now, what you will have to be very cautious about, and this is a very nice question you have asked. What you have to be very cautious about is, when you fill up, you will have to assume somebody will come here. You will have to assume at some point somebody will come here. And you will have to keep that space here. So, when you fill up, you will fill up A here, B here, C here, D here, and then keep a space. And then move on to F. This is what you will do. Very nice question. This is something that all of you please also understand, that when you have a space which is naturally supposed to be filled up, then to convert it into an array, please make sure that that space is empty, because your genetic logic of child and parent will take into account that particular node also. Right, so good question. Thank you for that. Ketchup Night. If we consider 0th index array, then the left child formula will be 2i plus 1. Right child formula will be 2i plus 2. And parent would be I minus 1 by 2. Yes, that is right. Acha, Shudojit, you wanted something to be repeated one more time. I don't know what that is, because I missed your chat. I was on another screen. Okay, so that's all I think I have covered. Shudojit, if you want something to be repeated, please call it out. What to be repeated, I will repeat it happily. So let's move on. We have a lot to cover on trees. Okay, now comes a very important thing that typically comes. I've seen this come at least 2-3 times. So please concentrate on this particular thing. Minimum height of a binary tree with n nodes. Right? So if I give you n nodes, then probably you can create a tree like this. I have given you 4 nodes. You create a tree like this. Is this the minimum height? It is not the minimum height. The minimum height that you can create with 4 nodes is this. That is, this is a 2 height tree and this is a 4 height tree, but with the same number of nodes, 4 and 4. So I hope you understand the question now. What is the minimum height given n nodes? How can you know what is the minimum height of a tree? Right, so what we will do is, okay, Shurojit says the mathematical expression. Which mathematical expression, Babu? This one. The maximum number of nodes in a binary tree of depth k. Is that the one, Shurojit, you are talking about? Whatever is on the screen right now? Okay. So if you want a repetition of this, I'll quickly repeat. In these nodes, if you think them as levels, then how many maximum nodes are possible here? That is written on the right. Sorry, these are the levels, that is written here. So how many maximum node is possible at the 0th level? 1. How many maximum node is possible at the 1th level? 2. How many maximum nodes is possible here? 4. Right? And so on and so forth. So can I write 1 as 2 to the power 0, 2 as 2 to the power 1, 4 as 2 to the power 2, 8 as 2 to the power 3? Then definitely at the kth level, what is this 0? This 0 is this 0. This 1 is this 1. Right? So then at the kth layer, if there is a kth layer here, then this last element will be 2 to the power k. That means you are summing up from 2 to the power 0 to 2 to the power k. That means this is the sum that you are doing. That means this is your output. So that's all that is there. Shurojit, clear? Okay, good. Now let's move on here. So what I was saying is, given n nodes, these are my n nodes. 4, 4. I can actually create one node like this, one tree like this, one tree like this. Their heights will be different. Question is, how can I know what is the minimum height given n nodes? So to tackle this problem, what we will do is we will try to use whatever we have learned in the past and see if we can actually do justice to that. Now we have already learned that 2 to the power h minus 1, if you remember, we learned a formula earlier. Where is this formula? We talked about it here, right? So total nodes at a height is equal to 2 to the power h plus 1 minus 1. So at a height, whatever height that is, my total number of nodes is 2 to the power h plus 1 minus 1, where h is my height of this. So that is my maximum that I can have in terms of the total number of nodes at a particular height. So I'm trying to approach this problem by saying that let me move to the correct position. So I'm trying to approach this problem by saying that my maximum height, let me remove this, done. So I am what I was saying is, yes, 2 to the power h plus 1 minus 1 is the total number of maximum nodes. I hope all of you agree. At a height h, 2 to the power h plus 1 minus 1 is the total number of maximum nodes. Now if that is the case, then I can always say that if my tree has n nodes for that matter, then n will be less than n max. Or if I write it in the other way, I can say that while I understand that n max is the total size, is there a minimum size or is there any arbitrary in between size? That in between size is n, right? That in between size is n. So if that in between size is n, can I write that n max is greater than n? Definitely I can write, or greater than equal to n, let's say. Then can I write then this is implying that 2 to the power h plus 1 minus 1 is greater than equal to n. I just substituted here this because this was equal to n max. So 2 to the power h plus 1 minus 1 is greater than n. Then if I now solve this, 2 to the power h plus 1 is greater than equal to n plus 1. Then h plus 1 is greater than equal to, if I do a log, h plus 1 is greater than equal to log base 2 of n plus 1. Then h is greater than equal to log base 2 of n plus 1 minus 1. So if there is such a height where the total number of nodes is lesser than the maximum number of nodes, then that height will be at log base 2 n plus 1 minus 1. That is your answer. I'll again repeat, this is a critical thing to probably understand. We are saying that we know that given a height, the maximum nodes possible is 2 to the power h plus 1. Given a height, the maximum nodes possible is 2 to the power h plus 1. Now can I therefore say that I will keep on reducing that n and see if I can have an intermediate value of this, which is n. I am reducing from n max and I am coming down and I am getting an intermediate value of n, and in that intermediate value of n I can definitely assume that 2 to the power h plus 1 minus 1 is going to be greater than equal to n, right? So what this helped me is to find out a relationship between the number of nodes and the height of a tree, and then I'm playing around with it, right? So I wanted to see that height of a node and the number of nodes, that relationship I wanted to see. The only relationship I knew was this. So I started with this relationship, height and number of nodes, and then I said n max will definitely not happen, right? So let us reduce that n max to an arbitrary value, which is n. Therefore n max will definitely be greater than n, right? So that is that n that we are talking about. This n is what we are talking about. This is that n, right? So with this n, what is my height going to be? So then I will substitute this here and I will calculate for the height. I will solve for the height, and that will be my answer, right? So this is something that is very critical for you to understand. It's a bit off track kind of a derivation, but it comes, right? So please read it carefully. Now, maximum height of a binary tree with n nodes. Binary tree with n nodes. The maximum height is going to be a skewed binary tree, na? Because if I give you 8 nodes, then the maximum height you can create is n minus 1, because e is going to be n minus 1. That means e will be 7. Height comes from e only, na? So height is e, which is 7. So that is the maximum height you can create. And when will that happen? It will happen when you do like this, right? So it will happen when you do like this. This is your first edge. This is your second edge, third edge, fourth edge, fifth edge, sixth edge, and seventh edge. How many nodes have you included? 1, 2, 3, 4, 5, 6, 7, 8. Right? So for 8 edges you have, or 8 nodes, you have e equal to 7, and that's your maximum height. No other way you write this tree you can get a maximum height than 7. Therefore the maximum height of a binary tree is going to be always n minus 1, which is nothing but your e. and that happens when in a skewed binary tree. The relationship between leaf nodes and degree 2 nodes. So if I take these nodes, then what are my leaf nodes? My leaf nodes are this, right? So how many leaf nodes do we have? We have n0 is equal to 4. And how many number of 2 degree nodes we have? So the number of 2 degree nodes we have is, this is one 2 degree node. 2 degree node means 2 children, right? So 2 degree node means 2 children. This is one 2 degree node, which is one more 2 degree node, right? So you have n2 as 3. So what is the relationship? n2 is equal to n0 minus 1 is coming out to be the relationship between leaf nodes and degree 2 nodes, right? So that I hope is clear here. Yeah, now this is again something for which you need a good calculator. It's called Catalan number. If I give you a tree, if I give you a tree to draw with let's say 3 nodes, right? If I give you a tree to draw with 3 nodes, you will be probably drawing like this, or you could draw like this, right? Or there could be other possibilities if I increase the number of nodes. So when I say that these are the possibilities, for 4 nodes there might be some more possibilities of how you can draw a tree. How do you figure out, given a particular number of nodes, how do you figure out the total size of a particular or total number of ways in which you can draw a tree? That is what it is saying. Number of all possible ways in which a binary tree with n nodes can be created. Structural count. The structures change. How many counts of such structures are there? Given n nodes, can you create so many structures using those n nodes only? And that comes from the Catalan number, which is 2n factorial by n plus 1 factorial and n factorial. Outside your purview to probably prove that, this is a formula. Apply n and you will get 14. So for n equal to 4, this is 4 nodes that we were talking about. We will have 14 such ways of drawing a tree. For n equal to 12, imagine how big this number is, right? So this is your Catalan number concept. Just take the formula, apply it, but I hope you understand the basic principle, what is happening. As long as you understand that yes, if given n number of inputs, I will be actually consuming that many number of ways in which I can draw a tree, and that's what is Catalan number. Minimum number of leaves. Again, skewed tree will come to your help. In skewed tree only, you will have the minimum number of leaves, which is equal to 1. This is going to be the minimum number of leaves of a tree. 1 is minimum. So which tree will always have 1? Skewed. And maximum leaves will occur on a perfect tree. Perfect tree would mean like this, or it means like this. So this is your perfect tree. You have 4 leaves here. How do you get that? Total number of nodes here is 7, right? So you put a formula n plus 1 by 2 and do a ceiling of that. So then you get 7 plus 1 by 2, which is equal to 4, right? So that is how you get the total number of leaves or the maximum number of leaves given a value of n. So those are the leaves that you can do. You might not be doing that. That is an arbitrary value of n. But for a maximum value of n, you will always have to go there. So that's on the possible number of leaves for n nodes. Internal nodes versus total nodes. I think this you understand already. This is my tree. Then n0 means my leaf nodes. Leaf nodes, why? Because 0 children. So 0 children is how much? 4. These are my 4 leaf nodes. Internal nodes are all those nodes which are not leaf nodes. So this entire stack is internal node, right? How many internal nodes are there? Ni. Ni is equal to 3. Then the total number of nodes n will be 4 plus 3. That is a no-brainer, right? So n0 plus ni. So that is what this particular slide is trying to tell you. Now we get into the traversal part of it. We are at 12:30. Let's see if we can finish it off before 1. I doubt, but if we have something left, we will start after lunch and we will finish it off before starting the rest of the trees. BFS, DFS. Let me check the chat window. Some time gone. Why I am writing k plus 1 in the power? Shurojit Ghosh. Why I am writing k plus 1 in the power? Where are you writing it? Let me see which one you are talking about. K plus 1 in the power. Oh, okay, this derivation. Sudhajit, please see Taylor series and please see binary theorem. Or sorry, what is that? Sorry, not binary, geometric progression. Both of these, if you see, you will get your answer. That is beyond the purview of this class. Otherwise, if you want, come down to me, I will help you. Please see Taylor series expansions and please see geometric progression. You will get to see how this comes to 2 to the power k plus 1 minus 1. I hope that is what you were asking. Okay. Mathematically I have explained. Logically you can think about it. You will get the answer also. Logically also you will get the answer. Now, where were we? Okay. So we are now starting with the traversal. So breadth first, depth first, we have heard about it. Now we are going to talk about it also. Breadth first, depth first is where normally all the operations that we do are depth first operations. Your pre-order, in-order, post-order, all of that are depth first operations. So depth first operation does what? It goes deep before going wide. That means it will go like this, then go like this, then come down like this, is what depth first operation is. But breadth first will do what? It will go like this. That is what breadth first will do. And we will see the breadth first operation when we start doing some amount of graphs, right, at the next class. But then that's our primary focus right now in today's class is the depth first operation. And when we actually need to complete one path fully before we can actually go to the neighbor. But here it goes to the neighbor first. That is, go to your left and right neighbors and then go deep dive there. Right? Once all the neighbors are done, go to the next level neighbors and so on and so forth. I hope you understand. One is row wise, one is column wise. That way also you can think. Now, if I talk about the pre-order, in-order and post-order, one important thing please remember, don't mug up what is in-order, what is pre-order, what is post-order. Right? Always think that this in-order, pre-order, post-order is with respect to the root. Pre, the word pre applies to the root. The word in applies to the root. The word post applies to the root. So if the word pre applies to the root, then therefore pre must be the root. Then do a left right. If the word in applies to the root, then it should be in between, inside, in between, and then do the left right. And if the word post applies to the root, then the root should be at the right, post at the end, and then apply your left right. So that way you will never forget. So apply it to the root, and that's what this was meant for. Now, if you understand this, how to remember, then how to traverse. So we will only print. Print means what? A tree is meant as a storage. And at the end of the day, somebody will utilize that storage. So when he utilizes it, he could do several things with every node. I am saying he's only doing the print. In DSS terminology, it says visit. This term is very important, visit. Visit means you are doing the work that was intended to be done with that particular node. That is what is visit. Again, my camera shifted. Is it okay? Okay. Again, what I'm trying to say is that think about why you are storing things in a tree. You want to do something with those elements. What do you want to do? Probably you want to take it and create a let's say you want to multiply 20 to each of the elements and store it back. That is an operation. That's called visit. Visit could also mean that take those nodes and print it. Yes, that's an operation. Any operation is a visit, right? Any operation that you actually wanted to do, for which you stored them there, is a visit. So if we do a pre-order traversal, right? People who might not be aware of how to do a pre-order traversal, please concentrate here. We are saying that pre-order traversal, we will take root, left, right. We start from the root element here. Now every element is a root. Every element may have a left, may have a right, but every element is a root, right? So this is a root where this is my left subtree of the root, this is the right subtree of the root. This is a root where this is the left subtree, this is the right subtree. This is a root where this is the left subtree and there is no right subtree. This is also a root where there is no left subtree, there is no right subtree. This is also a root where there is no left subtree, there is no right subtree. This concept you have to get very clear. Every element is a root, and you have to imagine that element as a root in order to solve this problem. So when I say root, I have gone here. If root is something that I can visit, and remember when I said visit, you can only visit the root. When the root comes in your sequence of things, you can visit the root. You cannot visit the rest of the nodes, left or right. You will traverse, but you will not visit. Right? So that's something. Acha, my picture has gone off. 1 minute. Let me bring it back. I hope it is back. Yes. Okay. So now let's come back. We are doing a pre-order traversal. How will we do the pre-order traversal? Let us see. I have to visit the root. I have the right to visit the root. Root comes in the first sequence. Therefore, I will print A. Then I have to go to the left. Left means what? The entire left subtree. It says go to the left subtree and give me whatever it is. So the whole process again starts here. The whole process of this again starts here. When you go to this left, right? So the whole process will start with what? By saying that, okay, now take the root. Take the root means I have visited. Take the root means I have visited. So if I visit, then put it here. Printing. I'm saying printing is the job that I'm doing. Then visit means printing. Now this is printed. Once this root is printed, what do we do? Left. So then I will go left. Right? Left of this. Left of this means this is one more subtree. Right? This subtree, the entire process starts here. Again, the entire process will start here. When this process starts here, this is the root which doesn't have a left subtree and a right subtree. Right? So I am visiting the root means I will print it. So I will print this. Then I will print what? I will print, I will go up because my D is gone, my D is done, my D is done. So I go up. I had come to D because B told me process the left. I process the left, I have come up. Now B tells me process the right. Because that is the right thing that needed to be done for B. So B had to do what? B had to do root, left, right. So B root is what I have written here. B left is giving me D. Now B right has to happen. Right? So B right will treat this as one more new thing, new subtree, and which will have no child here. And therefore this E will be printed first. Then left child is not there, right child is not there, it will come up. Right? So what will be printed? E will be printed. It has come up here. B says, I am done. I am done. My job is done. Who asked it to do it? A asked it to do it. Now we started with A. We said left subtree. Let's see what it is. So now A is saying right subtree. So A says right subtree. In the right subtree I get this small subtree. So this starts, again the root starts. So this is C, which is the root, right? So this root will say that I can visit the root. So I will visit the root C. When I visit the root C, right, I am okay to go to the left subtree and right subtree because this is an independent tree for me. I am doing this entire process again. So root, left, right is what I will do. So root I have done, left I have gone. This left becomes one more subtree for me. So I will do this left as a root first, right, and then this as a root first, and because it does not have any left child or right child, I will come back to C. C says okay, go to the right. Right does not have any child. So then C's process is over. Who asked it? A. So it goes back to A. A says I am done. My left is done, my right is done, root was anyway done. So that is your pre-order traversal. Now people who might not have thought about it in this way, this is the best way to remember it. And if you have already thought about it, fantastic, right? I'm just trying to give you the best way to remember it. There is one more way we will discuss, and that way I'm not going to the in-order and post-order traversals in details as this. I'm sure you can now figure out how to do in-order and post-order in the same manner I said, right? In the same manner, please attempt it. I'm sure you can do that. But I hope you can understand what is happening here. Recursion is happening here, right? And we will come to that. What is the problem with this? So I told you I'll give you one more way, and this way sometimes comes, and we are therefore talking about recursion now. If I use standard recursion to actually do what we are supposed to do, then how will this entire pre-order traversal look like for us? Let us try to figure that out. Now, pre-order traversal for us means root left right, and we will try to create the same pre-order traversal that we had done through this process. Now, if we say that a function is there called pre-order root, so I will give it the root and I will ask it to do the pre-order. Then the function says, okay, you are coming to me. I know I have to do three things. I know I have to do three things. What are the three things? Visit the root. What happened to the visit the root, do a pre-order of left, that is call self. Something is wrong. Okay, call self, so it starts calling self, and do a pre-order of right. So that's what pre-order says, that if there is a function called pre-order root, then it will do three things: visit the root, pre-order left, pre-order right. Right? Now, if I use this to my advantage and say that I will start with visit the root. This is my root, so I will start with visit the root, right? So visit the root, whatever that visit root is supposed to do, will do. The next step it is supposed to do is pre-order left. Now who is the left of A? B. So it will pass B to the same pre-order function, pre-order of B. Now pre-order of B will start, that means this function will start with pre-order of B. This entire three steps will have to be done now. So let us do those three steps. So the three steps are that first step is visit B. Yeah. So the first step is visit B. So that is what we are trying to say. Pre-order means that the first step is visit the root. So visit B. The second step, right, is that the same function will now need to do pre-order of left of B. What is left of B? D. 1 minute. Pre-order left of B, which is D. Right? So pre-order of the left of B. Now pre-order of the left of B, we'll call this function again. Right? So again some timeline will start here, which is visit D. Visit D. And that will mean that we need to therefore do after this pre-order of the left of D. Left of D is null, right? So the left of D is null would mean that pre-order of a null node, and this will immediately exit, because pre-order of a null node will exit. There is a stopping condition there, which is your condition of exiting from the recursion, the base condition that we call it. Then we have pre-order of right, that is the job. So pre-order of right, so that will also immediately exit, which means that this particular function has completed its 3 things that it was supposed to do. 1, 2, 3. These are the 3 things every function is supposed to do. This function has completed these 3 things. So it will now return here. If it now returns here, then this now starts off from here. Remember that you will have to make it start from after this last line has returned, because it's a timeline view. So it has to start from here, right? So from here you will start and you will say that it is a pre-order of D. After D you will go to the right of that child, which is pre-order of E. And the pre-order of E will also follow the same thing. It will be visit of E, and it will also now do the 2 null checks, which is pre-order X and pre-order X. So those are the 2 things that it will also do, which is pre-order X and pre-order X. So then this also has completed the 3 things that it was supposed to do. This also has completed the 3 things that it was supposed to do. So these are the 3 things that it was supposed to do. So it has completed those 3 things. So if it has completed those 3 things, then this has completed now 3 things. So now this area will start after this line, and we will say that you are going to do a pre-order of the right portion of A, which is your pre-order of C, right? So pre-order of C is what you will do. Pre-order of C means what? Visit C, right? And then this means pre-order of the left child of C, which is X. There is no left child. That means it returns. Then it does a pre-order of the right child. The right child is F, right? The right child is F. That itself calls one more time the pre-order, which is visit F. Do a pre-order of the left, which is your what is your left? Where is my left? Pre-order of left. There is nothing left, right? And there is nothing right. So we will have nothing on the left. We will also have pre-order of nothing on the right, right? So then this also completes its job. This also completes its job of 1, 2 and 3. So then this will return here. So this will complete 1, 2, 3. This will therefore complete 1, 2, 3. So my entire pre-order of the entire traversal is done. Now all you need to do is just log the visits, right, at your output. So just log the visits, which is A here, then you have B here, then you have D here, then you have E here, then you have C here, and then you have F here. If you match it, A, B, D, E, C, F, Did we get it? ABD ECF is what we got it. So this is how using recursion, if they ask you, please use recursion to show the in-order traversal. This is exactly the answer that you will have to give. Right? I hope this makes it clear. We are 10 more minutes. So let's see the chat window. Okay, Vishal, your question on pre-order, in-order, diye diye che, we will have to find a tree. We will discuss that in this same session. Just hold on to the thoughts. But I hope, guys, you have understood this recursion. Just tell me yes, okay, or no. The same way I explained here. How to use recursion to do pre-order. Waiting for your responses. Good. Thank you. So now you understood recursion. The same way, this is the same stack way that I would have taught you in case you have been with me for Tower of Hanoi. Same stack way for factorial. I would typically use this lifeline way of doing things. This is called a lifeline chart of doing things to actually explain the lifeline of a function and how it moves. So use this and then we can work on that. Now there are quite a few of other stuff that are remaining. I'm just trying to think whether it makes a sense to logically break off because this is more of a half an hour more session. I'll not take half an hour. Let's see how much we can complete. At least we'll complete one of it and then take a break at 1 o'clock. Actually no, it's already 7 minutes left. I don't think we'll complete it in 7 minutes. So we will take a break now. We will take a break now and we will assemble back at 2 o'clock. I hope we can get over the lag of half an hour that we have. We are lagging by half an hour. So we will finish this quickly and move on. There are a lot of trees that we will be completing today. The entire trees is what we will complete. So please be on time. Lot of questions comes from trees. I can't stress enough as to why I'm insisting that you attend these next 3 sessions, or rather the next 2 sessions after lunch and tomorrow mornings. Right? So please don't miss it. B tree, B plus tree, AVL tree, BST, all of that we will discuss. Right? So let's meet up and then we can start. Quiz, how will I do? We have not completed what we wanted to do. Right? So quiz we will do only after the binary tree is complete. We have 4 or 5 more slides for binary tree to be completed, which will take half an hour, after which we will do the quiz. So I'm switching on a timer of 60 minutes and then we will meet up at whenever we said we will meet up. Hi all, welcome back. Ayush, good afternoon. We will start in a couple of minutes. Hold on. Good afternoon, Shurajit. Good afternoon, Sneha. No, header list is not part of your syllabus. Good afternoon, Ketchup Night. We have 67. I'll just give it another couple of minutes. Farhan, good afternoon. Shomiran, good afternoon. Hashing is there, so we will see what to learn in hashing. Depending on the type of questions for run, whether hash table will be done tomorrow or not, I will decide that. So we will see, but it's just one single liner in your syllabus which says hashing. So hashing can be many different things. So depending on the type of questions that come, you will get to learn hash tables as well as different hashing concepts. Good afternoon, Srijib. Okay, so let's start off, guys. We have 70 of you here. I'm sure the others are struggling to finish their lunch. Dictionary in Python in your syllabus. What is this syllabus, Ketchup? We are talking DSA syllabus or Python syllabus? No, not really. I mean, in our data structures, we do not have anything which is similar to a key value pair that is part of our syllabus. At least I am not aware of it. But you can build it, whatever data structures you have. Python is also not a beast, right? They have built data structures based on some basic, or they have built dictionary on the basis of some primitive data structure only. So using some primitive data structure only, they have defined it. So let's say a linked list. Can you use a linked list to build a dictionary? Of course you can use a linked list to define a dictionary, right? So there's no stopping us to actually do it with the kind of knowledge that we have. And that's how people start building new things. As long as now you are powered or empowered with linked list, you are empowered with trees, you are empowered with graphs, you can start thinking of building any kind of complex data structures using those. but directly, of course, that is not part of your syllabus. We have 80 of you now. Good. I hope it hits 100 by the time we start off with the quiz. Let's proceed now. We will be starting wherever we left off. So first thing is construct a tree from a given postfix expression. And to construct this tree, we'll be a bit fast so that we can finish it off between now and 30 minutes from now. So let me just show you how we'll do it. So first things first, what we'll have to do is the construction of tree will be a stack based construction. We are calling this an expression evaluation. So this typically comes under your syllabus under binary tree expression evaluation, or they might tell you directly as a theoretical question without giving any example that give an example how binary trees help in expression evaluation. So you have to talk therefore about the expression tree. So we are trying to build a thing called an expression tree out of this. So how will we do it? So what we'll do is we will take a stack like this, and inside the stack we will take the elements as and when they come in. So if you remember, we had done this earlier in terms of our infix, postfix and postfix expression evaluation. So we are trying to therefore do a postfix expression evaluation here, and the postfix expression evaluation said that take the operands and push it into the stack. So A goes inside the stack, B goes inside the stack, C goes inside the stack, A, B, C. C goes inside the stack. Then you get to C star. So keep star outside, and with star you create an expression which is taking out the last two elements of the stack. So the first element will go to the right side, the second element will go to the left side. We have done this earlier. Now this becomes a unified expression now. B and C no more exist independently. So please put a bracket. They are aggregatedly evaluated and then push it back into the stack. So B star C gets pushed back into the stack. Now when B star C gets pushed back into the stack, the nature of this B star C can be represented rather as a tree. How? Let us see how we can represent B star C as a tree. So in B star C as a tree, we can say star, B was to the left of star, C was to the right of star. So when we are actually converting or using the infix way of writing things, we can actually draw that as the left node and right node of the operator. So B and C, this is the way we will actually write it, and therefore we are slowly going to build this binary tree from it. Now we are done with these three and the star. Now when I get a plus, again I will pop out these two. So I will pop out these two means the first pop will go to my right side, which was B star C, and the second pop will go to my left side, and the whole thing now becomes an expression, right? A unified entity. So that unified entity we will put here. A plus, we'll push it back into the stack. A plus B star C, then bracket ends, right? And this, if we now have to represent here, then how does it look like? B star C, if you see, is this part of the story is here. All you need is A and a plus. So don't you think that the plus will be here and the A will be here? This is something that will be justifying the way we will try to do things, right? So then we will put a star here, we'll put the connection here, and then we will take this and put the A here. So that means that this was already present, and this is something with which we are doing a plus operation. So this and this will be plussed. So that is how we are now building the tree. Next, what we'll do is we have done with plus, so now we are getting D. So D we will push into the stack. Then we are getting E. E we will push into the stack. Then we are getting star. Now this star will pop out two elements again, which are the top two elements. So we will say E will be popped out because of this star that came in, and then D will also be popped out. And we will put a bracket like this and push it back into the stack. So we will say D star E and push it back into the stack. And where we will probably write it, we will write it, let's say here, because we can't attach it to the left tree. So we will say star D and E. For the time being, let us keep it outside. Then we have F coming in. Then we have plus coming in. As soon as you see plus, what is your job? Whenever you see an operator, your job is to pop out the last two elements. So the last two elements we will pop out now. So F and D star E are the last two elements. So F and D star E means with plus, because plus came in, the pop happened for F, and D star E also was popped, which is the next element. D star E also popped, right? And this entire thing now becomes a complete expression, and that complete expression is what we are writing here. That is D star so D star E plus F. This is the entire expression we are writing in this part, in this portion of the stack, right? So that is how we will write this. Next, what we will do is this tree we will have to consider. So D star E was always there. All we need to do is have a plus and an F. So it is similar to the earlier example. The plus will be here, the F will be here. So then we can say that this complete entity is to the left of this plus. Yes, this is to the complete entity is to the left of this plus, and to the right is F. So that is how we will represent this part of the problem. Next, we have G coming in. So G will go here. Next, we have star coming in. So star will want G and the next item to be popped. So let us pop that. So we will be popping first G. Because of the star, G will be popped first, and then on the left we will write the next pop, which is D star E plus F. So this is popped and this is popped, right? So D star E plus F, and this entire thing becomes one single entity, and that entire thing now moves to this particular area of the stack, right? So we will put this here again back into the stack. So we are saying three brackets. Be careful about the brackets. D star E plus F star G. So that is how you will do it. And this D star E plus F, this left hand side of this particular thing is this left hand side tree. Then all you need is star and G coming up here. So what we'll do is we'll say star and then we will say G and attach them together. So now we have this particular issue also sorted out. And the last that we will get is plus. So if we get a plus, then this plus is going to pop out this element and this element, both these elements. So this star plus, for that we will have three brackets here, D star E plus F star bracket star G, and on the left we will have A plus B plus C, two brackets. So don't you think this plus is actually supposed to sit here and join these two trees, right? So this was your left subtree, this was your left subtree, and this was your right subtree. So this was your left subtree, here is your left subtree, and here is your right subtree. So this is how you will construct a tree given a postfix expression using a stack, right? So that's the way out. You can write a table. In that table also you can use the stack, write the stack. We have explained stack as a table in the last session also. So use that concept also if you don't want to do this particular concept. Now next what we will cover is this kind of problem very much comes. Be careful on not missing out on this particular problem. Post order and in order. Given the post order and in order traversal, construct the binary tree. So I will be either given a post order or an in order, or I might be given a post order or an in order, or I might be given a pre-order or an in order, but I will be never given a post order and a pre-order. This will never come, right? Because that is impossible to do, and we will explain why later on. But for post order and in order combination, or pre-order and in order combination, you will be asked to do a binary tree. And the way to do it is, we know that in a post order, we know that the root is always on the rightmost portion. If you see this expression, this clearly tells you, screamingly tells you, that A is the root of this particular tree. The post ordered expression will always have the root on the rightmost part of it, and the pre-order will have the root on the leftmost part of it, and the in order, what does it contribute? The in order contributes by saying that for any node, given any node, it can tell you the left and right subtree. Given any node, let's give E. So E, if I give it, it will say the left subtree is going to be DBG, the right subtree is going to be ACHFI. That's what this particular in order expression will always keep on telling you. So if I now take these concepts and apply it here, right, what we will get? Let's see. So we will say that we know now the root is A. So we will draw the root, because on the right side we have A. Rightmost portion of post order is the root, right? So A. Now we know if A is the root, then if we go to in order and say in order A is the root, give me the left subtree, right subtree. What will be to the left of A? What will be to the right of A? It will immediately tell you. I cannot give you the exact nature of the tree, but I can give you that D, B, G, E, A will be present on the left subtree, and C, H, F, I will be present to the right subtree, because these are to the left of A, this is to the right of A. So it tells you that these will be present, but where it doesn't tell you now. We'll come to that. Now take this left subtree. So this is also a tree. This left subtree is also a tree. If this is a tree, then the post order, if I search for this tree, then whichever element of this tree comes at the last will be the root of this small subtree. So if I search from the right, and I try to figure out which element from here, in fact my bad, I kept A is already taken, so it should be the left of A, right? DBGE. Okay, now if from this right side, if I go this side, which letter comes first out of DBGE? If I see this, B comes first. So B has to be the root of this particular tree. The subtree DBGE should have a root of B, is what your post order is trying to tell you. So now you go to again your in order friend and say that I know B is the root. Give me the left and the right. So now it can tell you the left node exactly. So D is the exact left node. It can tell you that. And G and E, it will still say that I still don't know between G and E how they are placed, but they will be there on the right part. So G and E will be there on the right part. So with G and E, if I again go, because G and E is again a subtree, so I can again go to post order and say between G and E, which comes when I see it from right to left? Which comes when I see it from right to left? So E comes when I see it from right to left. G comes later. So E becomes my root, because post order gives you the root. And with E, if I go here, then I immediately get to see that G is to the left. G is to the left. And that completes my left side of the subtree. That is, if you now see that originally in order predicted DBGE will come here, and see we have created DBGE here. Now on the right side, CHFI is what it had predicted. Now let us see if we get CHFI. So CHFI, if I take CHFI and see from again the right side, then which letter comes first? C comes first. So C definitely is my root. Now this C, if I take here and see what is to the left of that, nothing is to the left of that. So nothing is to the left of this particular C. Right? Only thing is HFI is to the right of C. That is what the in order can tell you. So to the right only this tree can grow. And if I take HFI and I try to see from the right which comes first, F comes first. So F definitely is the root. Now if I take F and go to in order and say tell me left and right, it tells H is the left and I is the right. And that's your tree. So this is how, if you get post order in order, this is how you will do it. If you get pre-order in order, just take the root to the leftmost part. We took the root to the rightmost part and then right to left we came. For pre-order, we'll do left to right. Rest of the process will remain the same. So that is on how you solve this. Now prove that the maximum number of nodes in a binary tree of depth k is 2 to the power k minus 1. We have already done it, which was 2 to the power h minus 1 if you remember. The n was equal to this. So that we have already done. Number of all possible binary trees with 4 nodes, this will be done through our Catalan number. You know how to do it now. Right? Question, number of possible distinct binary trees with 12 nodes, Catalan number again. So we'll use the Catalan number to do it. The minimum height of a binary tree of n nodes, that is the log expression that I told you earlier. So if you see here, we did this log expression calculation, this one. Minimum height of a binary tree with n nodes, log base 2n plus 1 minus 1. Right? So that is the answer to this. So these are the questions that typically come. So you should be careful about not missing out on these questions. And a binary tree has n leaf nodes. The number of nodes of degree 2 in this tree. So number of nodes of degree 2. Let me open it up in the chat window. Can you solve this? Binary tree has n leaf nodes. We have already done the formula. Try to recollect and apply that formula. Question is the last question that you see. Binary tree has n leaf nodes. Number of nodes of degree 2 in this tree is how much? Good. Good. Good guys. N minus 1 is the answer. And the way we are getting that is, we are saying N0 is equal to N2 plus 1. So my N2, which is the number of nodes what was the question? Binary tree has n leaf nodes, the number of nodes of degree 2. So n2 is the number of nodes of degree 2, which is equal to n0 minus 1. n0 here is given as n, which is the leaf node. So n minus 1 is the answer to this problem. Good. All of you have answered correctly. Let us do this. Who will answer this? You have to apply the formula, the flattening formula. Index number of the parent node. So given a child at I equal to 6, where is my parent? Yes. Yes, good. I by 2. That is where your parent is, which is 3. So 3 is the answer. Given a child, your parent is at I by 2. We had done this earlier when we were talking about flattening the array. Okay, now next question is on the same topic that we were thinking about, that given a pre-order sequence and post-order sequence, why can't we construct a tree? We said that pre-order plus in-order, we can construct the tree. We said post-order plus in-order, we can construct the tree. But then post-order plus pre-order, we cannot construct the tree. Why? Because they might give you the position of the roots. So there is nothing much additional that this particular expression gives you other than giving you the root, right? So post-order and pre-order both will give you the roots. Pre-order will say root is on the left, post-order will say root is on the right, but the root will be the same. So no additional information you will get, only root you will get from both these expressions. So what you will write as an answer is that you will have to say that let us take the pre-order as ABC. Let us take pre-order as ABC, which means A is my root. So this is my pre-order. And let us take the post-order for the same tree to be let's say BCA. Okay, so let us take the post order of the same tree to be BCA. So then A is to the right. So that's what I said, that you will not get any additional information. All you are getting is A is the root. That is all you are getting. So with A as the root, what can you do? You can actually say that my tree may look like this: A, B and C, right? Where I can say that the pre-order expression will match with ABC, or I can also say that my tree may look like, let's say, A, B, C. I can also say this, right? In both the cases, both pre-order and post-order will be satisfied. Now, both the pre-order, if I do a pre-order traversal of this, I will still get this, and if I do a post-order traversal of this, I will also get this, and I can do a post-order traversal of this also, I will get this. Right? So both the trees are perfectly going to give you both of these every point in time. So then which tree is correct? You don't know. Right? So they are not, so post-order and pre-order given together cannot give you one single tree. You can actually make sure that you draw multiple such trees which will satisfy both post-order and pre-order, because all we are speaking of is the position of the root. So that's all that is there from a this particular answer standpoint. Now the last question on this particular topic, let us cover that. That last question is on how do we take a non-recursive method to actually solve a binary tree in its in-order format. So you saw the recursive method. I explained the recursive method to you. Whenever you are doing depth first search, you will actually do a recursion in order to not repeat the steps or not do an iteration, not lengthy your code. You will use recursion to help you, and we saw that in the first half, right? How to use recursion for that. Now what I'm saying is the question wants you to do left root right, which is your in order traversal, and show us that you are not going to use any recursion to actually solve a particular tree. So left root right is what it wants us to do, and not use any recursion. So if we have to do that, then again let us take a stack, and don't think just because I'm taking a stack I'm going to do recursion. Stack will help you in actually taking things in the principle of stack, which is your first in last out, and that is what we will try to capitalize here. So let us take a dummy tree for that matter, and we will do that as an example. We will take A, let us take it in a different color, A, B, C, D, E, and then let me take this here, right? So let us say this is our tree and we want to do a non-recursive traversal of this tree to get the in order. What is the in order of this tree? If you see, the in order of this tree will come to D, B, E, A, C, F. This is the in order. Now our job is to actually do this in order, but without using recursion, using this stack. So let us try to do that. The rule is go left till you reach null. Go left till you reach null. From the root, go left till you reach null. Left, left, left till you reach null. I have reached null here. Every time I was going left, I was actually pushing the data into the stack. So I was pushing here A into the stack. I was pushing here B into the stack. Then I was pushing C into the stack. So these are the data that I was pushing into the stack. A, B, D, sorry, not C, A, B, D. So these are the data that I was pushing into the stack. Now because I encountered a null here, right, I will now start, for every null, I will pop out one element from the stack. So I have popped out D, then I go to the right of this, we will have to go to both the childs of it, and there I get one more null, right? So I pop out B. So I will pop out B from there. Next I will go to the top. I'll go to the top. This B is already visited. So I'll go to the right because I have to take, once the left is done, I'll have to go to the right. So I'm going to the right of the B subtree, and for the B subtree right, I get to see E. If I get to see something, I will push it into the stack. If I get to see something, I will push it into the stack. And now what we will do is, we will go to the left of E, we will get null. Because we went to the left of E and got null, we can pop out one item. I said, if you get null, pop out an item. E to the right also has a null. Pop out one more item. Go up now. Go up, B is done. A was already done. So now you are visiting the right subtree of A. So you are going here, C. So C you are visiting first. So you will take it inside. Right? So C you have taken inside. And then you go to the left of C, because I told you have to always go left, left, left. Right? Here you could not, this was itself a right subtree start for you. So in this right subtree start, you started with the root, which is C. And from the C you are moving left. You got a null. You got a null means pop this out. So pop this out. Go to the right. Go to the right. You visit F. You visit F means F has to go inside the stack. Right? And then, because on the left side of F, again go left, right? So and left side of F has null. So pop this out. So that completes your non-recursive style of getting the same in-order traversal using a non-recursive style of the tree. I hope this is clear, and it's very simple. Again, I'll repeat, go left, 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 left. Whatever you visit, put it into the stack. And then start taking left, right, left, right. Whenever you get a left and right, or left or right, or any combination of that as null, start popping out items. That will give you the in-order sequence. So with that, we are exact on time, which is half an hour we said, which is what we completed. Let us start with the quiz. Before starting with the quiz, let me see. Okay. Tonmoy and Ghost Coder, you are requesting for whatever we are doing it in the OneNote. I will share the OneNote OneDrive link. I think in the beginning of yesterday's session, there was a memory issue for which the first few, I think 10-15 slides will not have the handwritten notes. The rest is already there. It will come to you as a OneDrive link. Quiz time, guys. Open your phones. Okay, so window capture off. We are in the live stream. Okay. So we are on trees, and we are using the quiz now. One minute, it has logged me out. I need to log back in. Suddenly something happens with this site. Crazy. Okay, so I will have to log back in. So let me go there. Here. Yeah, see, it has logged me out. Okay, so we are doing binary search tree. No, sorry, not binary search tree. Tree. Carry on. Chalo, quickly. $112, so we'll stop at 100. 6 more of you. Four more, come on. Okay, let's start off. Easiest question. Good, 75. Audindam, Gitika, Sohan. Mostly new, but yes, I've seen you earlier also. But good. Next question. We did it just now. Don't get it wrong. $68. What happened? Anish, Pratyush, Shayon. Leaderboard changed. 10 of you answered I-1. Where I-1 is coming, I don't know. You could have been confused with 2i, 2i plus 1, that I understand. But okay, let's move on. Shayan Pratyush, wrong shit. What's happening? Why this problem? Children are unordered. General tree differs from binary tree. That means they are talking about the general tree, not the binary tree. Right? So general tree cannot be having always two children. General tree, I told you, can have infinite children. Right? So general tree differs by having infinite children, or general tree will have the children in an unordered manner. Binary tree has to have the children in an ordered manner. So the unordered manner is the right answer. 30 of you, I think you confused yourself with answering about binary tree. They didn't ask about binary tree. General tree differs from binary tree. So it's asking about general tree. Still okay, but you should have got this correct, every one of you. Postfix means root is at the right. Just now we did such a big sum. The root is at the rightmost portion. Plus means the root operator is plus. Why did somebody think G? You missed the plus, is it? This entire expression does not mean that plus or minus or star has to be eliminated from this and then you see who is at the right. Everybody is a part of the tree. So plus could be the root, G could be the root, F could be the root, minus could be the root. So don't eliminate plus and star and then say G is to the right. That is probably something that you had done. Ending 71. Good. That means most of you would have answered with 0. Yes, 0 or 2. That's the answer. Ending the assignment. Let's see. Gitika, Pratyush, Shayan. Shayan, how come you become first every time? 0A. Now you have started with 0A. But Gitika is small case. Okay, we have a class accuracy of 62. That's okay. Let's move on. Let me see the chat window before I move on. Farhan, you press dot instead of 0. Okay, Farhan. That's okay. This happens. We will now start quickly. What do we have to start? BST. Okay. So BST means, oh no, threaded. After threaded, I think BST will be there. So when we talk about threaded binary tree, then this is a very new, this tree normally doesn't get discussed that often because this is typically used in operating systems. for optimizations of disk, and I'll tell you how it is used. So be attentive because this might be new for some of you. You might not have even heard about it. So from a TBT perspective, why do we need it? The reason of why we need it is that you just now saw that in order traversal we need a stack or recursion. Either ways, we have done both. We have done recursive method of solving in order. We have also done a stack method of solving in order. So these are the two things which we need, and both of them are costly. Recursion is costly. We have explained many a times how memory is being taken, how memory is locked. Yesterday also I explained, right? And stack, definitely you need one more memory to actually store, which is also costly, both in terms of time and in terms of space, right? If you have extra space needed, then of course you are going to do something with that space. That means you'll use CPU. That means you'll take more time, right? So that's why we have a problem when we say that in order traversal needs a stack or a recursion. And we will see how we can actually say that many pointers are actually wasted in a particular tree. Now let us see the wastage of pointers, and that's going to be interesting. So if I say that I have a tree which is like this, and I'm using what? I'm using a double-ended linked list which has a previous and a next, right? And these two pointers in order to create this tree. So when I say that, let us say A I have kept here, and then I'm using the next node. Let us assume that the next node is here, which is my B. And then let us say that we have another node here, which I will call later. I don't know what number I will give. So let me finish the tree and then I'll write the numbers. Then we will have one more tree which is to the left of this tree. And there will be one more tree to the right of this tree. One more node to the right of this parent node. And we will have one more node to the right of this node. So what we will now do is we will now integrate these through the edges. So the previous will point to the, this is my previous, right? This is my previous position. This previous will point to the actual tree. So this is how we are using a linked list, which is a double linked list, to implement a tree. We are not talking TBT right now. We are just saying linked list lelo, double-ended linked list, create a tree. That's what we are doing here. Then this left pointer will be pointing here. So this is called, let's say, C. Then this B will be pointing here. So this is called, let's say, so this is C, and this is called D, and then this is called E, and this E will be linked with the right pointer, and here also with the right pointer it will be linked. So this will be F. Now if you see these trees, then you will understand that we are wasting a lot of pointers. The previous pointer and the next pointer is what I am talking about. Each node has a previous pointer and a next pointer, right? Now we have, let's say, n nodes. Let's assume we have n nodes. What's happening? 1 minute, guys. Something is wrong. One node has stopped responding. 1 minute. It will open up. I need to see you are having to see this visibility. Yeah. Okay, so where is this gone? This is gone here. Yeah, so what I was saying is that we have n nodes here, let us say n here in this case, if we have the total number of nodes represented as n, right, then we can say that total number of pointers, each node has 2 pointers. So 2n will be my total number of pointers. What are these pointers? These are the standard pointers of your linked list previous and linked list next for every node. We have talked about this, that previous and next pointers will be the double linked list that we talked about, right? So in the morning. So double linked list will have 2 pointers, one previous, one next, and 2n will be the total number of pointers in this tree. Right now, if you see that the total number of actually used pointers is going to be n minus 1. So how do I say that? See, I have used this pointer. I have used this pointer. When I say used, it is being used to point to a node. That means that pointer is getting some value. So when I say that, it means that I have used this pointer, I have used this pointer, I have used this pointer, but I have not used this pointer, this pointer, this pointer, and this pointer, and so also these. How many pointers have I used? 1, 2, 3, 4, 5. So I have used 5 total used pointers. So if I have used 5 pointers, then what is 5? Count the number of edges in this tree. It is 5. So number of pointers that I am using is equal to the number of edges, which is equal to my n minus 1. So the total number of used pointers is actually n minus 1. So then the total number of null pointers will be what? 2n is my total number of pointers, and 2n is actually what? N minus 1 plus n plus 1. Sorry, n minus 1 is my 1 minute. So 2n is my total number of pointers, and 2n is equal to my n minus 1, which means that the total number of null pointers will be some variable I will take. Let's take this as some variable, let's say x. Now this x is the total number of these x pointers, right? So can I say the total number of pointers in this tree, total number of used pointers plus total number of unused pointers? Then what is x? X is equal to 2n minus n minus 1, which stands as n plus 1. So now think x equal to n plus 1. What is the total number of nodes? 1, 2, 3, 4, 5, 6. 6 nodes means n plus 1 is how much? N plus 1 is 7. So 7 pointers are wasted in a 6 node system. So out of 12 pointers, 7 pointers are wasted, 50% pointers are wasted. They are not used at all. And that is the biggest problem, right? Not only are we saying that we need a stack, we need a recursion, we are also saying that we will waste whatever you give to me. That is not acceptable. So this is how this problem statement has come. This is how we are saying that we need a solution to this problem statement. Now when we say we need a solution to the problem statement, then let me take this tree to the next slide. Then I don't need to draw it again. Okay, so if I take it to the next slide, now what is the thought process, or what is the wish list then? The wish list is that so now the wish list is that if we just bear with me, I'm just trying to align things out because of this copy paste thing. Yeah, so the total number of pointers that are wasted is 7, which we are now aware of, which is fine. So if the total number of pointers are wasted is 7, we now want to say a wish list. Now if I do an in-order traversal of this particular tree, then what am I going to get? In-order traversal of this particular tree, I will be getting C, B, D, A, C, B, D, A, E, F. C, B, D, A, yeah, C, B, D, A, E, F. That is what we will get. Right? So if I get this as my in-order traversal of this tree, then don't you think that when I am standing here, if I am standing at C, if somehow I know my next element, that is my in-order successor, if somehow I know my next element, it would be beneficial. Then I don't need to go and do a recursion. If somehow here only I can get B, then I can directly go to B. I don't need to rely on recursion to go to B. By being here only I can jump. Similarly at B, if somehow I know that my in-order successor, which is D, is available here, right, then I can directly go to D without having to rely on recursion. So what I'm saying is, can the addresses of these elements be present in the nodes before that? And can we use those addresses in these wasted spaces? And that is what TBT will try to do for you. So let us take one at a time. Let us say that at C, if I want to know what my in-order successor, what am I trying to do? I am trying to actually create a way by which I can do an in-order traversal without using any recursion. Right? So then what I will do is, I will say that this particular element C, because this is part of the C node, the right, the next, the prev and next, right? Though both the pointers are there, both pointers are wasted. Before C, is there anybody? Before C, there is nobody. So left side will still be wasted. We can't store anybody's reference there because there is nobody at the left of C. And at the right of C, we have B. So if the right of C has B, then can we say that instead of wasting this, I will take a thread? When I say a thread, because it is not a solid line, because it is reusing that pointer, it is not really pointing to the child, because this is supposed to point to the child and the other way around, it is supposed to point to the parent. We are not talking about the parent thread or the child thread. We are talking about a thread that is actually used to give you the in-order successor. So this is my in-order successor. So in order to distinguish between those two lines, we are saying the in-order successor line will be a thread. So thread means a dotted line, right? So the dotted line is what it points to. That means here it no more contains cross. So here it no more contains cross. It contains a valid pointer. And similarly, these will contain valid pointers, right? So we will put those pointers as we go along now. Now this, if I see now, what is the next available thing? The left of D. The left of D, where do you think it should go? See, the left of D is B. So it should point here, right? So that is what now it points to the in-order predecessor, right? Left of B means in-order predecessor of D. That is your pointing to B. Next, D, the right of D is A, in-order successor. So then this should go like this and point here with a thread. So the pointer should point directly to A. Next we have E, which is, let's see where it is. Achha, E is here. So E has A before it. E has A before it. So from E, I have to point to A, in-order predecessor. F has E before it, in-order predecessor. So F will point to E like this. So what you have created is now a threaded binary tree. And this threaded binary tree, you have created these threads so that you can be anywhere, and from there you can directly actually bring out this expression. Because now you know everything. Now you know everything in this chain, right? So if I now go ahead and see what or how we can actually use this for us to help, then again I will have to take this to a different slide. Let me take this again, because I'll be using this diagram again in the next slide. So let me paste it here. Okay. So now if we talk about this threaded binary tree, then there is a possibility that you might not be using both sides of the pointers to create the thread. You might be using any one. It depends on your business logic. You are free to use any one of the pointers to create the thread, right? There is no hard and fast rule. But one thing that you have to remember, that if you create only one side thread, left side thread or right side thread or both side thread, right? Left side or right side thread, you are creating a single thread. Right side thread and left side thread put together, you are creating a double sided thread, right? So either you are doing a single thread like this, or you are doing a two-way thread like this, whatever we have drawn just now. Now, how does the structure look? The structure says that, and this is where you have to pay a bit more concentration. So what we will have is, we will have two additional variables in our double linked list. So double linked list will have two additional variables in order to accommodate what we want to do. So this is the data portion. So this, let's say, is C. So I'm saying this is this C, right? This C, I'm representing this C as I'm blowing it up and saying that how does the data structure of that particular node look like to me. So the data structure looks like C, which is my data, right? So this is the data portion of it. Next, I will have a left pointer here and a right pointer, because I told you it is a double linked list. So I have a left pointer here, I have a left pointer here, and I also have a right pointer here, and this will point to my left and right nodes. Now these left and right pointers, along with that, have an L thread and a right thread. So a left thread and a right thread, which are Boolean variables. So which are Boolean variables. Now if I put this, if I now see C, what is my left pointer here? My left pointer here is null. So my left pointer here is null. Why is it null? Because you see this pointer is null, because C, after C there are no children, so it is null. And we also understood that the in order expression, C to the left of C there was nothing, right? So we couldn't actually place any thread there. Now to the right of C we have ampersand of B. That is, we are taking the address of B and putting that address to the right of C. So to the right of C, that is here, if you see to the right of C, we have taken a thread to B. That means we have stored the address of B in our C. Here we have stored the address, and that's why I'm storing the address. And this is blowing up like this, right? So that is how you have to interpret this. So the entire thing is blown up. Now, how do I know this is address and not the child? Because you know the same area is being used for child also, and the same area is used for thread also. How do I know? How does the code know that this pointer is a thread or this pointer is a child? And that is why you need this variable, which is a Boolean variable. So you will place 1 here. 1 means it is a thread, and 0 means that it is a child. So the left thread and right thread is there for this particular reason. If we can do one more, let us see one more. Let us take E for that matter. Okay, so let us take E and let's try to draw it. How does E look like in this threaded binary tree? So if I take this, E will be here, right? My E has, to the left we have ampersand A, right? So this is my ampersand A, because E to the left is pointing to A, right? And to the right of E, it is pointing to F. To the right of E, it is pointing to F. And this F pointer that is pointing to F is a zero style pointer. That is, the right thread is actually a real child, whereas the left thread is actually a thread, right? So the left thread boolean variable will be 1, which will say that it actually has a pointer which is a thread, right? So that's how the structure of TBT is actually conceived. I hope you can understand this. Now, if I say that, okay, I have done this structure, then what is the way in which we will draw this particular tree? So what we will do is, we will go to, in fact, this one, let us see what is the time. Do we have some time? I will come back to this. I don't want to unnecessarily delay this because this will take some time. We are already delayed. Now what this was trying to do, in fact, let me see if I can do it. What this was trying to do is, this was trying to tell you that if given, why did you create a TBT? You created a TBT because there was a space issue and there was an issue in terms of in-order traversal taking a stack and in-order traversal taking the recursive route. Then can you do an in-order of this by creating a TBT out of it? Can we do an in-order of this by creating a TBT out of it? That is what this slide was supposed to achieve, right? So if we have to achieve that, then we will have to do the first in-order traversal of this particular tree. It will take some time because we'll have to draw the TBT first and then we will have to do the in-order traversal. And that in-order traversal will be making use of the nodes. So I will see, please remind me. I don't want to miss this, but I'm very cognizant of the time because we are 30 minutes late and this will take at least 15 minutes for me to probably show you. But this is essential because we are doing TBT so that we avoid the recursive nature of doing things. We avoid the stack nature of doing things. The whole point of us to take these additional pointers in our advantage was so that being on one node, we can tell what is the next node. Being on one node, we can tell the next node. And then the entire in-order traversal comes out to us. So it is with that context that we are trying to do. Now for this particular example, we'll first have to draw the normal tree. We'll have to convert it into a TBT and then we will have to do the in-order traversal, which will take some time. So let us go to the commonly asked questions. But remember, if it is asked, I will come to this, by the way. I will still try to make up some time and show you this. But before that, remember one thing, that because I didn't show you this, you are unable to appreciate the fact that yes, we discussed that stacks and recursion are to be avoided. So we created TBT. So the memory is getting reused in a maximum possible manner. Then will in-order traversals not require stack and recursion? No, it will not. But you have not seen that. How does in-order traversal come out from this TBT is what it was exciting to see, but unfortunately I'm unable to show you, but we'll come back. So don't forget that in-order traversal is possible without stacks and recursion by this TBT concept, and I will show you that. So let's move on to the next part of the TBT, whatever is left. What is a threaded binary tree? What are its advantages? You know about it, right? So if we go to this part of the story, this is what I'm talking about. What is a threaded binary tree? What are its advantages? You know about it. Write short notes on threaded binary tree. You can write about it, right? Just draw any sample tree and do the threads. That is it. In an in-order binary tree, right link is replaced by the address of its right link is replaced by the, put it up in the chat window. In an in-order threaded binary tree, the right null link is replaced by the address of its in-order successor, right? Right. The right null link will point to the in-order successor. Right means successor, left means predecessor. right? So in order successor, that's the answer to this problem. Now I'm feeling bad because I'm unable to show you how this why did we start this entire thing, just to get to that in order sequence, right? I wanted to show you that in order sequence. Unfortunately, I'm unable to, but then let's move on. Let us get into the quiz mode and let us quickly finish off and see if we can come back here at a later point in time. Okay, chalo. So threaded binary tree is what we are doing now. Come on. What is our total count right now? 100. Okay, so yeah, we can starting now. Ayush Sriji Bangad 63. What happened? You're not listening. Total number of pointers. One node has previous and next. There are n nodes. That means n multiplied by 2 will be the total number of pointers. I thought everybody will get correct this time. Angat, Srijiv, Ashmita, I'm seeing you first probably. But then n plus 1, n minus 1 might be a confusion, so I will leave it at that because you just heard it and then might have been confused, so I would not be worried about this. happening? Why such low scores in this? 23 in order predecessor. Right child, why predecessor? Every one of you answered successor in the chat window. Now you are saying in order predecessor. Right child is null, means right means successor, left means predecessor. Good. At least now I get to see 85. The threaded pointers help achieve in-order traversal without recursion or stack. Yes. Right. Good. Thank you. Shayon, Bhavya. Bhavya, I seen you for the first time probably in the leaderboard, or yesterday I probably saw you. Yeah, null 84%. Good. Ending the assessment. गीतिका, भाव्या, शायन. शायन तो कुछ किया है, काला जादू किया है शायन ने. Okay, so I am seeing a question from Farhan. Yes, Farhan, you are right. It's an even multiple always, but then size of a structure when you multiply or add that Boolean variable, it demands more memory. Don't get too worked about it, because the structure is never that simple as holding only one integer. No structure in real life will hold only one integer. Right, so it will have more elements, and that Boolean variable will be adjusted by whoever is the technical leader, whoever is that architect. He will adjust that Boolean variable to make sure that the structure memory is not wasted. So don't take the primitive or for lack of better words, don't take the simplistic examples to assume that that's how it will be. %68 performance. This one was a bit better than the last ones. So let's move on quickly to BST, which is our binary search tree. So if we, let me share the screen. Yeah. So if we now talk about a BST, then all of you are aware of it. I will not spend too much time. My left subtree will be less than this particular root, and my right subtree will be greater than this particular root. Right, so that is what a binary search tree says. Any node you take, left subtree will be less and right subtree will be more. Any node you take. So it's not just about the left child, it's about the left subtree altogether. So it is used for generating sorted order, which you already know, that I've already shown you in the tree discussion, that it is used for generating the sorted order for in-order traversals, and we can say that if we do an in-order traversal of a binary search tree, then we will get the sorted output back to us, because we are storing it in a conscious manner that it is sorted, right? And then we are doing the same set of steps as in order does, which mirrors the way it is stored. Left is less, right is more. So that way also we are doing left, root, right, and that's why the in order traversal will be always giving me back with a sorted order for the tree. So that's what this particular table wants to show you, that if you do the in order traversal, how does the sorted order come out. So I'm leaving it for your consumption here. I'm sure you can do an in order traversal of any tree. In the morning we have discussed about it. So if you do an in order traversal of this the way we have discussed, the way you know about it, you will get back a sorted order, and that is guaranteed. That is the property of a binary search tree. So if I now take a BST versus a binary search tree as an example, now for a BST we are saying it's a binary search tree, yes, but for a let's say I take some numbers, let's take some numbers 70, 50, 90 and 10, and let us say that I'm doing a BST out of it. So 70, 50 will be to the left, then 90 is to the right, and then 10 is to the left. This is my BST. So this entire thing is a BST. Now can this tree be represented in any other manner? Yes, it can be. If I say 90 and then I say if I say 90 and then I let's say 70 and then I go to the right, 70, 50 and then 10. What is this tree? Can anybody tell me what this tree can be called? The right side tree is a binary search tree. What is the left side tree? Yeah, it is a binary tree. No, it's not reverse BST. It is a binary tree, because there's nothing called reverse BST, but a good guess. I never thought that this became reverse of the tree. But yeah, this is a binary tree. This is a simple binary tree. That's all it is. Right? So now we are talking what? We are talking binary search tree and binary tree. So of course, this is a binary search tree. Of course, a binary search tree is a binary tree. But can I say this tree is a binary search tree? We cannot say, right? So with this example, you can show that all binary search trees are binary trees, but all binary trees are not binary search trees. So that's the reason why I took this example. Search detection depends on comparing the key node with value when we talk about searching as an operation. So if we talk, we are now getting into the operations of a binary search tree, and in the operations of a binary search tree, we are saying that the when we are actually searching for a particular element, let's search for what is this example? Let's search for 60, right? As a part of this example, 60 is here. So when we will first go to the root, and then we will see the key. What is the key? I told you in the beginning itself, the value that is stored inside a node is called the key. So if the key or in this case the key is not that, right? In this case they are saying key is the target that they are searching. They should not have confusingly used this word. A key, as you saw in the definition earlier, was the value stored in the node. Here they are saying no, key is the search value and the node value is node value, right? So if the key is less than the search value is less than the node value, then go to the left, which we know. If it is greater than the node value, go to the right, which we know. And if the key is equal to the node, then we say found. Now what is that we are searching? 60. So go right. Then we are searching with the key value with 70. 60 is searched with 70. Go left, and then we are comparing this node with the same logic that whether the key is equal to the value. Yes, the key is equal to the value, and therefore you found it. So you had to do how many iterations? You had to do 3 checks, right? So you have to do 3 checks in order to get to that particular element. Now, why 3 checks? First, you are checking here. Second, you are checking here. Third, you are also checking here, right, to ensure that you have reached to your actual element. So first check is go right. This is the first check. Second check is go left. Third check is this. So these are the 3 ifs that will get fired, right? So that's why now if you come here, what is my best case time complexity for this search? Best case is if I'm searching for 50, then I get it as an order of 1, or I would say theta of 1, whatever I want to call it. You already know why I'm saying theta and why not O. I can say O, I can say omega, whatever I want I can say. Why? Because 1 is a well-known complexity class called constant complexity class. Average case of this will be log n, which we have proved earlier. Take all the individual cases and then sum it up, divide it by the total, and then try to see if you can get a relationship. You will get a relationship of 2 to the power h is equal to, or 2 to the power t is equal to 2 to the power k rather will be equal to n, right? So from there you can get k is equal to big O of n by taking log on both sides. And the worst case is for a skewed tree. So if you have a skewed binary tree, right? So if we talked about a skewed binary tree like this, 1 2 3 4 5. So 1 is here, 2 has to be to the right, 3 has to be to the right, 4 has to be to the right, 5 has to be to the right. So this is a skewed binary tree. In a skewed binary tree, what is my worst case? If I want to search for 5, then how many times will I have to compare? 1 2 3 4 5. So I'll have to compare n times for a skewed binary tree. So that's my worst case. So this is on binary search tree in terms of searching. In terms of insertion, it is easy. So we will just see where we want to insert, and accordingly we will insert it. So if we want to insert, let's say 48 suppose was not here, then first we will come to the root. We will see 48 is less than 87. We will come here. We will see 48 is greater than 36. So we will take the right part. Then we will see 48 is less than 56. So we will come here, and then we will create this node and add it here. So that is the insertion part of the story of BST. The deletion part of the story of BST is where we are saying that 3 cases. First case is if we are deleting 80 which does not have any children. So if this does not have any children, just free this. Just free this node and make this 70 equal to null. 70 point to null. That's all you will do. So 70, the right pointer of 70 will become null, and this particular node that you had will become free. Those are the only 2 things that you will have to do for case 1. For case 2, what you have to do is, if there is a child, if I want to delete 60 which has 1 child, that is case 2. That has 1 child, not 2 child. 2 child is case 3. If it has 1 child, then it is as simple as removing this and putting this here, which means my new node will look like this. New tree will look like this. 50, 30, 70, 55. So I just have to move this 70's next pointer to 55. 70's next pointer was pointing to 60. All I need to do is move 70's next pointer to 55 and delete 60. That is free 60. That's all I need to do. So that is how you delete with 1 child. Now if you have 2 children for a particular node, let's say that we have this 70, and this 70 I want to delete. Now there are 2 children. Now I know that if there was 1 children it was easy, but with 2 children, which one will come up? Somebody has to come up, right? So which one will come up? I hope you understand why somebody has to come up. Here somebody came up. See the children of this 60, 1 children was there. It came up to replace the parent. It came up to replace the parent, right? So that's the normal logic. But here we have 2 children. Who will replace and who will become the king? That is what we want to find out. So in order to find out that, what we need to understand is that let us take a bigger example, then I think it will be clearer. Let us say I'll take the same example and I'll elaborate it. Let's say I'll take this as 30, then I will take this as 70, or let's say I will take this as 69. Right? Let me take this as 69. I'll take this left side as 60. Then I will take 55, let's say on this side, 62 on this side, then 80 on this side, and 75 on this side, 85 on this side, and finally we will let's say 82 and 90. So all of these nodes are arranged in a proper order, with the left subtree being greater than the right subtree. Now we want to delete, let's say 69. So I want to delete this record. Now what will I do? How will I move, or how will I decide which needs to go up? Right? So there is what you need to consider, that you can have two options. One is you can take the in order successor of the left subtree to actually do this. That means the smallest in the right subtree, where what is a successor? Successor, we already have done a lot of questions on it. A successor is the right subtree, right? Or resides on the right subtree, resides on the right, right? So the successor, the right subtree is the successor. The successor subtree, right? 69's successor subtree is the right subtree. So what we will say is, we will take the minimum from this and move it to the top. From this entire successor of this after 69, we will take the minimum. Who is the minimum? 75. So this will be replaced with 75, and 75 will be removed from here. So 75 will be removed from here. So that way, if you now see whether it is balanced, not balanced, the BST still holds BST or not. It still holds. See, 30, 50, 75, all nodes to the left of 75 is less than 75. All nodes to the right of 75 is more than 75. And that is exactly why you took minimum, so that everybody can be greater. When I put that minimum percent here, then everybody will be greater than that, and then we will not have any problem. This is one way. Another way is you don't do on the right side, you take on the left side, and you take only the maximum from here, right? So instead of 75, what will come is 62, and this 62 will go away, right? So to the left of 62, I can see that we have 60 and 55. To the right of 61 or 62 rather, to the right of 62, we can see 80, 85, 92, 90. So there also my binary search tree concept is getting preserved. So this is the deletion algorithm for your having more than one children. Now I have not taken a simplistic example like this, where the children was the next level itself. I have given you the example where we are talking about a subtree. The entire subtree will have to be selected from there. So it's not about just checking the immediate children, right? So it's about the subtree. So that's on this. Now yeah, now this is a question that somebody was asking probably, and what we will try to do is, I'll try to tell you what to do here. It says that there is given a pre-order 40, 20, 10, 30, 60, 50, 70. They have given this pre-order. Pre-order means this is my route, and they are saying, give me the binary search tree. Give me the binary search tree for that. So I need at least the in order. You know that to draw a tree, we need pre-order, in order, post-order, in order. We have done that just now, right? So I need pre-order and in order. Pre-order will give me the root, in order will tell me the left and right subtree. Where is the in order? There is no in order. They have not given you in order, but they have said binary search tree. So binary search trees in order is what? The sorted expression. So let's sort that expression. That will be the in order, na? So then 10, 20, 30, 40, 50, 60 and 70 will be the in order. We know that. So you are deriving the in order. Now you are good. Now can you draw the tree? Yes, you can draw the tree. We have done that. Right? So this is how this particular problem. Be careful. You will be given BST. Find the word BST. Just don't say question is wrong because just pre-order is given. Question is not wrong. BST is given. So bring in order. Do the in order. BST, you know, in order traversal will give sorted tree. Sort it. Then you are good. Right? So that's how you will do this. Now they are saying insert the following in the search order. So this is a classical problem that sometimes comes in various varieties. So we will say that we will start with 87 and whenever we get an element, we will see whether it goes to the left or whether it goes to the right. So 36 goes to the left, 22 is less than 36. So 22 will go to the left, 15 is less than 22. So 15 will go here and 56 is to the left of 87 but to the right of 36. So 56 is here. And then 85 is to the right of 56 and then 48 is less than 87. 48 is to the right of 36 but to the left of 56. This is my 48. 91 definitely to the right of 87. 72 is less than 87 but 72 is greater than 36. 72 is greater than 56. 72 is less than 85. So 72 will go here, right? And then the final thing is 6. So 6 will go here. So this is your tree. This is the first thing they have asked. Draw the resultant tree. Then delete 48. 48 is a person without any children. Delete directly. Case 1, right? Then delete 15. 15 is a person with one child. Delete and move the child forward. So this now becomes 6. And that's your resultant answer. So I hope it is understandable. Write a C function. Now who the hell actually says C function in a DSA class? I really don't understand these guys. They want you to write a code for an algorithm. Anyway, so if you have to write a code for an algorithm, so be it. We will also write it. They want you to find the minimum and maximum element from this particular section. Okay, minimum and maximum element in a binary search tree. So a binary search tree, if we have to do that, then as I said, in a binary search tree, what have we taken? We have taken a methodology in which we are saying that we will take a double-ended linked list. So we will do this: struct node int data, and we have taken let's say the left and the right pointers, which is our struct node star left and star right. These are the left and right pointers we have taken. So what have we achieved here? We have achieved in creating a double-ended linked list which can now represent the tree. And we will now say the function that we will write is find minimum maximum. One function, or let's keep it separate just to make sure that you don't get confused. You can do two functions, one find minimum, another find maximum. And here you will have to pass the root of this particular tree, because everything starts from the root. So you will pass struct node star root. and there we will say that if my root is equal to null, so we'll do a null check first. If my root is equal to null, then I will do what? I will print that the tree is empty and I will return null. So print empty tree and then I will return null. So I'm not doing it exactly syntactically as C. I hope you can understand. In a hurriedly I'm trying to write it. Then what I will do is I will write a loop, because now I want to I got a proper tree because root is not null. So then I will go root left, because if I go to the leftmost portion of a tree, let us take a tree, okay, let us take a tree, then it will be easier. 30, 5, 7, 90, 10. If I draw the BST of this, it will look like 30, 5, 7, 90 and 10. 10 will be less than 30, 10 is greater than 5, 10 is greater than 7. So 10 comes here. Right. Now, can you tell me which is the or where is the smallest element? The smallest element is here. How do we reach here? From the root, go left till you find null. That is your smallest element. And from the root, go right till you find null, and that is your largest element. That's the beauty of a binary search tree. Right? So leftmost element will be the smallest, rightmost element will be the largest. That is how you get sorted order when you do an in-order traversal. Leftmost will be less, rightmost will be large. So if I say that I will run a while loop here till, let's say, root left is not equal to none. So I will keep on moving left till my root left is not null. I'll keep on moving left till my root left is not null. And that is what I will do. What I will do, I will say that, okay, I will move root to root left. That is what I will do. And that's it. So when I have come here, what do I have? I have reached null. That means my leftmost is my smallest element. So I will return that smallest element. I will return root arrow data. That is all I will do. So this is your algorithm for minimum. The maximum, what you will do? Maximum, same thing you will do. Instead of left here, you will go right. That's all. These are the two changes you will actually do. Everything else remains the same. Right? So you will go right till you reach null. Wherever you have reached, that data is your maximum. Return that data. That is what we have done here. Okay, so what else is left? Let us see on this particular topic. The value of in a BST can be sorted in ascending order by which traversal? In order. We have been discussing this so many times. It's a very popular question. All binary search trees are binary trees. All binary trees are not binary trees. Binary search trees. We have discussed that also. Worst case time complexity to access a search element in a binary search tree. Worst case time complexity. Now worst case time complexity we have already discussed. In a skewed binary tree, binary search tree, it will be order of n. So it will be like this. This is my worst case. So it will have to go through all the elements to actually reach this element. So that means it is order of n. So that's on BST. So we start off with AVL after this quiz. And let me see the chat window. Any fun is happening? Binary tree, reverse binary tree, complete binary tree, skewed binary tree, linked list, convert into in order. Okay, good. Left child, order of n. Good. Okay. So we will now start the quiz. Let me switch the window. Chalo. Come. Nine. What happened? Attendance has dropped. Okay, we'll start. Come on guys, if BST you don't know, then it's very difficult. Left is less than right, left is less than root is less than right. Suddenly how come left became greater than root? For 22 people. Okay, this at least is decent. Next question. Okay, good. Okay, fine. Next question. 63. Yeah, good. At least it was a confusing question, but you have answered 63% of yours, which is okay. Let's move to the last question. I gave so many hints, still 51. Shanik Barui, I'm seeing your name for the first time. Good. 51. Sorting, arrange. How can arrange? Okay, you. I understand. So you didn't remember the word sorting, but understood that you have to arrange it, right? So which is okay. At least concept is there. Sorting. Ordering. Yeah, okay, good. At least concept is there. Let's see who is the winner list. Shanik, Upasana, Shayan again. Kya kala jadoo kiya Shayan tune? How come? You have some backdoor with this wayground.com or this.com. I'm sure you're paying them money. Guys, dislodge Shayan. What is this? He will definitely eat away all your goodies. Okay, chalo. We will do AVL tree, and then I desperately need a break. My throat is gone again. So I will take a break and then come back. Okay, so now we need to stop this. Yeah. So AVL tree is named after three gentlemen, Adelson, Waleski and Landis tree. In fact, not three gentlemen, one gentleman, Adelson, Waleski and Landis tree. In an AVL tree, only two conditions we need to be careful about. One, the tree is a binary search tree. And two, the height of the left subtree minus the height of the right subtree for any node that you take should be between -1, 0 and 1. So the difference of the height of the left subtree and the right subtree will be an element of the set -1, 0 and 1. So these are the two things that you need to remember. One, it is a BST, right? It is a BST. And second is this condition. So this is my first condition. This is my second condition. In fact, it was written here. It's already here, right? I missed this. This is the first condition. It should be a BST. Now, if you see what I have given here on the left side, I've given you 4 important cases that you need to consider when you are actually doing this kind of a rotation or adjustment in a AVL tree, which we will just see just now. Before doing that, let us see the rules, right? So it's not easy to construct an AVL tree without these rules. So what we will do is, we will say that if suppose I have x less than y less than z, in that case, can I say that my BST that I will draw will be looking like this? X less than Y less than Z. This is my BST, right? But is this AVL? This is not AVL. Why? Because if you see Z and calculate what is its height on the left side, you will see that there are two edges. Height is 2 on the left side. On the right side, the height is 0. Therefore, this has a balance factor of 2. This is called a balance factor. The height minus the height is called a balance factor. So if this has a balance factor of 2, then it's definitely not a part of -1, 0, +1. That means it is not an AVL tree. Why did you reach this problem? Because you did a left. Both the units were left. So that's why the case is called left. So when the case is called left, do the ulta. Ulta means if your letters are the same. If your letters are the same, do the ulta rotation. Do the right rotation. Do the left rotation here. So where will I rotate it from? I will rotate it from here, from the top. So when I rotate, what does that mean? It means that Z will be pulled down and Y will go up. That is what this rotation means. Z will be pulled down and Y will be pulled up. That is what the clockwise rotation means. So in that case, our new converted after rotation tree will look like this. Z is pulled down, Y is pulled up, and X is there wherever it was. So this now becomes an AVL. Why? Because Y has left node 1, right node 1. 1 minus 1 is 0. So the balance factor is 0. This has left child 0, right child 0. So 0 minus 0 is 0. This has left child 0, right child 0. That is also 0 minus 0, 0. All the nodes are balanced. Right? So that is on the AVL, this particular case. So don't forget, if you have a left, then do a right rotation from the top. If you have a right situation, let us say that Z is less than Y is less than X. Then we will write it like this: Z, Y, X. So of course Z will be unbalanced. I am not going there. By the previous example, you understand now how to calculate. Z will be unbalanced. So to balance Z, why did this imbalance arise? Because we did a right. Right imbalance means both letters are the same. Do the ulta. Okay, if you do the ulta, what does that mean? It means pull Z down and push Y up. Pull Z down and push Y up. That is what it means. Right? So then the resultant tree will look like Y, Z, X. That is on the RR portion of it. Next, and that tree that we got was balanced. Now if we have a situation where we have Y is less than X is less than Z, then we will have to take Z, then Y, and then X. Right? So this is how we will achieve that. Now this tree still is unbalanced because Z is unbalanced. Now if this is the tree, why did we land up in this unbalanced situation? Cause, left movement, and then a right movement. So the cause is a left movement and a right movement. Now these letters are not the same. Letters are not the same, you cannot do ulta. You will have to do, when the letters are not the same, you will have to do 2 rotations. When the letters are not the same, you will have to do 2 rotations. It will not happen with just 1 rotation. The second rotation will be simple. I will tell you the second rotation. But the first rotation will be the same as the letters. So left, right was the problem. So you will do a left, right rotation only. First rotation will be left, the next rotation will be right. And the first rotation you will do from the midpoint, that is between left and right, whichever that point is, that is the point where you will do the rotation. So you will do the rotation like this. That means you are trying to say that X will go up and Y will come down. So then your tree will look like this. X will go up, Y will come down. This is your tree. Now, do you think this is matching with this? Don't you think it is matching with this? So then what does that mean? So you have landed up with a LL problem. If you land up with an LL problem, what do you need to do? You need to right rotate from the top. Right? You need to right rotate. So do a right rotate, and that's why this says that a left right problem has to be addressed with a left problem first. This is the left rotation that you did. And then you can remember that you have to do a right rotation, or whatever you land up actually marries with this. So you know that left needs a right rotation. So do a right rotation. If you do a right rotation, the resultant tree will look like that Z will come down, X will go up. So X has gone up, Y, Z. So this is what will be there. And likewise, the last case, if I solve that, so if I solve that, let us say that Z is less than X is less than Y. In that case, Z is less than X is less than Y will look like this. Right? Now, if that is the case, then what is the problem here? Z is unbalanced. Why did this problem arise? Right, left. So it's a different letter. That means you have to do two rotations. Two rotations are in the same direction of the letters, right and then left. So we will do a right rotation from the middle. So when we do that, then this becomes Z, Y, this becomes X because it comes to the top, and then Y. Now this tree, don't you think is the same as this particular problem? If this is the same problem, then why did this problem arise? This problem arose because we took a right. And right means letters are the same. So letters are the same means you will have to do a left rotation. You will have to do a left rotation. Here there is left rotation. So when you do that, your tree will look like X, Y and Z. Sorry, X, Z and Y. Because X will go up, because you are doing left rotation, X will go up, Z will come down. So that is the rule. Now let us apply this rule on this problem statement. It will be clearer. So okay. We will first insert 12. We'll keep on inserting and creating a binary search tree till we get a problem of imbalance. That is the way to do AVL. So insert 12. So once you insert 12, is there a problem with 12? No, because the left child is 0, right child is 0. There is no problem with 12. Now insert 11. There is a problem with any of the nodes? No, all the nodes are balanced properly. Now insert 13. Is there a problem anywhere? If we insert 13 like this, then there is no problem anywhere. Right? Then insert 10. Now 10 will go where? 10 will go here. So is there a problem anywhere? Let us check. After 10 goes here. Is there a problem anywhere? There is no problem anywhere, because if you see 12 has two edges, which means the height is 2. On the right side, height is 1. That means there is no problem. 2 minus 1 is 1. Perfectly allowed. So there is no problem there. Now the next node we will insert is 9. Now 9 will create an imbalance. 9 will come here and an imbalance gets created at 11. Why? Because at 11, left, that is 2, right is 0, 2 minus 0 is 2, not allowed. So why this problem came? Left. right? So do the ulta. Both letters are the same, do the ulta rotation. So when we do the ulta rotation, what we will have? 12, the left will be 10 because it will come up, 9 will be on the left, 11 will be on the right. Right? So that is what this tree will look like once you have done the rotation. And 13 will remain the way it was earlier. So this is the new tree, revised tree. Now we will take the next element, which is 15. 15 will go where? 15 will go after 13. So for this, did the balance change for 12? No, none of the nodes balance would have changed. You will have to check that. I have checked it. I don't think there is any change of balance. Now we will insert 14. 14 will go to the left of 15. So 14 goes to the left of 15, but my 13 is an imbalance. Why? Because 13 does not have a left child. Right way there are 2. Right? So that's 0 minus 2, minus 2. Minus 2 is not allowed. So you have an imbalance. Why do you have an imbalance? The reason, right, left. So right, left, letters are different. You have to do 2 rotations, one right, one left. And you have to do that right rotation from the middle. So therefore, your new tree will look like this. It will be 12, 10, 9, 11, 13, and we are doing a right rotation. So 14 and 15. So 14 will come up, 15 will go down. So 14 and 15. And now you still have a right problem. Therefore, you will do a left rotation. So this is the left rotation that you are doing. So right one you did, the left one you are doing right now. Why? Because you had started with this right left problem. So you have to do 2 rotations, right and left. So what does the tree look like? We'll again draw the tree. So it will look like 12, 10, 9, 11, then we will have 14, 13 and 15. This is how the tree will look like. So next element that will come in is I think 14 is taken, 18. So when we insert 18, we will insert it here. This 18, does it create any imbalance? I don't think so. There is no imbalance. Now 7 will be inserted to the left of 9. Does it create any imbalance? It doesn't create any imbalance. 6 will be inserted to the left of 7. So 6 gets inserted there. So once 6 gets inserted there, imbalance is noticed at 9. Imbalance is noticed at 9. Why does 9 get an imbalance? Because 9 left side is 2, right side is 0. So this is because of left problem. So do a right rotation. So when we do that rotation, we will get 12, 10. Instead of 9, we will have 7. 6 will go to the left, 9 will go to the right, and then we will have 11 to the right of this, and then we will have 14 here, 13 here, 15 here, and 18 here. So those are the nodes that we will have. What is left out? We are done with 6, so 5 and 4 are left out. So 5 will go below 6. Does it create any imbalance? Yes, it creates an imbalance at 10. It creates an imbalance at 10. So if you see here, because of this 5, 10 gets an imbalance. Left, left, left. So that there are 3 edges on the left side. And there is only 1 edge on the right side. So 3 minus 1 is 2, not allowed. So therefore, you have a problem on the left imbalance. So you'll have to rotate it like this. So if we have to rotate it like that, then our new tree, let me remove some portion of it at least. Let's see if I okay, let me push this to the top, then at least things will be better. Yeah, now we have some space. Let's use that. Okay, so our 12 comes here, our 10 we were rotating from the right, so 7 will go up and 10 will go, 7 will go up and 10 will go down, so 7 that goes up will have 6 on this side and 5 on this side, and the 7 on the right side will have 10 and we'll have, because 10 has come down, then 9 and 11. 9 and 11. So that will be your tree. And then the final thing that will come is 4. So 4, if I take it to the left of this 5, it creates one last imbalance, and that imbalance is on 6. So if you see 6, it's imbalanced because 6 has left, and that is 2 on the left and there is nothing on the right. So 2 minus 0 is 2. So you have a left, and because these two are left, you have to do a right rotation. So if you have to do a right rotation, then this tree now will look like this. So we will now have 12, we will have 7, and we are doing a rotation on the right. So 5 will come up, 6 will go to the right, and 4 will go to the left. 10 will go to the right, 9 will come to the left, 11 will go to the right, and then from 12 you had your original 14, 13, 15, 18. So this, everything is balanced. So that's how you will approach a problem for AVL tree. I hope all the 4 cases are clear, and I hope you can manage this whenever given to you. Typically AVL tree will take 10 minutes for you to probably do it if you are having this large numbers. I had around 12 nodes, so we took around 10 minutes to actually do it. How does an AVL differ from a binary search tree? Now binary search tree, the first difference is all AVLs are binary search tree, but all binary search trees are not AVLs. That's one difference that you can always talk about. Binary search tree, there are no rotations. You know about rotations. One unique feature about AVL is what you have to do is in terms of rotation. You know about the height. You know about here there are no height requirements because you are actually maintaining a height difference between both the ends. Therefore, the worst case in terms of a binary search tree, we had saw that in a skewed tree it was an order of n. But because now you are doing like this, you are trying to maintain both left and right subtrees to be almost equal. That means you are dividing things by half, and therefore log n will be the order that you will almost get. Only if you divide things by half, one part will be almost equal to the other part. That is what we are achieving through an AVL. And of course, the easier to implement, harder to implement, all those things are here. But these are the top 3. Write short notes you can do. Maximum possible height of an AVL tree with 7 nodes. Okay, this is interesting. So, if you have to solve this problem, then the maximum possible height, how do I know that we are talking about an AVL? Let us take 7 nodes. The tree that I can think about with 7 nodes is this. Is this an AVL? Yes, it is an AVL. Left subtree is equal to the right subtree when I see this particular node. If I see this node, my left subtree is equal to right subtree. So that's why similarly the others can also be checked. It is an AVL. But is it the maximum possible height with 7 nodes? Right? So have you taken the advantage of an AVL? AVL gives you an advantage saying that left can be 1 more than the right. Isn't it? AVL gives you that advantage. Left can be 1 more than the right. You have made left and right equal. So if you would not have made left and right equal, what would have happened? Your height would have increased. Right? So that's what it is saying. Maximum possible height. So the height would have increased for an AVL tree if you take this advantage. Right? This advantage. You are not taking that. So that is why you are supposed to take that. So how can you take that? You will reach, let's say, this kind of a problem where if you take those 7 nodes and arrange it in this manner, you will get to an AVL tree. 1, 2, 3, 4, 5, 6, 7. So see, we have 7 nodes and see that every node is balanced. What is the height of this? 1, 2, 3, 4. 4 is the height of this AVL tree of 7 nodes. 4 is my answer. Right? But how do you find it? How do you find it? Is it so easy to interpret that I will probably draw this and say 4 is there? It will take so much time for me to imagine. I know the answer, that's why I am giving it to you. It will take so much time for you to imagine, and sometimes you may not be imagining that you can get this kind of a answer with 7 nodes. So the height of an AVL tree has a formula, and that formula is that, and this is a recursive expression, so please be watchful. Height of an AVL tree is nh minus 1 plus nh minus 2 plus nh minus 2 plus 1. This is the formula. In cases of and the basic assumption is that your n1 is equal to 1 and n2 is equal to 2. Now what is the right hand side? That is the height. What is the left hand side? That is the total number of nodes. Right? So that is what it is. Now if I give you saying that height is 3, then n3 will be equal to n3 minus 1, which is n2, plus n2 minus 2. Sorry, 3 minus 2, which is 1 plus 1. Now what is n2? I have already written n2 is 2. Right? So 2 plus 1 plus 1, which is equal to 4. That is how we get 4. Right? So that is how we get 4 from a height which is 3. Then we get 4 as the total number of nodes. In fact, total, sorry, my bad. 4 is the total height from a tree where we are talking about the actual h equal to 3. If we take h equal to 3, then we will get 4 as my total height of the AVL tree. So if we take a height of, let's say I will take the next height. So I will take n equal to 4. So if I take this, then I get n3 plus n2 plus 1. So n3 I have already calculated as 4, and then I have calculated n2 as 2 and this as 1. So 7 will be the height of my AVL tree. So that's the height of the AVL tree that I will get. So similarly, I can take n5, n6, and I can substitute from my previous result, because n3 I substituted from the previous result, just like this, right? So this is how I calculate what is my height of the tree with whatever number of nodes that we are given. What is the height of my tree? That is what I will be calculating. So that's on this particular problem. In fact, there was one issue in the earlier thing. That's what I was thinking. So my bad. What you have to interpret here is, there is no issue in terms of the workings. Workings are fine. Only my interpretation was wrong. In this, I said that this is the 4 that we were looking for. This is not the 4 we were looking for, because this right hand side is not the 4, because it talks about n3. n3 itself means number of nodes. So this is talking about this 7. So right hand side is talking about this 7. To get 7, what do you put here? 4. That 4 is this 4. So my apologies for that. On the right side, seeing 4, I myself got confused. So it's not that, because you are creating n. A value of n is the total number of nodes. Total number of nodes is on the right side, right? So that total number of nodes is 7 for h equal to 4. We have substituted h equal to 4 here. And this is how you will calculate when given this. You will never be able to probably imagine this. So let us see what is next. Okay, we are done with this. Now we'll do a quiz, and then we will take a break again and come back on the other side. What is the time? 4:20. So we have 1.5 hours and we have to do 2 trees. It will be done. So let's complete this now. Camera off. One minute, guys, I'm trying to fix the camera. Video. Give me 30 seconds and then we'll start the quiz. Okay, let's start the quiz. I'll figure out the camera. So we are now at AVL tree. I hope I have shared my screen. Yes, okay. Yeah, login. start at 85. $70. 10 more. Okay, let's start off. Abhay, first time Abhay, thank you for being in the leaderboard and not losing patience. Left subtree less than right. Okay, yeah, 70%, that's good. Let's move on. Pratyush Arindam Angad, 77. Okay, so looks like you guys know AVL tree better. Nice, good. Meghna is still at the leader, good. $84, very good. But the leaderboard keeps on changing. I don't know why. Which is okay, good. Lumshit, Pratyush, Arindam. 91%. I think I made this quiz very easy. Okay, let's end it and see. Arindam, Pratyush, Rumshit. Good. New names. Shayon, what happened? Everybody else is doing Kala Jadoo against you. Okay, so I see that some people had some confusion. So Tanmoy, you had a confusion. So more than 2 will create problem. So we have to rotate while it is more than 2. Yes, more than 2 creates a problem. It has to be -1, 0 or 1. More than 2 will create a problem. So you will have to rotate till every node is within -1, 0 or 1. So that's the answer. Farhan says the root is not balanced. Farhan, which one? This last one that we did. 1 minute, let me see. So you are talking about this one. So are we talking about this 12 not being balanced? This 12 not being balanced, the root not being balanced is what you said. So I have 1, 2, 3. And on the right I have 1, 2, 3. So it is balanced, right, Farhan? I'm not understanding which tree you are talking about. The next question, okay? The next question. Which question? This one. Yes, you're right. You are right. The root here is of course not balanced. The root here is of course not balanced. If we draw the root like this, then this will of course not be balanced. That's something that I did not see, but the answer still will come as 4 will be the height. So this particular tree, though it has 4 as the height, then it's still not an AVL tree. So you may have to do some rotations in order to get to there. But if you do some rotations, your height might change. Needless to say, irrespective, because this is something you will never know, right? So don't worry about that. Yes, I understand that the root is not balanced. So I also didn't get this from my head. Whatever sources gave me that is a wrong source. I will correct that. But I will probably do it with this formula. So this formula will still give me that with 7 as my total nodes, I will still get 4 as my height of an AVL tree. Now what that AVL tree is, we'll have to figure that out. Nobody will ask you to draw that. Tanmoy says, got it. Sir, what to do for 2 same numbers in AVL or BST? It will not come. Why do you get so pedantic about silly things? 2 same numbers in AVL and BST will not come. If it comes, put it in any one of the areas, left or right. Doesn't matter. Please provide lectures, recorded lectures. Recorded lectures, Poonam, I have already told you what is the stance. If I had to provide recorded lectures, I would not have taken a live session like this. My channel is anyway there. You can go there and see the recorded lectures. I might decide to give the recorded lectures at the very end towards the time of your examination so that you can view those. But it will be also useful for you to see all the detailed lectures which are available in YouTube. If you want a quick shot like this marathon, we will see. I mean, I will have to see and I will have to check with the relevant people who are coordinating this, whether a decision was taken that this will never go recorded to you. But I will see. If before the night, now no, but before the exams, whether we can provide it for your revision, I will check that. Random flick says आप सर आप दिन में कितने देर तक, then nothing, कितने देर तक क्या, कितने देर तक मस्ती करता हूँ, कितने देर तक रोता हूँ, कितने देर तक खाता हूँ, कितने देर तक. So please put a proper this thing. Yes, written PDF I will provide. I told that at the beginning of this call. I will provide written PDF. Yes, I will provide it after the session is done, Poonam. After the session of tomorrow is done, the entire PDF I will provide you. Now, we will take a break because I cannot speak. You can see that my voice has gone down. Give me 10 minutes. I will be back. Don't go away. Be here. You also take a break. Let me see if I can grab some hot water. And I will be back. So give me 10 minutes break. Okay guys, we are back. 20 of you have left. I don't know whether they will be back or not, but we'll start off. Can you confirm all of you are there? Just say okay, okay, yes, okay, whatever you want. Then I'll start. Fine, let's get started. So we have two more trees. We have 1 hour and 10 minutes. Let's see how much we can complete. If you think about the threaded binary tree, right? I forgot to mention one thing. In the threaded binary tree, one of the things that I missed telling you is the use of that threaded binary tree. So if you see the threaded binary tree use, then you will see that the threaded binary tree use is mostly in cases where you will have to do a lot of in-order traversals, where you will have to save around the recursion cost. Typically where your space is less, memory is less, but you'll have to perform large computations, large storage. That is where you will start using a threaded binary tree. Now B tree similarly will have some use, B plus tree will have some use. Both those uses I will tell you. So these three uses of these extra trees, I would so call it for lack of better words: threaded binary tree, B tree and B plus tree. Please remember the uses of that. I've told you threaded binary tree, B tree I will tell you. Before telling you, I will have to explain to you what a B tree is. Now, it already says where the B tree is going to be used. It is going to be used in disk-based storage and large data sets. Why? I will tell you. In a binary tree, what do we do? In a binary tree, we simply land up by saying that we will have data like this. How much of data can we get from this node? How much of data can we get from this node? 1 unit of data. Right? Whatever is there in my data structure, the structure that I have defined, the double-ended linked list, I can get that amount of data. Now suppose I wanted all of this data in one node. All the data I want in one node. I don't want the relationship. I want all the data in one node. And there will be relationship. So I will say that instead of a single data, I would want to have all my data in one node, and then I can start talking about creating trees from that node. So if I say like this, let's say I had let me remove this. Now imagine one node in a double linked list that looks like this. This is what it looks like. So imagine you have put K1 there, which is a key element. We know that inside a node resides a key. That is the data that we talk about. So then there can be another element which is also a key, that is K2, and these two can be linked like this. Similarly, this can be linked in this side by this. So we are creating what? We are creating a tree using a double linked list. So that is no rocket science, you know by now how to do it. Now I am saying, can we push this inside here, as well as this here, as well as this here, and this entire thing now becomes one single node for us, which has multiple keys. The basic definition of node was it has keys. Now we are saying multiple keys, right? Yes, we can, and that's why we have B tree. All these keys will be part of my B tree node, right? So all these chota wala keys will be part of my B tree node. So what will happen is I can actually draw the B tree like this, saying that this is my overall way in which I want one node to look like, right? So one node is quite large because it has to accommodate so many smaller nodes, right? I told you, right? It is going to accommodate nodes. Then this can I say that this is that smaller key that it is accommodating, which is your K1, right? So this is going to be my K1, and this is your the right part of or the next part of that particular node. So that K1 is here. Can I say that there is one K2 here which has this, which is the right part of K2? So where is the left part of K2? I am taking help of this only. So this is also the left part of K2 as well as the right part of K1. The right pointer and the left pointer. The pref pointer of K2 and the K1's next pointer are the same. I hope you can understand what I am trying to get at. Can I say then I can keep one more element just like this, where I will say that this is my K3, and I will have let's say this will be becoming my right part and that becoming my left part. So K3 has some left part, K3 has some right part. The left part of K3 is borrowed from the right part of K2. So right part of K2 and left part of K3 are the same. And the last node, if I say, let me draw it like this and I will wipe off. So let's say I will take with 4 keys, and that 4 keys I have drawn like this. So this is my K4, right? So this is my K4. Now I have a left part, right part of everywhere. So now if you see this, there is something called as order for a B tree. Now order, if it is 5, it means that the keys that you can have is 4. So in our case, I have taken max keys as 4. That means in one node, how many such keys can you keep on adding will depend on the order of the B tree. So order of the B tree saying 5 means max I can have 4. I have given those 4 here. I have added those keys here. Now I will, while I have added those keys here, I still need a tree because I broke the tree. K1, K2, K3 were happily there as a tree. I broke it and I said all of you come together to me. But I didn't take everything. I took probably the related items. The rest of the items are still there as a tree. So then this particular K1 will have definitely some child. This particular K1 will definitely have some child. So where will that child go? That child will go pointing from the left pointer of K1, right? So this is how the left pointer of K1 will point to a child which is called as C1, let's say. So we will therefore say that this is C1. Okay, so what is the necessity or necessary condition that should be satisfied here? C1 should be less than K1. That is the necessary condition that should be satisfied here. C1 should be less than K1 because you are at the left child of K1. You are also minded, we are also maintaining binary search tree. So C1 has to be less than K1 because K1 is the we are putting C1 at the left of K1. That means it has to be less than K1. So C1 has to be less than K1. Then we will draw, let's say, this particular element which is C2, and we will say that this child resides here. So when I say this, then don't you think that C2 should be greater than K1 and C2 should be less than K2? Both the things should happen because we are sharing that space, right? So we are saying that because this is to the right of K1, right? So we are at the right of K1. Therefore, C2 should be greater than that of K1, binary search tree. And we are also at the left of K2. So C2 should be less than K2. I hope you are getting this point. This is the most important and the only point that you need to understand here. Now, I can also say that I will have another node which is going to be pointed from here, and that would mean that my C3 is, so this is C3, let me mark this as C3, and that would mean that C3 is greater than K2 and C3 is less than K3. So that would mean that also. And the next thing that we will also make sure that we do is put a node here which will say that C4 is greater than K3 and C4 is less than K4. That is what we will say. And then the last node we will have is here, which will be my C5. So I will say my C5 is greater than K4. So I hope you understand what I did. I said we will take best of both the worlds. We will not allow single nodes. We will say one node will be very big now, and inside that there will be several keys, right? And the maximum number of keys is dependent on the order of the tree. Order of the tree being 5 means maximum number of keys is 4. And the order actually says what is the maximum number of child that you can have. See the number 1 child, number 2 child, and so on and so forth, number 5 child. So how many childs that you are having? Maximum, you are having 5 childs. Where does it come from? Because order is 5, right? So order and child are the same when it comes to maximum. Now that's on this particular concept. Now if you move forward to the next area, so what did we achieve by this? Let's talk about what did we achieve. Instead of going and pulling one K1, we are now pulling K1, K2, K3, K4 all together. So going into a disk, hard disk, and taking some data out from a file across multiple memory pages, instead of going through each individual memory blocks, that's what we are achieving. So we are taking care of going, because IO is always hungry. Any disk IO is very hungry. So if you are going to the disk, make sure you are taking maximum content out. And that maximum content out will only happen if your node contains those data elements. That's why you are putting more keys in the node, while you are still keeping the entire tree structure valid, but you are taking best of both the worlds. Each individual node now is no more one node, one key. It is multiple keys. For that matter, this child could have been multiple keys also, for all you know. I could have put here C11, C12, C13, C14, because one node can have 4 keys maximum. That is why my order is 5. So I can have my children also as having 4 keys. It's not that the root only or the parent only has to have 4 keys. Any node can have 4 keys. I did not take 4 keys just to save time. Otherwise I could have taken 4 keys in the children also. So that way, if you think about it, you will see that you understand the concept that the 4 key concept is applicable to all the nodes, or the m-1 key concept. This is m-1, right? So we are saying that order is equal to m. Then this becomes m-1. So the m-1 concept is applicable to all the trees, right? So the m-1 concept is applicable to all the trees means, all the nodes means everywhere I can actually create multiple data items put together, probably logical blocks of data I can put together, but still maintain a tree structure with other different blocks. Those are also logical blocks of data put together, right? So that's what is a B tree. That's the advantage of B tree, that you get the tree feature plus each individual node, you get so much of data. So that is what is B tree. Now if you understand that, this is a very important table and questions come from this table. So try to understand what it is trying to say. max children we just now discovered is m. For an order of m in a B tree, the maximum children is m, and the maximum keys we have calculated as m minus 1. So if you remember, we had 4 keys and we had 5 children. Right? So 5 children is because our m was equal to 5. Right? So that's what we had. Minimum children is ceiling of m by 2. You cannot just say I will have 1 children minimum. It will be a ceiling of m by 2. So m by 2 is what? M by 2 is 5 by 2. Ceiling of that is what? 3. So I need to have minimum 3 children. Beneath every child, every parent, I need to have 3 children. That is what this is trying to say. And the minimum keys that I need to have is 2. That is ceiling of m by 2 minus 1, which is equal to 3 minus 1, which is equal to 2. So minimum keys that I need to have is 2. And I violated that in the last example, if you see. Right? So for lack of time, I have violated that, because here I have given how many keys? I have given only 1 key. But with m equal to 5, how many keys should I have? I should have m by 2, ceiling of that minus 1, that is 2 keys minimum I need to have everywhere. Here, 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 everywhere I need to have 2 keys. But I have not given that. Right? So I have given that just as an example. You have to increase it to 2 keys in order to make sure that you are following the particular methodology that has been defined. The root minimum keys is 1. For the root node, you can have 1 key. That is allowed. 2 keys are not required. And the root minimum children also, you can have 2 children. And that root minimum children that you are going to do for the root will not follow the normal philosophy of m by 2. It will follow 2 as the minimum children. So it's a hard-coded number. Root minimum children is going to be 2. For 1000 nodes also it is 2. For 2 nodes also it is 2. Now root as a leaf. Root as a leaf. If the root is a leaf, that means after the root nothing is there. Then the root may have 1 to m minus 1 keys. And that is standard, because as you know, you can have 1 key, minimum key here, and your maximum key is m minus 1. So 1 to m minus 1 is your root as leaf number of keys. Total number of keys you can have is 1 to m minus 1. The key order, the keys in each node are sorted. Very important. The keys that we talked about, K1, K2, K3, K4, all these will be sorted from left to right. In whatever order you choose, ascending or descending, it will be sorted. The child rule I have already mentioned. I have drawn this also in the last slide. Leaves at the same level. Leaves will be at the same level. That means when we draw the tree, we will see that leaves are not scattered around. Right? It will not be like this. Like in a normal node, we can have 1 leaf here and 1 leaf here. It will not be like that. So leaf is here, leaf is also here. They are scattered. They are not at the same level. But in a B tree, the leaf will be scattered. Leaf will be at the same level. The rest of the rules we will see later, because unless you understand how to draw the tree, you will not appreciate how to or what that rule is all about. Right? So we will do this example, and this example, if you understand, then that's all that is there in B tree. Then we will do some questions and B tree will be over. Right? So let us do some examples now. We are trying to construct a B tree of order 4. So the order is given to us. So the order means 4 means m is equal to 4. Right? So if m equal to 4, can the chat window type how many keys can I actually have? If m equal to 4, how many keys can I have? Maximum. Okay. Very good. So you are listening. So if m equal to 4, key is equal to m minus 1, which is equal to 3. So I can have maximum 3 keys in my bigger representation of that tree, right? That is what we call as a node now. So what we will do is, we will create an area for 3 keys and we will start insertion one by one. So what first thing we will do is, we will create an area for 3 keys to be stored. That is the maximum that can be there in one node, and we will create it like this. So we will say 34 is here, 34 comes in and goes here, right? 67 then goes there, next number. 89 then goes there, next number. All this while, what are we checking also? We are checking whether the sorting is proper, otherwise we will also need to sort it. 34, 67, 89 is sorted. Be careful, it has to be sorted when it enters into the node. Otherwise, do the swap and enter it into the node. Now 90 will come in. So 90 wants to come in. It does not have a placeholder. Poor guy. It does not have a placeholder because you are crossing the maximum limit of that particular node. So there is an overflow. So if there is an overflow, then you have to calculate the median. Median means you have 34, 67, 89, 90. What is the more or less middle point? More or less middle point you can say is either this or this, because you have even numbers. If it was odd, you would have got pinpointed one number. But because it is even, you can take either of them as the median. You can either take this as the median or you can take this as the median. Right? So you are dividing and getting 2 numbers. One of the numbers you will take if it is even. I am taking 67, and when you take 67, always take the second element in a 4 key as the median. Don't do the same sum by saying in one case 67, in another case 89. Don't do that. If you are taking second position, take second position always. So if 67 is my median, then my median will be promoted to the top. So there will be a promotion that will happen now, and median will be promoted here. So for the promotion, there has to be a placeholder, and that placeholder will be what? Again, it will support only 3 keys only maximum. So minimum will come here and stay here, 67. So median does not, 67 does not feature here anymore. Right? So 57, that does not feature here anymore. Now, if I take from the right part of it, we have split it also. Remember, we have also split it. I forgot to tell you that at the median point, we are splitting it. That means this entire portion is going to separately go into a separate section. That means we will create one more section for this 89 and 90. So we will create 89 here, 90 here, and the rest we will keep blank. This 90 now has found a placeholder, and this does not exist, and now we have created what we wanted to create. One of them we have moved to the top, and on the left now we have 34, on the right we have 89, 90. Why 89, 90? Because we have split it there after 67. So 67 has gone up and 89, 90 has gone on the right side. So that is what we have done. Now we have to now draw the pointer, that is who is whose child. So who is whose child? If you see here, this will be that pointer that I am talking about. This is your pref pointer. This is your next pointer. This is your pref pointer. Right? So this is what I am talking about when I say that we are now just from a, instead of drawing that big box and those pointer rectangles, right, we will say this line itself is my pointer. Right? So this line itself is going to point to here, because 34 is less than 67. And where will this 89 and 90 be? It is greater than 67, so it will be against this line. That line, mind it, is a point. It's not a line. We are drawing it from a simplicity standpoint. It's not a line, right? It's a pointer, and then the line ends, right? So 89 and 90 is to the right of 67. Now who comes? 90 is done, 100 comes. So where will 100 go? See where will 100 go? 67, start from the root, greater than 67, go to the right, 89, 90 and push it here, 100 goes here. Right, so it is sorted, yes. So 100 also done. Next, you will have to do 2. So where will 2 go? 2 will go less than 67, but 2 cannot go because 34 is residing here. As I said, you have to sort it. So 2 needs 34 to move to the right. So 2 will wait for 34 to move to the right and then it will come in. So 2 comes in here and 34 is here. So that is how this current situation looks like. Now 36. What is the next node? 36, right? Yes, 36. So 36 will go here. That's a no-brainer because it is less than 67 and there is already a placeholder available for 36. Good that it found that. Now 36 goes there. 76, where is 76 going to go? 76 cannot go anywhere because there are no placeholders neither here nor there. But it is greater than 67, that part I know. So 76 actually should have come here because then it would have made sense, it is sorted. So that way 76 is there. Now if 76 needs to stay in this particular zone, then my new overflow is looking like this: 76, 89, 90, 100. This is my new overflow. In this, again, if I am a consistent, then what I will do, I will take just a minute, I'm getting a window pop up, let me close that off. Yeah, done. Yeah, if I'm consistent, then what I will do is I will take this as my median. So what is my median? 89 becomes my median, right? So 89 will go up. So 89 comes up here. So I will move 89 up. So 89 goes up here. Now if 89 has gone up there, 67, 89 is staying there. So now this area, if you remember, I said the right of 89 will be created as a separate entity, right? They will be, because we had bisected it. So the right of 89 will be created as a separate entity. What was the right of 89? 90 and 100. So I will create a separate entity for 90 and 100. So I will create something like this, where I will keep 90 here, I will keep 100 here, and I will remove these from here. These are no more required here because I have split it from that side. So this is no more required here, and this 76 now can find a placeholder, right? So 76 and 89 will now find a placeholder. Somehow this has become very slow for me. I don't know what you guys are seeing, but because of the continuous recording, the machine has become absolutely slow. But that's okay. Let's see till what time it continues. Yeah. So now what did we have? 90, 100 has moved right. 76 was supposed to come in. 89 has moved to the top. So I have to write 76 here. So I have to write 76 here. So this is how my current situation looks like. Now is this pointer correct? That is what we have to see, because I have 67. The right part of 67 is pointing to 76, which is correct, right? And the right part of 89 should point now to 90 and 100. Right, so the right part of 89, this particular line, right, so this particular line should point now to 90 and 100 because 90 and 100 is greater than 89. So that is how this particular thing looks like. Now what is coming in? We are having 53 coming in. So if 53 comes in, then 53 will go where? 53 will go, where does it go? Okay, so 53 is less than 67, so 53 should be coming here and overflowing. So there will be an overflow here. So 53 wants to stay to the left, but we have already consumed everything on the left. So there is an overflow. Is this sorted overflow? Yes. So if it is a sorted overflow, let us take this to the right where we will calculate the median. So 2, 34, 36, 53. Right? So what we will do is we will take this out. We will remove this. So it is better you wipe out everything, or you draw one more diagram below your copy just to explain each of the steps. It's not necessary that you show the steps. So you can draw the final tree also. If you have a pencil, you can draw the final tree also by rubbing the pencil and drawing it. So now what we will do, we have taken, so who goes up? 34 goes up, right? So 34 has to go up. So this is my 34 which will go up. So if 34 goes up, then 67, 89 will need to be pushed to the right. So what we will do is, we will just, instead of wiping that, I'll just create here one more block. I will say this is my 34, and I will remove this block on the right just to make some space. Right now, in the bottom, what will I have? I need to have a placeholder for my 8. Right, you remember that we had 8 and then 34. 34 has moved up, but 8 will need a placeholder. So 8 has a placeholder like this. So 8 will be here. And 36 and 53 is something that we will have to adjust. So 36 and 53 will come here. Now 36 and 53, that is something that we will need to maintain here as another placeholder. So we will have 36, we will have 53. Right? Now we will adjust the pointers. Don't forget to adjust the pointers, because you have done a lot of jugglery, and that jugglery now should be consistent. So less than 34 is 8. If less than 34 is 8, then we should take this line here and put it to 8. That's what we should do. Now the other thing that we also see is that 36 and 53 are greater than 34. So then this particular line should now go here. That is to 36 and 54. 67 and 89, wherever they were, they are perfectly fine. We have not changed that. Right? So greater than 89 is 90, 100. Greater than 67 is 76. And mind it, 76 should also be less than 89. Because we said that that is the right pointer of 67, but also the left pointer of 89. Right? Similarly, 36 and 53 should be less than 67. So that is how I am interpreting this. I hope all of you are understanding. This example will go on now. 53, then we have 51. So 51, if we have to add, then 51 will go here. So we will say that this 53 will go right. So 53 will come here. So 53 goes there, and 51 comes here. Right? So I will place it inside 51. So 51 now also has entered. Then we have 12. 12 will enter here. Then we will have 10. 10 will enter here. So this 12 we will move to the right, and the 10 therefore can come in here. Right? So we will do that. Then we will have 77. 77 will go to 77 can go after 76. So 77 will go here, and after that we have 69. So 69 will be here. So I will move 77 to the right. I will have 76 here, and this 76 will give way for 69 to come in. So I did not erase it and do it just the way I was doing it, but you have to assume that I'm erasing it just for the sake of time and not erasing it. So 69, 76, 77. So this is your final B tree. You see, all the leaves are at the same level. Every leaf has 3 nodes. Every leaf has 3 keys. Maximum 3 keys. It cannot have more than that. How many children are there? 1, 2, 3, 4. 4 children means m equal to 4. So all of that is getting validated here. So I hope you understood what we are doing on the right side. We are doing the median calculation. We are taking that median to the top, and then we are taking the right side, completely separate placeholder we are creating. Left side we are keeping as it is, and then adjusting the pointers. Mind it, very, 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 very important that when we are talking about this pointer here, then everything that we are keeping here should be not only less than 34, greater than 34, but also less than 67, because that pointer serves both 34 and 67. For 67 it is the left pointer, for 34 it is the right pointer. So 36, 53, 56 should be in that mode, 51, 53 should be in that mode. So that's on the construction of binary tree. What else we have? We have, I think, some theoretical questions. What are the properties? We have discussed the properties. That property table we have discussed. Does a B tree grow at its leaves or at its root? Who will answer this? Let's answer this in chat. Let's see if you can answer this. Does a B tree grow at its leaves or at its root? How does it grow? Yes, it increases at the root. The height of the tree is what they are asking. The height of the tree grows because of we putting more leaves? No. So Farhan, we are not putting more leaves there. We are putting leaves. We are putting keys inside the leaves. But that's not growing the tree. The growing the tree means I have to create one separate entity at the top, another separate entity at the top. That's how we will grow the tree. That's how we'll increase the height. That means it's a bottoms up growth, right? So imagine that in that sense. Purpose of B trees for which appropriate, I have already explained in the form of a disk read, so that you can read maximum content from the disk. So that was all from a B tree perspective. Let us quickly get into the quiz. Yes, Farhan, as the median element always gets promoted, that is where the growth happens. Okay. Quiz time. Yeah, I mean, 66, 82. Okay, let's start. Okay, Ayush. Okay, Farhan, I see you at the top. Good. Shayon Meghna. 44%. Increasing the number of keys decreases the height. Come on, guys. If I have 10 keys, and I mean, if I have the keys in a particular tree as 10, and I say that I am giving you only one placeholder, then you will need a particular height. Now I say that I will give you two placeholder, then your height should decrease now, because in that two placeholder you will accommodate more nodes. So it doesn't increase the height, increasing the number of keys of the tree. So imagine this big rectangle, I have increased the number of keys that I can hold. Earlier I used to hold 1, now I can hold 5. What will happen? The total number of keys in that, the total number of nodes in that tree is constant. So I am accommodating more nodes now inside myself, then the height will reduce. Right? It's a common sense here. 42%. Come on. Good. Farhan, Shayan, Norindam. Okay. Many keys per node. Yes. Many keys per node. That's the right thing. Nine. Reduce tree height to 1. Purpose cannot be to reduce tree height. Purpose has to be a practical purpose. Reduce tree height to 1 is an outcome. It's not the general purpose, right? It's not the utility. They are asking for the utility. Good. Okay. Leaderboard does not change much. Let's move on. Let's see how many of you get this correct. Still I think it's okay, because it was a bit difficult to guess that the word was multiple. Yeah, someone says lols. Okay, multiple spelling wrong. Pointers, kuch bhi, huh? Pointer. The hint is there. Why are you giving pointer? Anyway, I'll end the assignment. Meghna, Shayon. For a change, Shayon has come second. Farhan has come in first. Good. Okay, we have one more quiz and one more topic. I think 15 minutes is what we will take. Only thing is, my system is now so slow that I keep moving my mouse and nothing happens. It's because the live streaming is going on for 9 hours now. I should have stopped it at lunchtime. Okay, now if I am talking about a B plus tree, then it is exactly the same. I won't say exactly the same, 90% the same as B tree. So what is the difference that we will call out is that we will say that instead of saying that my node here has data, so the nodes here will have data, which is my leaf nodes. They will have data. So some node might be this, some node might be this. You have seen this now, right? And they will also be linked together like this. So there will be a associativity from left to right of the leaf nodes, and on the top we will have some nodes which will have not data, but we call them as routing numbers. So the routing numbers will tell us where to go. So routing numbers might say this is to the left, this is to the right, just the way it was happening before, and this is to the right of this, right? And similarly there could be one more routing number at the top like this, which will say that this is to the left, this is to the right, something like this. So when I say routing numbers, I am saying that in this particular block, in this particular block which is not leaf, we do not store any data. All data is stored here. All data is stored here. This line is crazy. Okay, so all data is stored here. That is what I am trying to say. Now this will be clearer when it comes with an example, but what I am saying is that we were trying to store data, multiple data in one keys. Here also we will store multiple data in one keys, no changes. There also we had the concept of m being the order, right, and k the number of keys being equal to m minus 1, right? So that stays here, that also stays. There will be m minus 1 maximum keys. So here you will have n minus 1 maximum keys. Here also you will have m minus 1 maximum keys. But what are those keys? Here the keys are the data, the actual data. Here the keys are not the actual data. So it's the challenge, I can't see even the pointer. Okay, so here the keys are not the actual data. Okay, so these are what? These are routers. What are routers? I have to explain to you with an example. So that's what the B tree definition says that the actual data resides only in the leaves, whereas in a normal B tree, I think my video will be paused because I'm getting a call. Oh. अरे यार. Thanks for pointing out, guys. I'm sorry for that. I have to repeat this. Don't mind repeating it, but my machine is in such a sorry state that repeating means drawing again. Okay, let's try it out. This is what I was trying to explain. Let me see if without drawing I can explain you again. Camera off. Yes, because I was getting a call. That's why whoever called me, my camera got switched off. 1 minute. Should switch back on now. Yeah. Okay. Now what I'm trying to explain is B plus tree. As I said, B plus tree is the same thing. B plus tree is a same tree concept where we are saying that all my data will reside here in the leaf, unlike the B tree where I said data can reside here, data can reside here, data can reside here, here, wherever it can reside. In B plus tree, all data will reside here. Why here? This is the leaf node, that's why. Then what are these? These are called router nodes. These are called all router nodes. So these router nodes will be telling you which direction to go, right? And that's something that we will explain through an example. We also have the same concept of m and m minus 1 here. M is talking about the order, which creates m minus 1, which is the total number of keys. Total number of keys here will be whatever we will get from m minus 1. That will be the total number of keys here, and that is also applicable here. It's not that these are orphans. The same rule is applied for the keys. All of these are keys. This is a key, this is a key, everything is a key, but that key is not a data for the non-leaf internal nodes. These are all internal nodes. These internal nodes do not have data as the keys. They have routers at the keys. That is the only difference between B and B plus tree, right? So remember that at the leaves we have the data, at the non-leaves we have the routers, or we have the regulators. Some books call it differently, but you will understand what when you see what the adjective is being called. So here the data is stored, see, in a B tree the data is stored where? The data is stored in internal nodes plus the leaf nodes. But here in B plus tree it is only stored in the leaf nodes. The leaves are linked. Yes, this is something that I forgot to tell you. I told you then, but you were not able to see the screen. So the nodes are linked. So this node is linked to this node, and this node is linked to this node through this pointer. So that if you come here somehow, you will get this entire data, and that is the advantage of B tree. Now you will understand the advantage. Somehow from here, if through the router I reach this node, then I can get the entire data from here. I don't need to go anywhere. It's just a sequential iteration to get the entire data, because I have this wonderful pointer, right, which takes me to the next node. All I need to know is do a login kind of a model, come to this particular order, and then from here also I can get the entire node. If I come to the leftmost, I'll get the entire data, and that is why all the data resides on the leaf. If you come here, then go to the end, you'll get all the data. That is the whole thought process of B plus tree, right? So it's one more step ahead of the B tree, and it is typically used for large data now. Database is where B plus tree is typically used. whereas disk is where, or hard disk and files is where we use a B tree, right? So those are the two differences that we are talking about. Promotion rule, here we are promoting the data. The promoted key disappears from the child, and here the promoted key remains in the leaf node. We have not seen this, you will not understand this. Wait for some time. We will do this tree and it will be clear. So this, I think, is the last but one slide for today's session. Just concentrate for the next 10 minutes. You have been with me for 8 hours. Concentrate for the next 10 minutes. So first things first, we will create the placeholder and we will push that particular element to that placeholder. So we will say that these are my placeholders. Why did I take 4? Because my M is equal to 4 and my total number of keys therefore will be equal to 3. So that is why I took 3 placeholders here. So 1 comes in, 2 comes in, 3 comes in, and it has to be sorted, by the way. That requirement does not go away. Right now, what's happening is that you have put that data in the 1, 2, 3. The next data that wants to come in becomes creates an overflow. Right? So when 3 comes in, it creates an overflow because you have only 3 nodes that, or only 3 keys that can be taken. So what will happen is we will be splitting. So we will be let's draw the problem first and then I'll draw the solution. So the problem is that 4 comes here and says I don't have a space, I have an overflow. So what we will do is we will split this by the median, right? So we will split this by the median here. Okay, so that means that on the right side we will create a placeholder for 3 and 4. Now unlike the earlier example, we are not moving the data to the we are not moving away the data to the top. That means this data will stay here, 3 and 4 will stay here. Okay, 3 and 4 will stay here, and this is one more placeholder that is there, and it will have one more placeholder that is there. So it will be there, the placeholders will be there. So 1, 2 and 3, 4 have been split. Now at the top, therefore what gets created is the router. So the router, what will be created is the right part of the split tree, the leftmost element of it. Again I'll repeat, the right part of the split tree, the leftmost element of it. So this is my right part of the split tree's leftmost element. So this goes up not as a data but as a router, as a friend to tell you where you need to go. So then this 3 will point from this pointer to here. That is, everything to the left of 3 is 1 and 2, which is less than 3, and everything to the right of this 3 will be greater than equal to the router. So the router says that you come to me, I will tell you where to go. So 3 tells you go to my left, 1, 2 will be there, or go to my right, 3, 4 will be there. So that is what is happening. So now if you understand, then let's take the next element. So the next element is 5. 5 will find a placeholder here. One more time I am repeating that I have kept all the data in my leaf. So 3 has not gone to the top, 3 stays in the leaf. What goes to the top is a different entity. It is 3, but it's a different entity. It is for a different purpose. It is no more a data. The data is still there at the bottom. Right? So 3, 4, 5 comes here. Next we have 6. 6 goes to the right and it overflows. So 6 will go to the right and it will overflow. So 6, if it comes here, it will overflow. Right? So this creates an overflow. So what we will do, we will split. So if we split, how do we split? We will say that we will take this off and we will split it like this. So this will be my 5, this will be my 6, right? And don't forget that we have to also put the arrow like this, because as I said, they are linked together. So 5 and 6 comes here. Who is the leftmost in the right split? 5. So 5 will go to the top. That is my router. So 5, I am not moving to the top. 5 I am still keeping below, but a different entity of 5 goes to the top, and that different entity says, I will help you with the routing approach. So the routing approach says now that this 5 is linked here. So anybody who comes to 5 and goes to the right pointer can go to 5, 6 block. Anybody who comes to 3 and goes to the left pointer of 3 can go to 1, 2 block, right? And if he goes to 1, 2 block, he can get the entire data set. That is the beauty of B plus tree. So now we have done that. 6 has gone there. Now we have to give 7. 7 will go here. Then we will have to take 8. 8 will create a overflow here, because 8, if I put here, it creates an overflow. So what I will do, I will create another node for the split, and 7 and 8 will be put there. And I will remove 7 and 8 from this side. I will remove 7 and 8 from this side. Right? So this is what I will do. And then this 7 will be the leftmost of the right division. Right? So leftmost of the right division will go to the top as the router. And this particular line will be drawn so that it says that if somebody comes to 7's right, then he will come to 7, 8. So that is on the 7, 8. Now we are going to 9. 9 simple, it has a placeholder here itself. So we will put the 9's placeholder here. Next we have 10. Now 10 is going to be interesting. So leaf 7, 8, 9, in this area 10 overflows. So 10 overflows here. That means we have to create a separate entity for 10, 9 and 10. So 9 and 10 we create a separate entity. Right? This is the entity that we create. For lack of space, I am creating it at the bottom row. You will create it there itself, because it has to be at the same level. Everything has to be at the same level. So what will I do now? I will remove this 9. I will remove this 9. So 7, 8, 9, 10. Okay, everybody is happy. Now what happens? 9 has to move to the top. So now comes the fun part. 9 is moved to the top, and 9 creates an overflow. So when 9 creates an overflow, then the way we will tackle it is in the same way we've tackled B tree. Right? We tackled B tree by saying what? We had taken, you remember we had taken the median approach, 3, 5, 7, 9. Then we said we will divide it here. So 7 and 9 will be the right block, 5 will move up, 3 will be here. So we will do the same thing. So we will now remove this, and we will draw what we were talking about. Then we will readjust the pointers. Nothing to worry on that part. So we will say that on the left we have one node for accommodating 3, and on the right we have one node for accommodating 7 and 9. Right? And I will move to the top. I will move to the top what? 5 will move to the top because it is a median node, just like B tree. It will move. So yes, in this non-leaf node, we are moving that split element to the top. There is no concept of that being staying at that layer as well as going to the top. No, that is not the concept. So for all routers, we are following the concept of B tree. So this now becomes 5. So how do we adjust the pointers? Pointers say that 5's left is this, 5's right is this, and this 3's left will be this, 3's right will be this, 7's left will be this, 7's right will be this, and then 9's right will be this. That is your final tree. Easy as long as you practice it out, but of course the concept is that at the lower level you are not moving anything to the top. All data is here. Put the arrows so that if you come to any of the nodes of the leaves, you can extract all the nodes. So put the arrows. So that's on the B plus tree. This is the last slide. B plus tree, both internal nodes and leaf nodes have keys. Both internal nodes and leaf nodes have keys. In a B plus tree, yes, they have keys, but then we call them as keys. Actually, it is a debatable question. I would say true. Everybody is a key. Now, one key is data, another key is router. So both internal and nodes and leaves will have keys. I will mark it as true. Somebody will say key means only data. Then that becomes ambiguous. And B plus tree and B tree, I have already explained you the difference in the last slide here. So how does it differ? Here I have already explained to you through the properties what is the difference. Anyway, if you want the structured difference, it is here. We will not go through it. It's more of theoretical concept. But I hope you understood what is a B plus tree, how it is related to a B tree, and what is it used for. I said it is used from a database perspective, whereas from a disk usage perspective, we use a B tree. So that was today's session. Thankfully, we have closed today's session in the right time. We will do the quiz and then we will wrap up. Unfortunately, that 15 minutes I couldn't do. Tomorrow I'll see that 15 minutes I'll definitely want to make up. Who is asking? Let me see the question and then I'll start the quiz. Why 5? Can we take 7? Islamic talk. Why 5? Let me see where I took 5. Oh, here. Yeah, you can take 7. Where were you, Islamic talk? I was talking about this in the first part of when we were talking B tree. I said when you have even number, then you can take either 5 or 7. Doesn't matter. But what you take consistently. Only when you have odd number, then the number becomes constant. But for even number, you can take either of that side. Yeah, so I think that answers it. Yes, Partho, there is a wastage of space, but you will have to do a trade-off somewhere. You want speed here. That is, you want to come to some node and get all the data. What is that? Speed. So to get that, you have to waste some space. That is the fact of life. Yeah, so I didn't understand why people are insisting that it has to be 7. As I said, it can be either. It can be 5 or 7. I have been consistently taking the second element as the one that moves up. So that is why I'm taking that as the person which moves up, and I'll take that consistently. If you want to take the third element to move up in a 4-element key, please feel free. There is no problem about it. Okay, so that's on. My throat is absolutely gone. Now let me see how much I can do for tomorrow. Okay, so B plus tree. I hope you understand it's not a matter of joke to continuously speak for 8 hours, 2 days at a length, and tomorrow also I'll have to speak. And I took this on me. Nobody told me to do it. I did it because I felt you might be beneficial out of it. So I hope it is helping you, and I hope that all this effort that both you and me are putting are going in the right direction. Please continue joining. Please continue to be benefited of it. A lot of effort is being put for this. I hope that I am able to make you at least understand some portions of things which you have not understood in the past. Oh, sorry, I again missed on sharing the window. Come on. How many are here? 81. So let's go to 70 and see. Okay, let's start. I'll start it. $78. Okay, good. Very nice. Okay, you're listening. Arindam Shayan Ongod, okay. No new name, 65%. Forward links is a confusing statement, I understand. But as I said, select the most appropriate one. It's going to be a link structure for faster sequential access. That's more appropriate if you think about it. It is a forward link, but it is also a link structure for faster sequential access. So that way you'll have to select the most appropriate one. I'm sure some of you will get confused on this, thinking whether you are doing it for a B plus tree or a B tree. That's why the number will fall. But it's better, I think. 54 means Gitika Kashyap, I've seen Abhishek Shaha, good. Gitika, good. Angad, Alim, Ghazi, Sahil, Sharma. Okay, good. Only leaves hold actual data. So all of you understood that they are talking about B plus tree. I thought you will overlook that, which is good. Good. Okay. So this is okay. At least you have been attentive till the last moment. Thank you for that. Shayan Das again. Good, Shayan. Gitika, good. Alim, good. So with that we will end. But before ending, I just wanted to make one announcement. Tomorrow, second half, we are doing doubt clearing. If you don't put the doubt clearing things inside the Excel that I have shared, the shared Google form, I've shared a Google form, just fill it up there. Then tonight I won't be able to work on those. I won't be able to put it up as a slide in front of you, right? So whatever comes by tonight 12 o'clock, I will put it up as a slide. Otherwise it will be an ad hoc, and I might be scribbling things, right, to explain to you. So please put whatever you want to discuss, which is still a doubt, and I will take it up tomorrow. Please don't forget it. Thank you. Chalo, good evening.